Shaders are essential to making beautiful games. Both 2D and 3D projects rely on them extensively, and if you don't understand the basics, your games will be severely limited. So, in this course, you will learn everything there is to know about 2D shaders in Godot. We will create over 40 shaders that cover every major topic. It starts with shader fundamentals, goes over basic projects. We will cover vital math concepts like trigonometry and matrices and use that for advanced effects. Extra lessons for math will also be included if you struggle with that, and there will be a ton of examples and drawings to help you understand. This course will also include advanced concepts that are rarely taught, like using world and canvas space, light shaders, and subviewports to combine multiple shaders. By the end of this course, you will stop seeing shaders as black magic that you copy from a website and instead become a powerful tool that will make your games significantly more impressive. For this YouTube video, I will still cover all of the major parts, and you will learn every major shader concept. However, the more interesting looking shaders are behind a paywall. You can buy the course for £5 on Patreon, and if you subscribe there for £5 a month, you can watch all of my courses. Otherwise, the course is available on Udemy for $10 to $20 and on Flipped Normals for $10. So I hope you enjoy. Okay, let's talk about shaders. In the simplest terms, a shader is code that can change the position, color, alpha values, and light behavior of a pixel, among loads of other properties, but those don't matter as much. For a bit more detail, to display a graphic, a lot of processing needs to happen. This is called the graphics pipeline, and shaders allow you to customize parts of it. In the Vertex step, you can change the position of a pixel, and the Fragment shader lets you change their color, transparency, and how they handle light. However, all of this runs on the GPU, which complicates things quite a bit. If you have used basically any traditional programming language, you have coded on the CPU, which goes through your code line by line and executes it in sequence. GPUs, on the other hand, are designed for parallel computing. There are thousands of relatively weak cores that all work simultaneously. If you have a task with a lot of simple calculations, this delivers incredibly fast results. And computer graphics are the main use case. To get proper graphics, for each pixel, we need to do some basic math to get things like color, position, transparency, etc. It's not hard to do, but we have to do it for millions of pixels within a fraction of a second. Because of that, you don't run shader code once. You run it for every pixel simultaneously. For an example, imagine you want to draw a circle in GD script, so on the CPU. You would call draw circle. It's a simple method that wants a position, radius, and color, and then draws a circle. In a shader, so on the GPU, we have a texture and run code for every pixel. So we can't just create a circle. Instead, we would define a center point and calculate the distance to it from the current pixel position. If that distance is within a threshold, we show the pixel, otherwise it will be hidden. The formula for that would look like this. Getting started with this kind of logic is frustrating and often confusing. Just look at the circle formula. We created a circle by defining a float. It just feels weird and you need time to get used to it. Let's actually do two more examples. First, the Zelda-style stamina bar. This one actually starts with the Godot logo. Most shaders in this course do. We first remove the color and then define a large and small circle. If we remove the letter from the former, we have a ring. Next, we use trigonometry to cut out an area by the angle. If we combine the two and add colors, we are done. Next up, the fire. This one also starts with the Godot logo, although any texture would do. We once again want to remove the color and then use math formulas to get a pill kind of shape. Then we get a noise texture and scroll it. If we combine the two and clip the values, we basically have the main shape. Finally, we can add colors and we are done. Both shaders look impressive, but can be done with a few lines of code that actually become trivial once you develop an intuition for it. That does take some time though, but don't worry, we have a lot of examples to go through. And before we start, the definition of a shader I used so far is oversimplified and not entirely correct. I will fix that by the end of the first major part. It's simply not necessary for now. To get started, all you need to know is that shaders allow you to change the position, transparency, color, and light behavior for every single pixel. And this happens in parallel. Time to create our first shader, for which we are turning the Godot logo into a circle. Along the way, we are also going to learn the shader fundamentals. Here we are in Godot, and I already have a scene. We have a node 2D at the root, then we have a sprite 2D called icon. This is just the Godot logo. And finally, we have a camera 2D that zooms in by a factor of 5. The purpose of that is that when I run the scene, the Godot logo is a bit more visible. That's all it does. Besides that, inside of this scene, we have nothing else. There's no logic or script or anything like that. In fact, for this entire course, we are almost always starting with the Godot logo, so you don't have to download any project. That being said, a couple of shaders do look better with specific art assets. If you want those, you can find them in a Google Drive folder. Also, if you look at the folder setup in the project, at the moment, we only have 2 folders. But throughout this course, I am going to add a lot more. If you want to follow all of this exactly, you can find a shader starting project. This one has all of the folders and the art assets. Might make your life a bit easier. Anyway, let's create our first shader, for which we have to work on the sprite, because we can only add the shader to some kind of visible node, which for sprite 2D means that we have a texture. But much more importantly, what we need is a material, which inside of a sprite 2D is down here, and there we can add a canvas item material and a shader material. Add this one, and then you get the shader property. In there, I want to create a new shader. Inside of the next dialog, we have a whole bunch of options. Number 1 is the type. There we can create a shader and a visual shader. The basic shader is code-based, while the visual shader uses nodes. And this is what we want to start with. After that, we have the mode. Spatial is for 3D meshes, canvas item is for 2D objects, and then we have particles, sky, and fog. For this entire course, we are always going to use a canvas item. Then we have templates, which we can't even use, so just ignore it. Built-in shader means that you are not creating a separate file. Instead, the shader is part of the node, which you very rarely want to do. Instead, inside of a path, you want to create a new shader file. For visual shader, the file ending is tres, and the default file name is the name of the scene. Fragment basics here, and if you look at the top, there we also have fragment basics, which is totally fine. Just name it whatever you want, it doesn't really matter. Then click on create, and now, inside of the folder, we have fragmentbasics.tres, and if you click on the shader, like so, you can see the shader editor. Let me expand this and rearrange the logo like so. That's much better. Inside of this editor, you have 3 workspaces. Right now, I am in Fragment, but by default, you usually have Vertex open. This is probably what you have seen first. Inside of the Vertex shader, we can update the position of all of the pixels via the Vertex property. You have a few more properties, but they don't matter that much for now. Inside of Fragment, we can change, most importantly, the color and the alpha values of all of the pixels. We also have normal values and light behavior. I will cover these properties later on, but the most important properties are color and alpha. You are going to use those the most, by far. Finally, we have the light shader, and there we only have 3 properties: light, light alpha, and shadow modulate. The light shader isn't that commonly used. We are going to, at least for now, mostly work inside of the fragment shader. To understand these properties, you have to understand the circle next to them. Most importantly, it connects the different nodes. So later on, we can add different things to it and then combine different values. Besides that, every circle has a color. This tells you the data type that is expected. A gray value is looking for a float, meaning for alpha, we want to have something like 0.4. For the color, we have a dark purple. This stands for a vector 3. Colors inside of a vector are RGB values, meaning we have red, green, and blue. For each value, we have a range from 0 to 1, with 1 being the full amount. Same for alpha, by the way, this goes from 0 to 1, with 1 being the full visibility. Most values inside of a shader are normalized to a range of 0 to 1. That makes it much easier to work with them. To actually create something, we need nodes. And those you create either by right-clicking, then you get the Create Shader Node dialog. You can also get this one by clicking up here, Add Node, same dialog. In this thing, you have a lot of drop-down menus, and you can pick different things. This works exactly like the Add Node system in the scene tree. And like in the scene tree, most of the time, you use the search function. For example, for now, I want to create a float constant, which is just a float, so we can give it a value, let's say 0.6. What is important to understand now is that if a circle on a node is on the right side, it means that this node is outputting data. Whereas if the circle is on the left side, then it is accepting some kind of input data. Visual shaders always go from left to right. So what we can do now is connect the float constant to the alpha value, and then we are getting something. Now the Godot logo is less visible, and we have sharp corners. Why did that happen? And to simplify things a bit, let me change the value here to a 1. That way, we have no transparency at all for the entire logo. Any texture is always a rectangle. And if you want to have rounded corners, like in the Godot logo, this thing here, then you have to create transparent pixels in the corners. All of these pixels do have a color, but you can't see it by default because the alpha value is 0. Whereas for all of these pixels, we have an alpha value of 1. That's the default, but that we are changing with this shader. This one is looking at all of the pixels, like this one, this one, this one, this one, and this one, literally all of them, and it sets an alpha value of 1. So there's no transparency in the texture. That's all we are doing at the moment. Because of that, the corners are visible. To add a bit more math to it, you can add more nodes, like for example, the multiply node. Inside of operators, we have float multiply. The data type here is quite important. This one says float. There we have an integer. And if you scroll down, we have vector 2, 3, and 4. At the moment, we only want to work with a float multiply. Create this one, and then you get 2 inputs and 1 output. You can multiply 2 floats, and then you get an output, which also has to be a float. And if you want to connect this node to the current operation, you can simply drag and drop it on the connection, like so. Godot connects it automatically. Once we have done that, the Godot logo disappears. For every single pixel, we are multiplying 1 with 0. The result is always going to be 0, and that is the value for all of the alpha values for every single pixel. Hence, the logo is invisible. But if you click on this field, you can change this to 0.5, for example. Then we are getting 50% transparency. You could also create another float constant and connect it like so. For some kind of value in here, let's go with 2. Then we have all of the pixels without transparency. Important to note here, at the moment, we are multiplying 1 with 2. So this operation is giving us a 2. But inside of alpha, the maximum value is 1. We can't be more visible than 100% visibility. As a consequence, the 2 is clamped to a value of 1. And I guess with that, we have the most basic math operation inside of a shader, which still isn't very impressive. This kind of operation just doesn't do very much. What I guess is slightly more interesting is we can create a vector 3 via the vector 3 constant node. Click on this one, and then you have a shader where you can set X, Y, and Z. If you connect this to the color property, then we get a black color, because now for red, green, and blue, we all have 0. As a consequence, we have no color, hence it's black. If I change the X value to a 1, then we're getting a red color. At least this one is a bit more visible. That being said, it's still quite limited. To get actually interesting effects, you need to have some input data, meaning you want to know the current color of a pixel, the alpha value of a pixel, and the position of a pixel. That information you can get via two nodes. The first one is called color. All the way at the bottom, you want to have a vector for color. Create this one, and via this node, we have a golden output. This is for vector 4. The color scheme for the values is a bit weird. Dark purple is a vector 3. Light purple, down here, might be a bit hard to see, is a vector 2. And finally, a golden circle is a vector 4. And besides that, a gray circle is a float. I don't know why they chose this color scheme, but well, it is what it is. You do get used to it quite fast. What is much more interesting, via this drop-down menu, you can see and select all of the values. We have red, green, and blue, along with the alpha values. Although what might be a bit confusing here, for this red, green, and blue, we don't get gray like we do for alpha, but these values are still floats. Don't worry too much about it. What is much more important for now is that you can get these values, like for example the current alpha value, and connect it to alpha. That way, we have not made any change. We are reading the current value and then setting it to the current value again. We are going basically in a circle. But now what you could be doing is to use the blue values of the texture and set those to the alpha value. That way, since the pixels of the actual Godot symbol have a much higher amount of blue, they are more visible. The background, on the other hand, is much darker, so we have less blue and hence less alpha. We will be looking at color in much more detail in the next part. For now, I am not too concerned, so let me delete this one. Instead, I want to look at another node, which is called UV. Vector 2, UV. This one gives you the position of a pixel. And to talk about it in a bit more detail, a UV coordinate is just a fancy way of saying X, Y coordinate. That's all it is. It gives you the position of the pixel, and the way it works is if we have the Godot logo, the U values are the horizontal position, while the V values are the vertical ones. The top left position is always 0 and 0, while the bottom right one is 1 and 1. Like for the colors and the alpha value, these values are normalized to a range of 0 to 1. The actual Godot logo is 128 by 128 pixels. But inside of a UV coordinate, we are going from 0 to 1. This makes it much easier to connect the different values. Just for another example, if we were on the top right, we would be at 0.9 for U and 0.1 for V. Back in Godot, if you click on the drop-down icon, you can get the red and the green values, which stand for U and V. One thing that can be a bit confusing for shaders is the naming of the variables inside of a vector 2. Sometimes they're called red or green, other times they're called X and Y, and sometimes they're called U or V. All three of those basically mean the same thing. We are looking at the vector 2, and we're getting the X value or the Y value. If you click on the red value, then you get a color preview. On the left side, we have a black color, and on the right side, we have a white one, which means we're going from 0 to 1. For these kinds of previews, Godot has to create a color, which is always going to be a vector 3, for which, as a reminder, we will need R, G, and B. Since the red color is a float, let's say here, we get a value like 0.1. And this value is used for both red, green, and blue. As a consequence, we get a really dark gray. You could connect the red color to the actual color of the output, and we would be getting the same value. I will talk about the conversion from a float to a vector 3 in the next video in much more detail. There are some rules that you have to keep in mind. For now, it's not too important. For the green color, we do the same thing on the vertical axis. And if you click on this eye symbol, we get something a bit weird. But if you think about it, I think it does make sense. Once again, Godot, to create this color, needs to have a vector 3 with red, green, and blue. Since we only have red and green values, blue is always going to be 0. In this picture, there's not a single bit of blue. But for the red color, we are looking at the x values, meaning on the left side, we have 0, and on the right side, we have 1. So if you only look at this top bit, we go from black here to pure red up here. And then for the green values, we are looking at the y position. Up here is 0, and down here is 1. Once again, we start at the pure black color, and then in the bottom left, we have a pure green color. If you go down diagonally, you're combining these two values. In the bottom right, we have the full amount of green and red. So down here, we have yellow. To actually use this value, let's say I want to get the horizontal position of every single pixel and connect it to the alpha value. And now we are using the pixel position to set the transparency. On the left side, since the x position here is 0, and we're using that value for the alpha value, we're getting an alpha value of 0 as well. But the further to the right we go, the closer we are getting to 1. And on the right side, we have a value of 1. So no transparency anymore. The same thing we can do for the green or y values. Now we're doing the same thing on the y-axis. For both of these, we get a gradient. And to turn this gradient into distinct values, you need one node that you see a lot. It is called step. Make sure you get float and step, not smooth step. If you have that, you get 2 input nodes and 1 for the output, in which we have to define an edge and a value called x here. For the edge for now, let me set a value of 0.5. And then I don't want to use the y values. Instead, I only want to look at the red values and connect those to the x value. The output of this node then goes to the alpha values. And now we can only see the right side of the logo. The way to think about it, if I enable the preview of the step node, you can see what's happening here. Step is comparing the value, x in this case, against the edge. If x is smaller than the edge, the return value is going to be 0, which would, for example, happen if we are here with an x value of 0.2. 0.2 is smaller than 0.5. As a consequence, we are getting 0. And the color value Godot is generating from that is black. So this pixel is black. However, if we are here with an x value of, let's say, 0.7, then we have a value greater than 0.5. So this value is going to be 1, like so. This would place us here. The resulting color is white or 1 as an output, which we're then using for alpha. As a result, only the right side is visible. And by the way, what you can do as a really neat trick is to use the current value as the edge, and then the actual value can be a constant, like 0.5, for example. Then you get the inverted value. Can be super handy. UV is very often used with the step node. These two go very well together. And with all of that covered, we can do an exercise. I want you to turn the texture into a circle, for which you want to look at 2 additional nodes. One is called distance, and the other is a vector2 constant node. Just remember what I talked about in the last video on how to create a circle. If you use distance with a vector2 and the UV coordinates, you can already create a circle. Pause the video now and see if you can figure this one out. All right, let's go through it step by step. Number 1, I don't need this step function anymore. For now, I want to look only at the positions. We have the current pixel position via UV. Besides that, we need a center position for this texture, which we can create via a vector2 constant. For this one, we want to find the center of the UV coordinates. Since we know that they always go from 0 to 1, the center point has to be 0.5. And then we want to get the distance between these two, for which Godot has a distance 2D node. Connect all of this, and then if I show the result, we have kind of a circle. We can also connect all of this to the alpha value, and then we get something that's not terribly impressive, but we are getting there. I hope so far all of this makes sense. We basically have a center position via this node, and then we are looking at all of the other pixels and their position via the UV coordinates. For example, a node here would be reasonably close to the center, so the distance is quite low, let's say 0.2. This would be the alpha value for this pixel, quite low. We would be vaguely here. However, for a node very far away, let's say up here, we would have a much greater distance. For this one, let's go with 0.7. This would place us up here. The alpha value would be much higher. So this pixel is much more visible. This we now have to convert to a proper circle, which we can do via the step function. Basically for this one, I want to set for now an edge of 0.5 and then connect the output of distance to the x value and then get the actual alpha value. And with that, we are cutting out a circle. A good start, but not exactly what we want. For the proper value, we want to invert these two, which we can do very easily. The edge should be the distance, and then the x value is going to be 0.5. And now we have a circle that we can also customize. If you change this x position and change the x value, you can move it left or right. And if you change this x value, you can make the circle larger or smaller. And that would be a very basic shader to create a circle. Let me clean it up just a bit. I guess at the moment, if you want to play around, just look at more nodes and see how you can connect them. That is the most important thing to understand at the moment. Although maybe watch the next video first, because to connect different nodes with different kinds of data, you have to understand a couple of important rules. But this part has gotten quite long, so let's finish it here. Now that we have the basics of shaders, we can look at stuff in a bit more detail. Most importantly, I want to look at colors and how to convert values. So how could you convert a float to a vector 3 to get a color, for example? Back inside of Godot, I have the same setup I had before. Now we are in part 2, Fragment color. Like before, I want to attach a shader to a sprite 2D, for which I want to go to Material and then create a new shader material, in which we want to create a new shader, a visual canvas item shader called Fragment color.trace. Create, and now we want to work inside of the fragment shader, like before. We pretty much only worked with the alpha values, for which we needed a floating point value, which in turn updated the alpha values for every single pixel inside of the texture. For the color, we will need a vector 3, which we have already created. Vector 3 constant, this we want to connect, and then we can set any color. 1, 0, and 0 is the full amount of red, no green, and no blue. So we are getting red. If I have 1 for all 3 of them, we are getting a white color. Besides a color free constant, what we can also do is to add a color constant, where we can set the color right away, like you have probably done many times before. Let's go with a purple-ish color, something like this. This color value is a vector 4. We have a golden circle with red, green, blue, and alpha values. And now you might be wondering, how can we connect this vector 4 to a vector 3? And well, let's just try and see what happens. It just works. Whenever you have a vector 4 with red, green, blue, and alpha values, and you convert all of that to a vector 3, then the last value, so the alpha value in this case, will simply be discarded. You could still use it though. So for example, in this case, you could connect the alpha value to the output alpha value like so. And since this value for color constant is 1 at the moment, or whatever value you set down here, we're getting that value in the output as well. If you want to go from a vector with more values to fewer values, the extra values will simply be discarded. And the other way around, let me re-add the UV values. As a reminder, this one looked like this. On the x-axis, we have the red values. On the y-axis, we have the green values. And if we go down diagonally, we are combining the two and get yellow. Connecting all of that to the color is giving us the same output. For the color right now, Godot, once again, wants to have a vector 3 with red, green, and blue, but we are only giving it a value for red and green. So blue is going to be 0. Finally, what if you assign a float, so a float constant with any kind of value, let's say 0.4, to a vector 3? Well, if I do it, we are getting a grayscale value. Just like before, we want to create a vector 3 with red, green, and blue. And now we are giving this value only a float, so a single value, which Godot then has to turn into a vector 3. It is doing that by assigning the same value to all 3 parts of the vector. All 3 of those are going to be 0.4. The result is going to be a grayscale value, which you can actually use really well by using the color node that you have seen earlier. All the way at the bottom of add node, we can create a vector for color, which is different from the color constant. Do be careful here. The color constant is simply a color that you can define. The color node itself, let me create it, is giving you the current color and alpha value of every single pixel. Meaning, if I connect this to the color, we don't get any change. We are reading the current color value and then setting it to the output. Once again, we are going in a circle. If you want to turn this color into a grayscale value, all you have to do is pick either red, green, or blue, and then set it to the color value. And then you have a grayscale value that you can customize depending on which color you want to prioritize. Imagine we are looking at this pixel here, which is quite blue in the original. So for example, we might have 0.7 for the blue value, 0.4 for the green value, and finally 0.2 for the red value. We can choose any of them, and this is going to determine how bright this color is going to be. If we chose 0.7, like we're doing right now, then this color is going to be quite bright because we do have a lot of blue. But if we chose the red color, it's going to be quite dark. We're basically turning this float into a color by assigning it to vector x, y, and z. That's all we are doing here. With that, we have all of the rules to convert values. If you understand these, you can connect nodes much better. Now, before we are going to do an exercise, there's one additional node that I want to cover, and that is called time. If you create this one, you get a floating point value of the current time. Or to be a bit more specific, the time that has passed since the scene was created. If I attach it to the alpha value right now, then we are simply setting the alpha value of every single pixel to 1. That is because I created this scene quite a while ago. But if I run it, then you can see the Godot logo is slowly emerging. Hence, we're getting the project time. Now that we have covered that part, let's do an exercise. I want you to have no blue values in the Godot logo at the start of the scene. Only add those over time. And the end result should be Godot's original colors. Avoid adding too much blue to the texture. As a tip, check out the nodes vector for recompose and clamp or min. Both would work. Pause the video now and see how far you get. Number 1. We have to separate the colors. For which, first of all, we need the original colors. So vector for color. In there, we can get the red, green, and blue value, and we want to remove the blue one. For which, basically, we want to create a whole new vector 3, which we can do by using vector 3 compose. The difference, let me add this one, and then also add vector 3 constant. The difference between the two is that a vector 3 can accept an input, while the constant one cannot. And that you can use by assigning the red value to the first one, the green value to the second one, and then connect the output, a vector free, to the color. With that, we don't have any more blue values inside of the texture. If I add blue to it, we are back to the original, which we don't want to do. That value we only want to add over time, for which we want to use the time node. Now you might be tempted to simply add it to the Z value, but that would not work. If I run the scene, this is giving us way too much blue. We only want to go up to the original blue value, but we don't want to exceed it. The way you are approaching that, and there are a couple of ways of doing it. The first one would be you could multiply the time with the blue value, like so. This is still going to add too much blue. Let me connect it like so. If I now run the scene, we are pretty much getting the same outcome. There's way too much blue. Let's say for this pixel here, we have an original blue value of 0.4, which we are then multiplying with the time. When we start the scene, the time is 0, so the outcome here is going to be 0. After a while, we get to 1 second, and then we are at 0.4 at the end of the node, which is exactly what we want. The problem is, though, that we don't stay on 1 second. Very quickly, we're going to get greater and greater values. Let's say we can get 5, and then we are multiplying 0.4 with 5, which is giving us a value of 2. As a consequence, we get 100% blue, a lot more than the original. That we can avoid by limiting time to a maximum value of 1, which you could be doing by adding a clamp node with the floating point values, and then you are getting 3 input nodes. The value you want to observe, a minimum and a maximum. We want to observe the time and clamp it to a value of 0 and 1. If I now connect the output, we are back to the original. And if I run the scene, we start without blue and then go to the original colors. This worked. Alternatively, you could also use the min node, which returns the lesser of 2 values. Which means in this case, I want to get the time, and the other value is going to be 1.0, which I then want to connect to multiply and run the entire thing again. We are getting the same result. Because very quickly, time is going to be greater than 1. But inside of this min node, we are picking the smaller of these 2 values. As a consequence, we can never get beyond 1. Now, this would be one way of approaching it. That being said, the current setup you could simplify. Maybe pause the video now and think about which node can be removed. The node that we don't actually need is multiply. Because what we can do is use minimum with the time and the blue value. That way, the time is never going to be greater than the amount of blue. And if I connect this one, we once again end up with the original color. This is going to work, but now the output is going to look slightly different. Because for each pixel, we need a different amount of time to reach that value. It's going to be very hard to see, but actually, what we can do, this time, we can multiply with a very small amount to slow down the animation. So I want to multiply it with, let's say, 0.2. If I now run the whole thing again, we are very slowly getting to the original colors, but the center part is going to take longer because the blue values here are higher. Whereas in the original setup, all the colors will be reached at the same time. Quite a minor difference, but a difference nonetheless. Anyway, with that, we have our second shader. All right, next up, we're going to look at textures. Using those, we can create some funky effects. I have pretty much the same setup that we have seen before. A Node 2D, a Sprite 2D, and a camera. Although what is different now, if you look at textures, we have two PNG files, checkerboard and pentagon. They look like this and like this. You'll see the purpose in a second. First of all though, I want to do the usual. Go to Material, create a new shader material, and then a new shader. Visual shader, canvas item, texture, create. And then we want to work inside of the fragment shader. And now, I want to work with textures inside of this editor. There's already one that we can access, the texture that we have assigned to this texture property. That is available inside of texture. If you create this one, you get a different kind of node, an input node where we have a brown output circle. To actually use that value, we will need another node, and that is called a texture 2D. You can see the colors right there. We need a sampler 2D. A sampler 2D in a texture is simply a fancy way of saying texture data. This we want to import, and now Godot is complaining that right now, for this texture 2D, we are telling Godot that this is a texture, but it's actually a sampler port. We want to sample from an existing texture. We don't want to create a new one. Although that we are going to do in a bit. With that, we can pick pixels from the texture. But by default, Godot doesn't know which pixel to pick. And to figure that one out, it needs a UV coordinate. By default, it is using the inbuilt UV property. You can see there it's default, although you could connect any other value, like so. And once we have that, we are getting the original color, which means if I connect it like so, we once again are reading the input values and connecting them to the output. This setup is doing exactly the same that the color node is doing. Under the hood, this vector for color is doing this operation, which isn't terribly interesting, but I think it's a good way to get started to think about textures. Because besides that, what we can do by removing all of this besides texture 2D, this is by far the most important node. In there, I can assign it a texture. And then, if I click on empty, we can create all of the basic textures that you have available inside of Godot. We could, for example, create a gradient texture 2D. If you click on it and you need to have the inspector open, then you can do all of this. Whatever value you are setting in here, you are getting the result inside of the texture right away. Now, to be fair, what you could also do, if I disconnect this shader really quick, and then with the Sprite 2D options available, if I remove the texture, I can click on empty and then get the same options. The create new texture dialog is the same for this one and for this one here. Although for now, inside of the icon, I want to work with the Godot logo. And by the way, you can drag a texture into this texture slot and you can drag it into this texture slot. For example, you can grab the Pentagon PNG file and drag it in there. Then you get the color that you can connect either to the color or to the alpha value, like so. And you're going to get a pretty neat effect. And I guess now that we have that, we can use it to create something a bit more interesting. Number one, inside of this texture, you can see we have a black center and a white outline. Wherever we have a white pixel, there the actual pixel in the output is going to be visible. If you want to invert that, you can use a node called 1 minus. It does exactly that. It takes a value and subtracts it from a 1. That way, you can invert these values super easily. You can also get a preview. This looks pretty good. That's all we need for the alpha value. Next up, I want to create another texture 2D node, for which we do want to use a texture, but under empty, let me zoom in just a bit and click on this again. I want to create a noise texture 2D that you have to look at in the inspector. In there, you can create a noise. The only option that you have is fast noise light. And if you click on that one, you get noise that you can customize a lot. Depending on what you choose in here, you can get pretty much any kind of random value. And from this texture, you can read all of the values. Although, since this is grayscale, red, green, and blue are going to be identical. The alpha texture for this kind of thing is always going to be 1. But just to demonstrate, I want to connect the red color to the color value. And now we are getting 1 bit from this texture. You could also connect the color right away, makes the entire thing just a bit more readable. That being said, I don't want to have this many gradients, I want to have more distinct values. For that, we need the step function. The color value that we are getting is going to be the x value, and then for the edge, let's say 0.5. If I show a preview, you can see that we are getting random black and white values that we can assign to the color, and this looks pretty alright. But this is not actually what I want. Instead, like you have seen in the intro, I want to have random circles. If you go to Fractal, you can refine this shape a lot. And if you lower the octaves by a lot, then you get this kind of shape, where you have a whole bunch of black dots surrounded by whitish color. If you combine that with the step function, you get this value, where we have a ton of white along with a couple of dots. And if you change the frequency, you can change the size of this thing. Let's go with something like this. And by the way, inside of a random texture, there's a lot that you can do, like the offset or inside of domain warp. If you enable this one, then you can add some random stuff to it. I want to keep it like this. That being said though, once again, I want to invert it, which we have kind of done before by using 1 minus. But that we don't actually have to do, because remember, inside of the step function, we can simply switch these two values around and then we are good to go. So edge is going to be the texture, and then the actual value is going to be 0.5. Alrighty, with that, we have a kind of interesting effect. This I want to customize more. I want to show the original Godot logo where we have a black color and where we have a white color, so where the dots are. For those, I want to create a gradient. Also, I think the dots are a tiny bit too large, which we can change by updating the value inside of x. Let's go with 0.35. Number 1, I want to create a gradient, for which, once again, we will need a texture 2D. I want to create a gradient. Let's go with a gradient 1D, just to have something different. If you click on this one, you can create a gradient with a bunch of colors. Let's say on the left side, I want to have a reddish color, like so. And on the right side, I want to have a yellowish, orangey color. Although choose whatever you like, it doesn't really matter. Inside of the preview, you can see what we are getting. And now, we have to figure out something. I want to get the original Godot logo, where we have a black color inside of the step function, and wherever we have a white color, there I want to get the gradient color. Figuring this one out is going to be your exercise. I want you to only show the gradient where we have the white dots. If we don't have a white dot, I want to have the original Godot logo. As a tip for this one, look at the mix node. Pause the video now and see how far you get. We have 2 colors at the moment. The texture 2D color that we are getting here, and besides that, we want to have the original Godot color, which we can get via vector for color. These 2 values we want to mix, which we can do via a mix node. There are loads of different data types. For this purpose, you could either use a vector 3 or a vector 4. Both would be fine. I'm going to go with a vector 3. If I now connect the original color with the gradient, then we are mixing both of these values at the midpoint, because this vector determines how much we're getting of the first color and of the second color. Let me actually connect it to the output, then you can see what's going on. if I connect it like so, then we are combining these two colors exactly in the midpoint. But if this value is 0, 0, and 0, then we only get the original color, the one that is connected to the A input. If this is 1, 1, and 1, then we only get the B value. And what is super interesting now is that you can combine this with the step function. If I do that, then we get the original logo with a whole bunch of dots. And once again, to understand this kind of logic, let me rearrange things just a bit so you can see what's going on. I want to have this one and this one like so. We are looking at every single pixel individually, meaning for every single pixel, the step function is giving us an output that is either 0 or 1. For all the white pixels in here, we're getting a 1. For all the black ones, we're getting a 0, which we're then turning into a vector 3 to mix these two colors together. If the value is 0, this is going to be a vector 3 with 0, 0, and 0. So we only get the first color, the original Godot logo. If, however, we have a white color, then the value is going to be 1, 1, and 1. So we only get the B color. That way, we can mix these two values together really efficiently, which is a pretty neat effect. And with that, we have also learned about using textures. Most importantly, you can use a texture 2D node with the texture option enabled, this one here. And if you have this one selected, you can create all of these textures. As an output, you are getting a color that you can mix together with other values using the mix node. You can also import other graphics, like we have done down here, and then manipulate them. You're always getting some kind of color output, and that, I think, at this point is quite workable. With that, we are nearly done. There's just one more thing that I want to cover, which you want to be aware of. When we are, at the moment, working with the Godot logo, we have a texture with a dimension of 128 by 128. So this thing is a square. Same for the Pentagon PNG file. This one has the exact same size. And to demonstrate that, I want to disconnect these two nodes like so. And then once again, use the texture 2D function, for which I want to use pentagon.png and connect it to the color value. You get the expected result. We have exactly the texture that we get when we are simply dragging this thing into the viewport. However, if I do the same thing with the checkerboard, which looks like this, quite a large texture, but that is intentional. Also, this thing is not a square. It is a rectangle that is twice as wide as it is tall. What happens now if we assign this checkerboard texture to this texture 2D slot? Well, let's see. Godot is doing something. Number one, it scales down the texture so that the entire thing fits into this little graphic. If you look at the checkerboard, we have 4 rows. Like we have down here, we still have 4 rows. Nothing is being cut off. That being said, Godot did shrink this texture on the x-axis. Effectively, what happens? When you assign a texture to this node, then Godot is scaling it to the size of the texture that you are working with originally. For icon, this would be this texture, with a size of 128 by 128. Or to be even more specific, we are using the UV coordinates of that original texture, which we could manipulate. And for that, let me zoom in just a bit. At the moment, we are using the default UV textures. So on the top left, we have a value of 0 and 0, and the bottom right is 1 and 1. And the texture that we have imported, all of this, is adjusted to that size. But that you can customize. If I get the UV values, we could connect them right away, like so, and that would literally not do anything. But if we multiply it with, very importantly, a vector 2 multiply, I want to connect this one like so, And now we get a pure white because we are multiplying the UV with 0 and 0. As a consequence, we are getting some weird results. But if I change this to a 1 and a 1, then we are back to what we had before. But if I now change the x values to 0.5, then we are only covering the left half of this texture. Changing these UV values can be incredibly powerful. Although for our purposes, we are not going to cover that one yet because it does get a bit more advanced. For now, don't worry too much about it and simply stick to what we have done before with the color and the alpha value, like so. But I guess make sure for now that when you are importing a texture that you want to use inside of a shader, you have at the very least the same aspect ratio as the original texture. Ideally, all of these should be squares. That simplifies your life a lot. By now, we have created a couple of fragment shaders, and we have pretty much covered all of the super important stuff. Which means next up, we can work on vertex shaders. Those focus entirely on the position, which you can use for a couple of super interesting effects. And for all of that, back inside of Godot, I have the usual setup. We have a root node 2D, a sprite, and a camera. Inside of the folder, we have nothing else, and with the sprite selected, I want to go to Material and create a shader material. New shader, visual shader, canvas item, vertex, or whatever name you prefer. And then, by default, we are opening a vertex shader. And this is what I want to use for this part. In there, we have an output node with a couple of properties. The single most important one is vertex. In the most basic sense, this one gives you the pixel position. Although, just to be super clear, that definition is not entirely correct. Which doesn't matter for now, but later on, we have a proper section on vertex shaders, and in there, we're going to refine things a lot. You can also update the UV position and the alpha values. Those two you have already seen. Then you have color and point size. Those really don't matter that much. I'll talk about them when we have the proper section on vertex shaders, but you can mostly ignore them. Other than that, you can add nodes to this thing like you have done for the fragment shader. For the most part, you have the same nodes that do, well, the same thing. However, there are a couple of minor differences. The most frustrating one is inside of a vertex shader, you have a vertex node that reads the current pixel position. If we attach it to the vertex output, we are once again going in a circle. This node we also have inside of the fragment shader. So in there, I can add vertex. And you might be tempted to think that those two nodes return the same bits of information. But they don't. They do similar things, but they are not the same, which can be really infuriating when you're getting started. But once again, I'll talk about it later when we have the proper vertex section. Instead, what I want to do is to change the vertex position. Since this is just a vector 2, we can do things like add a vector to it. Just drag and drop it on it, and then. We are currently getting the pixel position of every single pixel, and we are adding nothing to it. But if I change this to, let's say, a 10, then we are moving the Godot logo to the right. And this I can update. It works in both directions. Other operations also work really well. A super interesting one is multiply, which right now, since we are multiplying the position with 0 and 0, puts all the pixels in the center. So there's one pixel in the center here where we do have the texture, but obviously not ideal. At the very least, for this one, you want to multiply the texture with 1 and 1. That way, you are getting the original. But if I now change this value to 0.5, for example, then we are squashing it on the x-axis. When we are using the vertex property, we are looking at this outline, the red frame for the sprite 2D. In there, we're getting pixel positions, with the origin point being in the center. This would be position 0 and 0. The top left, in this case, since this texture has a size of 128 by 128, would be -64 and -64. And for an example point, let's say we are here, where we have in the original 50 pixels on the x-axis and let's say 20 pixels on the y-axis. This we're then multiplying via this node with 0.5 and 1. The 50 will become a 25 since this one is halved and the 20 stays as it is. As a consequence, this point is being moved closer to the center. And that is what we are seeing here. If the value for the x-axis is smaller than 1, we are squashing the logo together on that axis. That sort of logic you can also combine with other nodes that we have already seen, like the UV position, for example. And by the way, at this point, you might have a question. We have a UV position and a vertex position. These two can seem very similar, and in a way, they kind of are. Both give us a position on this texture. At least for now, the most important difference is that for the UV coordinates, we have this coordinate system where we are starting at the top left with a coordinate of 0 and 0. The bottom right is going to be 1 and 1. So this thing is normalized. Whereas for vertex, we are starting in the center and we are using pixel positions. The bottom right, for example, wouldn't be 1 and 1, it would be 64 and 64. There are quite a few effects that you can achieve with a vertex and with a UV. But not always, and it is important to separate these two. I guess for now, the main thing to separate them is that they are different coordinate systems that fundamentally give you very similar bits of information. For now, what I want to achieve is that we are getting the Godot logo, but it is slanting to the right. So the end result should look vaguely like this. For that, we still want to update the x position. But the higher up we are, the more of the value we want to get. If we're on the top part here, we want to go further to the right. And that we can get via the UV position. Because remember, if we look at the green values, we are going from 0 to 1. Although this we have to turn into a vector 2 first of all. For which I want to vector 2 compose. And we want to get the green value for the x position. The y position can stay at 0. And then for this vector 2 operation, we want to add a value. If I now connect the vector, then we get a slight difference. It's very hard to see, but it definitely is there. To make this effect stronger, I want to multiply this vector 2 with another vector 2. And the output is going to be what we're getting for this add operation. I suppose we could multiply the vector with 50 by 50 pixels. When we are somewhere up here, then the x value is going to be 0. As a consequence, when we are doing this operation, we still have 0, and we're adding nothing to the original vertex position. However, if we are down here, then we are getting a value of 1, which multiplied with 50 is giving us 50. So the bottom part of the graphic is moved 50 pixels to the right. If you wanted to invert the entire thing, you could use 1 minus and connect it here. That way, we are slanting the top right. This you could also animate later on by updating this value. So if I change this like so, by just dragging it around, then we get kind of a cute effect. This, fundamentally, is how you work inside of a vertex shader, where most importantly, you update the vertex position. Besides that, you can also set the UV position. And this we have covered a tiny bit in the last part. Let me first get the current UV position again, so we can work with it a bit more easily. If I connect UV to UV, once again, we are not doing anything. But this value I can manipulate by, for example, multiplying it with another vector 2, like so. This by default should be 1 and 1. That way, we're getting the original. But if I change this, for example, to 0.5 and 0.5, then we are scaling up the entire graphic. I hope the logic for that kind of makes sense. Imagine if this is the original UV coordinate. Because of this operation, we are basically getting the top left corner. If you change both of these values to 2 and 2, then you're only getting a quarter. And by the way, you're getting these stretched out bits because for the sprite 2D under texture, repeat is set to inherit. If we have it enabled, then we are getting the same logo 4 times. You can also mirror the entire thing like so, and you can disable it, although then you get the original bit. These parts you get because Godot, for the border pixel, doesn't know what kind of color to use. As a consequence, it repeats the border pixel. And alright, with that, we do have vector 2 UVs, which aren't too important for now. I mostly want to work on the vertex property. So now we can do an exercise. I want you to rotate the texture around the y-axis. As a tip for that, if you combine time with the sin node, then you get a value that ping-pongs between -1 and 1. Pause the video now and see how far you get. To get started with all of that, let me disconnect the things that we have done before and start basically from scratch. I want to work on the vertical position of all of the pixels, for which, number one, we need the original position, so vertex. And this I want to multiply with another vector 2, like so. We can also get the output right away. Then I want to multiply the original vertex position with 1 and 1. So we are getting the original. That's a good start. If you now want to invert this thing, you want to have a -1 for the y position. That way, this thing is upside down. The pixels with a positive y position have become negative, and the pixels with a negative y position have become positive. And this we can slowly move over time. So if this value ping-pongs between -1 and 1, then we are getting kind of a rotation effect. You do have to be careful though. If the value gets greater than that, we are stretching out the logo, which looks a bit weird. So we have to find a way to get a value between -1 and 1 that keeps on going forever. And for that, we can use the sign value or a floating point, float sin. And by the way, there's an entire section on trigonometry, which the sign function is part of. For now, just accept that if you combine the time with the sign function, you are getting a value, if I show it, that goes from 1 to -1. We're getting a lot of black, but that is because if we go below 0, Godot stays at 0. If I connect this value to the y portion of this vector, for which we will first of all have to create another vector 2. Vector 2 compose. The x value is always going to be a 1, but for the y value, I want to have this one. And now, if I connect it, we are rotating the Godot logo on the y-axis, which is a pretty neat effect. The next important topic is going to be variables. That sounds kind of trivial, but inside of a shader, it does matter. The easiest kind of variable that you have already seen are constants and compose nodes. They store data either with or without input. They don't do anything beyond that. Besides that, something we haven't seen yet is a parameter. These also lets you store data, but this data is exposed in the inspector. Finally, variance. This one lets you move data from the vertex shader to the fragment shader. And only that order is allowed. You cannot go from the fragment shader to the vertex shader. Because inside of the shader pipeline, we first do the vertex part and then the fragment part. So we can only go in one direction. Inside of Godot, I have the usual setup. And to the sprite 2D, I want to add a shader material. New shader, visual shader, canvas item, variables. All of that is fine. And let's work inside of the fragment shader for now. Let's say I want to create a vector 2. If you just type that one, you get a couple of options. We have vector 2 compose, vector2 constant, and vector2 parameter. Compose and constant are pretty similar. Constant lets you create two values, while compose lets you create two values that could accept some kind of float input. Other than that, they are pretty much identical. You could even add values right away inside of the compose node and treat these two as identical. Besides that, there is a vector2 parameter. If I create this one, then we can name this parameter. Let me call it test. Besides that, you might have noticed that we don't really get any value in here. If I connect the vector to the color, we are just getting black. So what's the issue here? Well, once you have a parameter, you have to look at the material, and now you should have shader parameters along with test, the node that we have just created. Keep in mind that this tab is only going to appear if you have the node connected to the output panel. If it's not connected, it will not appear. But if it is, you can give it a value, let's say 1 and 0.5. Then this is the value that we are getting from this vector2 parameter. You can also set a default value for the respective values, and you have a qualifier, which doesn't really matter. This one is a bit more advanced. Don't worry about it. Now we can expose a value to the inspector. And I guess for proper color, we shouldn't use a vector2 parameter. Instead, I want to use a color parameter that we can simply call color. This one I want to connect to the color output. Right now, we are getting black, but if I have a default value, let's say with a purple reddish color, then we are getting this value right away. I think so far this is pretty straightforward. Inside of the shader parameters, if you reset this thing, then you also get the color. And you could still change it to whatever you want. What is really important now is that this value can be updated using GD script. For which, to the root node, I want to add a script. And then func_ready. First of all, we have to target this shader parameter. What you want to do is number one, get the sprite or the node that has the shader. On there, for sprite2d, we have a material. So this thing here. This has a method called setShaderParameter, for which Godot does not give you an autocomplete. I don't know why, but it is part of material, so it does exist. This function wants to have two parameters. Now one, the name of the parameter, so this value. For me, right now, this is color, and then we need a value. For the color, this can simply be color dot, and then whatever color you want to go with. Let's go with a bluish color, dodger blue. And now, if I run the current scene, this node is going to be blue. Once you have a parameter with the data type, you can simply get the material in GD script, call setShaderParameter with the name of the parameter and the value you want to set. That's literally it. What you can also do is use a tween. Although for that, you need a tiny bit more. Number one, we want to create a tween that we can use to animate this color value. I want to have tween along with tween property and then get the icon material. And now we need the property. This is what Godot is predicting when you hover over the parameter. Shader parameter and color. The shader parameter part is really important. Don't forget this one. And after that, you want to have a final value. Let's say in my case, I want to get color and dodger blue again. And a duration. Let's say 3 seconds. I can run the entire thing again. And now we are going from orange to this blue. That's kind of it. It doesn't get that much more complicated. I guess the kinds of parameters that we have is the easiest one would be a float parameter. Then we have the vector parameters for vector 2, 3, and 4. These ones here. And besides that, the color parameter that you have already seen. These are the parameters that you are going to use a lot. So let's practice it. I want you to recreate this animation. It doesn't have to be perfect, but try to get kind of close to it. You will need two parameters and work both in Vertex and the Fragment shaders. Pause the video now and see how far you get. To get started, I want to work on the circle, which we have already done a couple of times. Number one, I need to define a center, which we can do via a vector2 constant, because for both of these values, I want to have 0.5. After that, I want to get the UV values and get the distance to the center point. Distance to D between these 2 points, and then we have a circle, the size of which we can control via this step function. The values of the distance node are going to go into the edge. For the x value, I want to use a float parameter that we can call size. Let me move it like so and connect it. Right now, this doesn't do anything because for a preview, we need a default value enabled, which for now I can set to 0.5. This is going to be the alpha value, and then we have a circle that we can now, inside of the shader parameter, update. So in here, I can now change the size. For the animation, I want to move this value between 0.1 and 0.5, which we are going to do via a tween. Let me comment out this part and then add another tween property. I want to get icon.material, target the shader parameter, but not the color. Instead, I want to have the size. Make sure the S is capitalized. That part does matter. Then I need a target value, 0.1, and the duration is going to be 1 second. If I now run the scene, you can see that we have a basic animation. After this tween is done, I want to return to 0.5, which should also be the default value, like so. With that, the circle gets smaller and then bounces back. To loop this tween, all you have to do is get tween and set loops without an argument. That way it runs forever, so we are getting this. I suppose all of this could have also been achieved by using sin and time, like we have done for the vertex part, but I did want to use tweens, so we can practice the whole system. After we have that, I want to use a vertex shader to move the position of these pixels to go from the center to the right, and then bounce back. For which, number one, we will need the current vertex position. To that, I want to add a value via the add node with the data type being a vector2. I want to add something and then connect it to vertex. The vector that we want to add is going to be a vector2 parameter. Connect it like so and rename it to offset. You could enable a default value, but I think 0 and 0 is pretty good, and those are the default. Once you have that, you get a second shader parameter that you can use to move this thing around. That works pretty well. To update all of this using a tween, I want to copy the two tween properties and change the size to offset. Since this offset is a vector2, this value and this value as well need to be vector2s. The first one is going to be 100 and 0. The second one is simply going to be vector2.0. With that, we do this animation, then this one, then this one, then this one, and then we start again. And there we go. Now we are using a tween to create an animation. And that covers the most important part. Parameters is something you definitely want to understand, which means we can come to the third kind of variable, a varying. And while we are doing that, I want to comment out all of this animation stuff so we can look at the Godot logo without any interference. Quite often, you want to pass data from a vertex shader to the Fragment shader. Let's say we want to get the vertex data and turn that into a color. Now, a vertex node does have a color property, but this one is doing different things. For example, if I add a vector-free constant that is red and connect it, we are just tinting the graphic. We don't get a pure red color. Instead, I want to get this vertex data into the Fragment shader. For that, we will need a varying. And actually, if you look at the top of the shader editor, there we have manage varyings. And to use a varying, we first have to create one. Add varying, and then we need a name. Let's call this one vertex. It is going to be a vector2, and then you have the options in which way this varying can go. There are only two. We can go from vertex to fragment or from fragment to light. That's literally it. Since the vertex stuff is calculated much earlier than the fragment, we couldn't go from fragment to vertex. It just doesn't work like that. Now, in our case, we do want to go from vertex to fragment. Then click on create, and now you have to add a varying setter, in which you can select the vertex varying that we have just created and then connect the vertex value to it. That's all we have to do in here. After that, inside of fragment, I want to add a new node, and inside of a fragment shader, I have a varying getter and a varying setter. Varying getter does not exist inside of a vertex node because there's no value to get. Whereas in a fragment shader, we can get and set values. But for now, we want to get the vertex value. And if I assign this to the color, we are getting something. Once again, don't worry too much about these values. We'll talk about that later. At the moment, I just wanted to have some basic data to work with. But, well, that's basically it. Now we can move data from a vertex shader to a fragment shader, which also covers all the different kinds of variables. We have a constant or a compose node, we have a parameter, and we have a varying getter and setter. In this part, we are going to start looking at code-based shaders. We are not going to learn anything particularly new. We are just going to express the logic in code. And that's all we are going to do. Although while doing that, I am also going to talk about the difference between code-based and visual shaders. As an example, here is a shader that we are going to create in a little bit. The end result is going to be a shield that can have a highlighty kind of shape. This would still be a basic shader, but it does get more advanced. If you used code, the entire thing would look like this. It does literally the same thing. Now, which one you prefer is kind of subjective. Some people like code-based shaders, other people like visual shaders. You can write the exact same shaders in both systems. They are equally powerful. However, in my personal opinion, I think visual shaders are really nice to get started, and they help you a lot by giving you a preview of the value. But they also become difficult to manage after some time. The more stuff you add, the less readable it will become. And code-based shaders suffer a lot less from this problem. So for example, this shader does look really complex, but fundamentally, we are talking about maybe 10 lines of code. And these lines even include a whole bunch of very basic math. Once you understand the code, I think this becomes much more readable and maintainable. You might disagree, and you can keep on using visual shaders, although I am going to use code-based shaders from this point forward. What is, however, really important to note is that all examples online use code-based shaders. The largest database of Godot shaders online is called Godot shaders. In there, you have a whole bunch of shaders, and all of these, literally every single one, is giving you code-based shaders. You sadly don't get an image with the visual shader. So if you want to use this resource, you have to at least understand code-based shaders. If you don't, you, well, lose out on a lot. Not to mention, if you're asking ChatGPT or any kind of AI chatbot, they will write you code-based shaders. That being said, Godot's biggest competitor, Unity, is relying heavily on visual shaders. And being able to take ideas from them is going to be really useful. As a consequence, ideally, you understand both visual and code-based shaders. It's going to give you a lot more resources. So let's talk about code-based shaders. Most importantly, shaders are not written in GD script. Instead, we use a shading language that is based on GLSL 3.0, which is a C-like language, like C, C#, and C++. This is going to introduce quite a few differences compared to GD script, but it's not that bad. People tend to overstate the difficulty here quite a bit. If you can write GD script, you can figure out the shading language. It's really not that bad. Inside of the shading language, the most annoying part is that you always need a semicolon after every single line. Then data types are very strict. When you're creating a variable, you have to set a data type. And you have to be explicit about combining data types. Even basic things, like adding an integer to a float, is not allowed. Finally, indentations do not matter. Code is grouped with curly brackets. You can see that in the example that I have used earlier. We have a function that doesn't return anything and is called Fragment. This one is called automatically. There are no parameters, and we use curly brackets to define what is inside of the function. Now, there are indentations, but you could remove them. They are just there for readability. Other than that, we are creating variables by defining the data type, then giving it a name, and then assigning a value, in which we are doing the usual stuff, so basic math, and finally, we always need a semicolon. Other than that, this code is executed line by line, but remember, all of this is done on a pixel by pixel basis, and all the pixels are covered in parallel. That part does not change. With all of that out of the way, let's create our first code-based shader. I have the usual setup, and I want to add a shader to the sprite 2D. Inside of material, I want to add a shader material, new shader, and now, really important, we want to have a basic shader, not a visual shader. The other stuff can stay the same. I guess the one thing to note inside of the path is now we have code.gd shader. The data type here has changed, but that doesn't really matter for our purposes. Click on create, and now we get a code editor, in which, number one, we have the shader type. Canvas item, as a reminder, tells Godot that we want to create a 2D shader. Then we have a vertex function and a fragment function. These are being called automatically. You could also create your own functions in a very similar way. Besides that, you have a light function that we are going to ignore for now. And now, to get started inside of the fragment function, the single most important property in here is all in uppercase letters color. This is a vector 4 that sets red, green, blue, and alpha. Let's actually give it a value. I want to create a vector 4, for which we need a couple of arguments. And Godot is quite flexible in terms of how you can create a vector. For example, if you add a 1 in here, then we have a vector that effectively has 1 for every single part. So red, green, blue, and alpha are all 1. As a consequence, we're getting a white color without any transparency. To create a red color, we would want 1, 0, 0, and 1 for the alpha value. Cool, that part works. Effectively, this color property replaces color and alpha from the visual shader. Inside of Vertex, we have the Vertex property. To that, for example, we could add with plus equal a vector 2 with 20 and 10 pixels. Don't forget the semicolon. Then we are moving the Godot logo to the right and down. Besides that, a couple of minor things. If you want to create a variable, you always start with the data type. So if I want to create a vector2 variable, I would have to type vector2 and then a name of the variable. Let's call it test. Then you can assign a value, which could, for example, be a vector2 with some kind of data. Alternatively, it could also be the UV coordinates, which we are storing inside of, in uppercase letters, UV. And this we can use inside of the vector4 to, for example, add the test. Then we get the two values from this vector 2, 0 for blue and 1 for the transparency. What you can also do is get color and then specific parts of this vector 4, which you can even combine. What you see a lot is that you only want to update the color, but not the alpha value. For that, you can get color, RGB, or X, Y, Z. If you now assign a vector 3 to it, with let's say 1, 0, and 0, and we comment out this part, then we have a red color that is ignoring the rounded corners. And this system is flexible. So instead of X, Y, Z, this could be Y, X, Z. Although don't actually do that kind of thing, this would be really confusing, but you can do it. Ideally, if you only want to change the color, add RGB. That is much more readable. Once again, RGB is the same as X, Y, and Z. I think all of this for now is reasonably straightforward, but there are parts that do get different. The most annoying part, let's say I want to create a float called test alpha, and this value should be the sum of 0.5 and 1. This in GDScript would be a very basic operation, but inside of a shader, this is not allowed. Godot is complaining that we are trying to add a float to an integer. Or in other words, you can't combine different data types. To fix that, what you basically always see is that people add a dot to the integer, and that way you're getting a float. You could write 1.0, but the end result would be the same, so people just drop it usually. To emphasize that we are using floats inside of vector 3s or vector 4s, people tend to write 1 point instead of a 1. That way, we are definitely getting a floating point value. The only exception is 0. For this one, you don't need that kind of system. Besides that, to cover the variables, at the moment, we are creating a float, and this we could change. Let me comment out all of this stuff by adding 2 slashes, which by the way is also different. And then we can get color.a and assign it test alpha. Since the alpha value can only be 1 at the maximum, this value doesn't really make sense. But what we can do is test alpha minus equal 0.8, let's say, and then we are getting transparency. Now, if you want this value to stay the same, you can turn it into a constant. That way, Godot is going to complain about this line because we cannot modify constants. That being said, in practice, you don't see constants that often. They are usually not necessary. But what you do see a lot is uniform. This inside of a visual shader would be a parameter. I don't know why the name is different, but if you want to expose inside of a code-based shader a variable to the inspector, you need uniform. For example, uniform float exposed variable. If you have that and look at the inspector, we get shader parameters along with the exposed variable. And there you can assign it a float, whatever you like. And if you want to assign a range, you need colons and then int range. Adding colons and some kind of hint is a really common thing. For a float, this one would set the start value, the end value, and the step size. So now I can only go from 0 to 1 in increments of 0.1. Which, by the way, you don't actually need. You could simply set a start and end value, then you have a lot more freedom in here. Another value that you could export is uniform vector 3 color, which at the moment, like this, is only going to give you a vector 3 with x, y, and z. However, if you add colon source color, then you're telling Godot that this vector 3 should be a color, which means in the inspector, you get the color picker, although without an alpha value, which you could add by turning this into a vector 4. If I now save it, this one looks the same, but if I click on it, we have an alpha value at the bottom. And this we could assign to the color property, so color is going to be color. And now, whatever value I set in here is going to be the color and the alpha value. That is pretty much it. If you understand the system so far, you understand code-based shaders, at least the basics of them. I guess we should do an example. Let me get rid of the stuff inside of the Vertex shader. In fact, let's remove the Vertex shader entirely, which you can do, and then recreate the circle, for which I guess I want to delete all of this, and then I want to have a float circle, which is going to be the distance between the UV position and a vector 2 with 0.5 and 0.5, the center of the UV coordinate system. Although Godot allows you to create a vector 2 with one value. This value would then be assigned to x and y, and in our case, since they're the same, we can write it like this. The result would be a vector 2 with 0.5 and 0.5. This circle we want to assign to color.a. So in here, we want to have the circle, and then we get a, I hope, kind of familiar result. If a pixel is close to the center, it is going to be invisible. The further away we go, the more visible it becomes. To control that part, I want to use the step function, and you could create a separate variable or do it when we assign the circle to the alpha value. I'm going to do it in here. So I want to use the step function, for which we need the limit and the current value. Let's go with 0.5 and the circle. That way, if a value inside of the circle is below 0.5, it's going to be 0, so we have a big hole cut out. But if the circle distance is greater than this value, then we get the full alpha amount. These parts are visible. Now you can invert that in two ways. Either, like we have done before, you simply flip these two values around with circle and 0.5. That way, you get the proper circle. Alternatively, what you can also do is 1.0 minus the result of step. You would get the same thing. Choose whatever you prefer. I am going to keep this one. I guess, finally, this exposed variable could be the circle size, which we want to use instead of 0.5, so size in here. Then via the inspector, we can control the size of the circle, although the range should go from 0 to 0.5. That way, we are maxing out here. Just feels a bit better. And I suppose, finally, we should use the color, but this color should not set the alpha value. It should be a vector 3, which we can then use to update color.rgb and set the color uniform. That way, we can set the circle size and the color. With that, we have a basic shader that is actually kind of useful. To finish this part, I want you to create a diagonal reveal effect from the top left to the bottom right. And this should happen using a code-based shader. Pause the video now and figure this one out. I don't want to touch this shader too much, so instead, I am going to add another Godot logo in the same position. I am always using the position 100 by 100. And then to this thing, I want to add a new shader material. All the defaults here are fine, but this should be code_exercise. Create. And now, we only want to work inside of the fragment shader, so all the other stuff can be deleted. Most importantly, we want to figure out where we are on the diagonal axis. We start up here and go to the bottom right, down here. This should then be used for the alpha value. That value you can get by adding UVX and Y, which I want to store inside of a float called diagonal, for which I simply want to have uv.x plus uv.y. And the result, I want to assign to color.a. So diagonal in here, and let's see what we get. Let me hide the icon that we had before, so this doesn't get confusing. Remember, for uv.y and uv.x, our range is always 0 to 1. If we are in the top left, so both are 0, then diagonal is going to be 0. However, if we are, let's say, down here, where x is 0.1 and y is 0.3. If we add those two together, we would get 0.4. And the same result we would get if we are here, with the two values inverted. 0.3 for x and 0.1 for y is still going to give us 0.4. As a consequence, these two values are on a diagonal. If I go a bit further down, let's say here-ish, where we have 0.4 for x and 0.6 for y. The value for this one would be a 1. And this is going to be the same for the center, where we have 0.5 and 0.5, and further up here, where we have 0.6 for x and 0.4 for y. Once again, we have a diagonal. That's how the math here is working. But the problem is, and you can see it in the preview on the right, once we reach the midpoint, we are getting a value of 1. So after that, we always have full transparency. That we can fix by simply dividing the value we are getting here by 2. Then Godot is going to complain because now we are dividing a float by an integer. This should be 2 point, meaning we're getting a float. And now, in the top left, the value is 0. In the bottom right, it will be 1, which we can turn into distinct values using the step function. Let's say for now with 0.5. And there we go. This looks pretty good. And I guess we should also add a uniform load. Let's call this one progress with a hint range where we go from 0 to 1. This value I want to use down here. And now I can reveal the logo like so. Although there's one issue. The corners are sharp now, which I don't want. I want to retain the original alpha values. Now, an easy solution for that would be to multiply the current value with what we're getting here. That way we can keep the corners and we have finished the exercise. Now, this is working pretty well. That being said, I forgot to cover a really important part, and that is textures. Number 1, to create a texture, you want to have a uniform sampler 2D with a name. Let's call it test texture. Don't forget the semicolon. And once you have that, you have the test texture, where you can do the usual stuff. Let's create a gradient texture 2D with some kind of thing in here. To read a value from this texture, you will need the texture function with the sampler, which is the test texture, and then the vector2 coordinates, which usually are the UV values. The return value for this is going to be a vector4. Let's store it in a variable vector4 test. It's going to be the texture, and don't forget the semicolon. Now we are getting the gradient, and we could assign it color.rgb by using test.rgb or xyz. Both would work. And this works. Perfect. This texture is the equivalent of the texture 2D node. So you need a sampler and a UV coordinate, and then you get the value that you want, and you can use it however you like. If, however, you want the texture that is assigned to the node itself, so this one up here, you would need all in uppercase letters, texture. And then you are getting the original values. That being said, this you don't really have to do, because via the color property, you can get the current value quite easily. Like we have done, for example, here, where we are getting the current alpha value and then multiplying it with all of this. Because of that, we keep the rounded corners. Although technically, what you could be doing is get the step function and then multiply it with texture and alpha. The end result would be the same. So we can still do all of this, and we keep the rounded corners. Just keep in mind, this is a lot more logic than you actually need. To finish up the introductory part, I want to refine our shader definition quite a bit. There are three changes that we have to make. And the first one we have already encountered, but step by step. So far, our shader definition was in parallel. A shader updates the position, color, and alpha values of every pixel. This served us reasonably well. But the one change that we already have to make is that we have to separate the position and the color values. We are first doing the vertex shader and then the fragment shader, which, if you want to use a varying, is really important. That's the first refinement of the definition. The next one is going to be about the fragments, for which I want to work inside of Godot, and we have the usual setup where I want to add a shader material along with a new shader. All the defaults here are totally fine, and then create. We want to work only inside of the fragment shader, at least for now, and then talk about what we actually work with. And to get started with that, I want to create a circle by update color.a with step 0.5 and then the distance between vector 2, 0.5, so the center, and the UV position. That is going to give us the center cutout, which I want to reverse like so. That way, we are getting a circle. And this we have done a couple of times by now. It works pretty well. But it only works well because the texture that we have is a square. That is 128 by 128 pixels. What happens to all of this if we don't have a square? Or in other words, if I stretch out this logo like so, let's say we can give it an X scale of 2. That way, it's twice as wide as it is tall. And that ruins the circle pretty badly. And I think it's quite obvious why. This UV coordinate system goes on the y-axis from 0 to 1. The same thing we are doing on the x-axis. We are still going to a value of 1 here. As a consequence, the actual distance that we are traveling is twice as wide. Effectively now, when we are working with the fragments, a pixel, since we're working with the UV position, would be stretched out on the x-axis, which is very, very bad. Most importantly, because it's literally impossible. Pixels are always squares. They are a physical object in your screen. The only way to get a non-square pixel is if you go to a factory and create a super weird monitor. A fragment shader does not actually update the pixels, at least not directly. Instead, what is happening is that the fragment shader updates what is called a fragment, which in turn is a potential pixel. If we create a fragment that looks like this, Godot has to figure out how to turn this fragment into a pixel. In this case, it would probably simply split it into 2 parts. The actual math is much more complicated, but that's the basic logic. We have a fragment, and those can have basically any shape. But then, when we are turning them into actual pixels, they have to become squares. If we have a perfect square for the texture, then every single fragment could simply be converted to a pixel. And you might be wondering how to fix this kind of thing. We would need to adjust for the aspect ratio. We are going to work on that in the next part. For now, don't worry about it. I just want to talk about the problem. The solution is going to come later. The really important thing for now is that we have to update our definition of a shader. Fortunately, we only have to change pixel to fragment. So the fragment shader doesn't update the pixels, it updates the fragments, which in most cases is not a meaningful distinction. A lot of tutorials treat fragments and pixels as identical, which honestly is fine in most cases. You just don't have to worry about it too much unless you encounter an edge case where it really, really matters. That would be the first issue. Next up, we don't need the fragment anymore. Instead, I want to have the vertex shader. So far, the definition for this one is that we are updating the position of every single pixel. And let's actually do an example. I want to update the vertex position by adding a vector 2 with, let's say, 50 and 0 pixels multiplied with uv.y. That way, we are moving this thing to the right. And while we are doing that, I want to reset the scaling so this looks a bit better. So with this shader, in our current understanding, we are taking the current pixel position and then check the distance from the top via the UV. This we are then adding to the right to add an offset, meaning the further down we go, the further to the right we go. The result is a slant in the texture, which we can also visualize using the Fragment function, in which we can update the color RGB value by creating a vector 3 with uv.y. Don't forget the semicolon. And now you can see that the further down we go, the greater the value becomes. So via the distance, we are moving further and further right. However, what if I turn this UV value into distinct values using the step function? I want to have a float. Let's call it the Y position, for which I want to use the step function with 0.5 and uv.y. After that, I can pass in the Y position like so. That turns the gradient into two distinct values. They are either 0 at the top or 1 at the bottom. And now we come to the interesting part. If I copy this value and use it instead of uv.y, the expectation would be that we keep the original top part and move the bottom part 50 pixels to the right, something like this. However, if we actually do it, then this is not happening. We actually did not change anything. So what's the issue here? Like for the fragment shader, we do not work with the individual pixels. Instead, we are working with the vertices, which for Sprite2D are these 4 corner points. If one of these is at the bottom, so we have this white value, then the vertices are moved to the right. But if we are up here, there's no movement. After we have done that, Godot is calculating a new shape, which would be this one. And only on there does it do all of the fragment stuff. Because of that, since we only have 4 points that we can move, we can't really create any kind of complex shape. That being said, what we can do is add another node, which is a polygon 2D. For this, you can create a couple of points and assign it a texture. I want to assign it the Godot logo. And then in the polygon editor, you have to create a shape around it, which you want to have very close around the shape. Otherwise, it's going to look pretty ugly. I want to create a point here, here, and then loads of points on the vertical axis. That way we have more to work with. Once again, for the bottom part, I don't care about the horizontal points. And then I want to add loads more points here. With that system, we are getting a lot more vertices to work with. Every single one of these points is a vertex inside of the shader. So now, if I assign it a shader material with the definition shader that we have already used, drag and drop it in there. Now for this one, we get a much better result, which we could even animate. I want to add a uniform float row grass with a hint range of 0 to 1, and then use it for the 0.5 in both step functions, like so. Right now, since this value is 0, we get a pure white color. But if I update it, then you can see once we hit a vertex, we are updating the shape. And I think with that, you can see it much better. We only update the vertices, we don't update the pixels. For the actual pixels, we are setting a shape via the vertices, and Godot fills in the rest. Which is bringing us to the final shader redefinition. This is our current one, and we have to change it to this one. In parallel, a shader updates first the position of the vertices and then the color and alpha values of every fragment. this is a much more accurate definition of a shader. And that also finishes the introduction to shaders. At this point, I would recommend to just play around with shaders and see what you can create. Also, something that I haven't mentioned yet. On the Godot documentation page, you have an entire chapter on shaders. The most important part in there is the shading reference. There you can get information on every single shader. You mostly, for now, want to look at built-in functions and canvas item shaders. If you look at those, Godot is giving you all of the properties, like for example, UV or color, and you can see there are loads more. We will talk about almost all of them. If you scroll down a bit further, you can see a whole bunch of examples that could be useful. Besides that, if you look at built-in functions, you get all of the functions that you could use. There are quite a lot. Sadly, for visual shaders, you don't have this kind of detail. You basically have to look at the code-based version and then convert it for your purposes. Not terrible, but also not ideal. With that, we have covered all of the basics. These we are going to use to create a whole bunch of proper shaders. That's going to be the second part. It is time for our first proper shader, for which I want to create a crosshair. It can also be animated, and it will teach you about how to think about shaders. Additionally, I will also cover how to use functions, this part. But first of all, here we are back in Godot, and we have the usual setup. A node 2D at the root, then a sprite 2D, and a camera 2D. All within a new folder, part 2, shader projects. And in there, we are making a crosshair, in which, with the sprite 2D selected, I want to go to material, and then create a new shader material. I want to create a new shader, canvas item, crosshair, totally fine, and create. After that, and let me rearrange things just a tiny bit. We do not need the vertex shader, nor do we need the light function. All we need is the fragment function, and in there, to get started, I want to change color RGB to a pure white color. So vector 3, 1. We don't care about the Godot texture. After we have that, there are 3 parts that we need. Number 1 is the center circle. Number 2 are the crosshair bits, so these vertical and horizontal lines. Finally, I want to have an outer ring, something like this. Let's start with the circle. This part we have already covered quite a few times. I want to create a float circle, for which we want to measure the distance from the current pixel position, so the UV value, to the center point, which is going to be a vector 2 with 0.5 for x and y, which we can then use for the alpha value. Color A is going to be the circle value. The further away a pixel is from this center position, the more of an alpha value we have. And this we want to invert and turn into distinct values. Once again, this we have done before. We need this step function where we need a value and an edge. That's a 0.5 for now. That's pretty much it. Now we have a circle. And this we want to be able to customize, for which I want to have a uniform float center underscore size, which is going to get a hint range of 0 to 1 with a default value of 0.5. This value I then want to use for the step function, like so. And then, inside of shader parameters, I can customize the center size. I think the logic so far is pretty straightforward. We have done this operation a couple of times by now. So let's start adding something new to it. Number 1, when you work with shader parameters, at the moment we have the center size, this range here should ideally go from 0 to 1. You don't have to do that, but it is good practice. It makes the entire thing much more predictable and, well, much easier to understand, especially if you work with other people. In our case, the maximum size should be 0.5. If you make it any larger, then the circle is going to get way too big. In fact, we should probably max it out around, let's say, here, 0.1. This value should be the maximum value. Or in other words, it should be a 1. which we can achieve quite easily by dividing center size by 10 or multiplying it with 0.1, whatever you prefer. If we do that, right now the circle is not visible, but if I change this value to a 1, we have the smaller circle. And if it is 0, it is not visible. With that, we are getting a circle that is much more limited in its size. And whenever people working with it, they know that the maximum value is 1 and 0 is the minimum value. Granted, this is a small part, but it's really, really good practice. And when you have more complex shaders, having these parameters normalized to value of 0 to 1 makes your life a lot easier most of the time. This will be the first part, and I want to have a default value of, let's say, this one. Next up, I want to create a circle around this point, vaguely like this. For that, we will need a large circle, and then a smaller circle, and then subtract the smaller from the larger one. While we're doing that, I want to comment out the center circle so we can focus on one thing. I want to have a float outer circle, for which, once again, we will need a basic circle. So step, I want to get the distance of the current UV position to the center point, which in our case is going to be vector 2 of 0.5, like so. Then we will need a value. Let's go with 0.5 as well. Just to demonstrate, I want to get color A and set it to the outer circle. This should be giving us a large circle, and there we go. This looks good. Next up, I want to have a float inner underscore circle, which is pretty much going to do what we have done up here. I can literally copy it. The only change that we have to make is that this value should be smaller. Let's say 0.3. And now, if I only use the inner circle for the alpha value, we get a smaller circle. And the really interesting part happens when you get the outer circle minus the inner circle. We get a ring. And I hope the logic for all of this isn't too confusing. We are getting, number one, a large circle. That's this entire area here. We are getting an inner circle that is this part. All of those are just floating point values. Every individual pixel, let's say this pixel here, is either seeing a 1 or a 0. And then we are subtracting 1 from the other. For example, once again, for this pixel, the outer circle is 1 and the inner circle is 0. As a consequence, the alpha value is going to be 1. However, if we are here, then the outer circle is still 1. Basically, this value is pretty much always 1 besides these corner points. But then for the green point, the inner circle is also going to be a 1. As a consequence, we do 1 minus 1. The end result is 0. So this pixel is not visible. Once again, all of this looks really complicated, but we are doing really, really simple math. This, however, I want to customize a bit more, for which I want to add a uniform float. Let's call it circle width. We want to have a hint range and go from 0 to 1 with a default value of 0.5. Besides that, I want to have another uniform float that I have called circle distance. With the same hint range, we want to go from 0 to 1 with a default value of 0.5. To use these values, when we are creating the outer circle, I want to get UV. The center is still going to be 0.5. We are always using that one. And then I want to get the circle distance, which has a default value of 0.5, which is what we had before. So no change. However, if I now change the circle distance, we can scale this thing out a little bit and even make it invisible. The same thing I want to do for the inner circle. Although in here, I want to get the circle distance minus the circle width. That way, those two work together. At least kind of. If I make it large enough, then you do get a center. The problem is at the moment, the circle width is way too large. This needs to be smaller, something like this. And now, we can customize the circle distance like so, we always get a ring, for which we can also change the width, and this works pretty well. We are doing the same math formula. The only difference now is that the values we are using are defined inside of these uniforms, where the large circle gets the circle distance, and the smaller one is the circle distance, basically minus the line width. After we have both of those, we just have to subtract the larger from the smaller value, and we are good to go. Now, to organize all of this a little bit better, I want to create a function, which is going to look very similar compared to the void fragment function. Number one, we need a return value, which in our case is always going to be a float. Then we need the name of the function. Let's call this one create circles. Then you need parentheses for the parameters and curly brackets for the actual code inside of the function. Really important. Inside of a shader, when you create a function, you always need a return statement that returns a value that you have specified at the beginning. Which means for Godot to be happy, we have to at the very least return, let's say 1.0, some kind of float. Then Godot's happy, we have a function that we could simply call all the way at the bottom. I want to set color A to create circles. Don't forget the semicolons. And now we have a function that always returns a 1. That's a good start, but not what we actually want to do. Instead, we want to do all of this. Let me copy the first 4 lines and paste them in here. I want to get the inner circle and the ring around it. The end result should then be returned. But before we can do that, we have an issue. That we have an unknown identifier and expression UV. This UV inside of this function does not exist. The reason for that is that the fragment and the vertex functions are special. They have access to all of these inbuilt properties, like color, UV, vertex, all of that stuff is only available inside of these functions. Inside of custom-made functions, it is not. To get access to it, we have to pass it in via parameters, which, by the way, you create by first specifying the data type and then the name. Let's call it in lowercase UV, which we then want to use for all of the UV values. UV, and then we are getting another error message that color A is also only available inside of the fragment function. We couldn't use it inside of a custom-made one. That's okay, we simply want to return the final value. Let me comment out this line, and to get a proper circle, I want to get step with the distance. Then we need the float, which is what we have done before, center size times 0.1. We basically put in the stuff we have done so far, all of this, into this one here. That way we have the circle inside of a single line. And now, for all of this to work, when we are calling create circles, we have to pass in the UV coordinates. Then Godot stops complaining, and we have to figure out the right return value. We want to get the inner circle, and then the outer circle minus the inner circle. So let's just do that. I want to get circle plus, in parentheses, the outer circle minus the inner circle. And now we are getting both. And once again, I know I am repeating myself, but to really understand these math bits here, you have to think about it from the perspective of every single pixel. For all of these pixels, we are looking at the distance from the center, this bit here, and then we are comparing an outer circle and an inner circle. And all of this we're then adding together. So for every pixel, these values are either going to be 0 or 1. And this we are then combining with very basic math to get the proper alpha values. That's all that's happening here. And to practice all of this, let's do an exercise. I want you to add a cross cutout to this shape. We are still working inside of create circles. The end result should look something like this. To achieve that kind of effect, you have to work more with the UV positions and their distances to the center position. Pause the video now and see how far you get. Back in Godot, inside of create circles, I want to create a float cross cut out, for which I want to get the distance of uv.x and the center position, so 0.5. Two important things. Number one, since we are working inside of create circles, we have to work with lowercase uv for the position. That we're getting from the parameters, although all that this is the uv coordinates. Number two, at the moment, we are only working on the vertical axis. Effectively, what we are going to do is to cut out an area like this. All we need for that is to measure the distance from the center and then go to the left or to the right by a certain amount. If we are within that range, we want to subtract the value, which means this cross cutout should become a rectangle, like so, which we then want to subtract from the outer ring. Although I guess for now, what I simply want to do is to return the cross cutout and comment out this part so you can tell what's going on. Right now, we're getting this. If a pixel is close to the center position, we have a very low alpha value. That part, I think, makes sense. This, once again, we have to invert and turn into distinct values, which we have done before loads of times. We will need the step function and then some kind of value, let's say 0.1. And there we go. We have a rectangle. And I guess while we're here, we can turn this into a proper cross right away. For which, we simply have to add the same value, except now we want uv.y, and then we have a cross. Think about every single pixel. For example, this one. For this pixel, we are number one, looking at the distance from effectively this center line. If that is within a range of 0.1, then we are getting a 1. To that, we will add another value, all of this. We are effectively checking for this line if a pixel is within this range. If either of those is the case, so if a pixel is in here or in here, then we're getting a value of 1. Although technically, what you do want to be careful about, if we are in the center, this bit here, then we would get a 2 because we have both the vertical and the horizontal axis. You can't see that because these values max out at a 1, but it is there, so do be careful about it. What is generally good practice? When you have this kind of case, you want to make sure that you always stay within a range of 0 to 1, which you can achieve by using the min function. We want to get all of this or a 1.0. In practice, this is not going to change anything, but now all these values are either 1 or 0. We don't get anything else. With that covered, this shape shouldn't be visible. It should be subtracted from the return circle. Let's make it visible again and get rid of this part. We want to basically remove all the pixels inside of cross cutout, which does work, but we do want to keep the center circle, which we should achieve by putting this operation inside of the parentheses, like so, and then we still can't see it. What's the problem here? Once again, ideally for a shader, we want to work within a range of 0 to 1. But inside of these parentheses, we don't do that consistently. When we have the cross cutout, vaguely this shape here, the operation we are doing inside of the parentheses is fundamentally, since we are getting 0 from the outer minus the inner circle, we are doing 0 minus 1. As a result, for all of these fragments, we are getting minus 1. If we then add the circle, which is a value of 1, we are getting an end result of 0. As a consequence, this circle bit will not be visible. That we can now fix by using the max function. We want to get all of that, but we always want to be above 0. And that way, we are getting the center point back, because now this entire operation can never go below 0. Cool. With that, we have the main circle. And I hope looking at this function is not too overwhelming. You basically want to look at every single pixel and then redo the math using the UV positions. If you do that for a little bit, the math should become clear. The most important thing that you have to understand is that I guess we have to use the step functions to turn a gradient distance into distinct values. Besides that, we are using min and max to make sure that we are always within a range of 0 to 1. And other than that, we are returning the alpha values that we are then using down here. Besides that, we don't need anything else. That covers the circles. Next up, I want to have a float create lines, for which, once again, I need the position, so vector to uv. And for now, I want to return a value of 1.0. With this create lines function, I want to add all of those lines. And if you want to challenge yourself, this could be a fun exercise. I want you to add the lines, which should also be dynamic. You should be able to change the position and the size of these lines. The end result should be something like this. Pause the video now and see how far you get. The way I approached it, number one, I created a vector to center distance, which is simply going to be the center, so vector to with 0.5. And to that, I want to add, let's call it the crosshair underscore distance. This value doesn't exist at the moment, so we have to create another uniform float crosshair distance with a hint range of the usual stuff. All right, with that, let's think about what this value means. Vector 0.5 is pretty simple. That one is simply the center. If we then add the crosshair, let's say at the moment this is 0.5, the operation we are doing is going to be a vector with 0.5 and 0.5, to which we are adding 0.5 once again. The result will be a vector with 1 and 1, which would bring us down here. Maybe a bit far, let's change this value to 0.25. That way, we are down here, which might at the moment seem entirely pointless, but let me actually use it. For which, I want to create an h width. This is going to be the width of the horizontal line. I want to get the distance of uv.x to this center distance.x. This value I want to return, h width, and then we can use it for the color A value. Create not circles, but create lines. That gives us a different result, but this is still not exactly useful. Next up, I want to turn this area into a proper rectangle. Once again, I want to turn a gradient into distinct values and inverse it. So I need step and then let's say 0.2. Now we're getting a bit closer. Once we cut away the top and bottom part and only have this bit left, this will look a lot better. But before we can get to that, we have to get the left side, all of this. We simply have to do the same operation again. Let me copy all of it and then plus this. But now we want to do 1 minus uvx. That way we're getting a mirror image. And to customize the width, I want to add another uniform node. Let's call this one the crosshair length. As always, I want to have a hint range from 0 to 1 with a default value of 0.5. This value I want to use here and here. Although this is giving us way too large values. To account for that, I want to multiply both with 0.25. Much better. And just to make it more readable, let me add all of this over multiple lines. Since we are using semicolons, we can be much more flexible in our setup. You don't have to do that, but in my case, I don't have that much space, and I want to keep everything readable. Next up, we need load h underscore height. This one is going to be much simpler. I want to have step, then the distance from the uv.y position to the center point, 0.5. Then to make the step function happy, we need some kind of value, let's say 0.05. We're going to customize that in just a second. I want to multiply it with the h width. So h width multiplied with h height, and we have the horizontal crosshairs. Once again, go through the math and insert random points for the UV positions. Then you understand what's going on here. To make this value more dynamic, I want to have a uniform float crosshair width with the usual stuff, hint range from 0 to 1. The default should be 0.5. And this I want to insert into the step function. And then I want to multiply it with 0.02. Just to double check, I can customize the crosshair width and the crosshair length. This looks really good. Also, the crosshair distance should be working. That looks really good. And that is now because we have assigned this center distance, which originally gave us a rectangle here. But now I hope you understand how this math comes together. We basically cut out a part at the top and the bottom, and we got a mirror image of it. That way, by simply defining this point that is basically down here, we can get only the horizontal position, which is up here, and then do all the other math around it. Next up, we want to do all of this for the vertical part, which means I want to have a float v height, for which we basically want to copy all the stuff that we have done here, except that this should be uv.y, center distance.y, same down here. The end result, I want to add to the return value the height. Then we're getting a super wide line that we have to adjust with float the width. And just to make sure you're not confused, for these two values, we have to inverse h width and h height. The width of the horizontal axis will become the height of the vertical one, which means we can copy this line once again. The only change that we have to make is that this should be uv.x with the center position, and the entire thing we want to multiply with the return value. So multiply with v width. And if I spell this correctly, then this is going to look much more professional. And there we go. Now we have the crosshair that we can still customize by doing all of this or all of this. And we can do this. Looks pretty good. The last thing that we have to do is to add these two values together, which is incredibly simple. All we need is the plus operation. Now we have the crosshair that we can customize to our heart's content. Let's say I want to have a smaller circle size, then this thing should be, say, like so. And I guess the crosshair distance should be here. This looks about all right. And I would really recommend you to go through the math and just add a lot of points and go through this math step by step. The math operation itself really is not difficult. The most complex bit of math that we are doing is basic multiplication and basic addition. That creates the entire shader. The only difficulty is how all of these values come together. And this you will only understand when you add lots of points and do the math, then you get the intuition of how this is working. The next shader I want to work on is going to be an energy shield spacey kind of thing. For this one, we mostly have to focus on how to combine values. We have a main circle shape with a noise texture and then a highlight color as well. Once again, for all of this, the math isn't complicated, you just have to understand the system, which I hope you're getting closer to. But let's work on it step by step as always. Here we are in Godot, and I have a node 2D, a sprite 2D, a camera 2D inside of a folder called shield. And I want to add a new material, shader material, new shader with all of the defaults, create. Once again, we don't need a vertex shader, although we are going to use it a tiny bit at the end, but that is going to be very basic. As always, I want to start by creating a circle, which I think at this point is going to be fairly trivial. I want to create a const center, which has to be a vector 2. This is always going to be vector 2 with 0.5. And then I want to have a float circle main. This will be the step function, distance, the UV coordinate to the center, where the cutoff point is going to be some kind of radius, which we should define. This is going to be a uniform float radius with int range and a default value of 0.5. To visualize the result, I want to have color A, circle, main, and there we go. We have a circle. Besides that, I want to have a second circle that is going to be different. That circle should be transparent in the center. However, the closer we're getting to the radius, the closer we should be getting to 1, which we are then going to use for the alpha value. Hence, we get a nice gradient that will become more and more visible the further we are from the center. Now, this you could already do in a basic way. Let me demonstrate. You could simply get the float, let's call it circle inner, for which we are using the distance from the UV coordinate to the center without using the step function. If we now multiply the value with the main circle, so circle inner, we get kind of a gradient that is invisible in the center and becomes more and more visible the further we get from that center. This does work, and you could customize it to make it work, but this doesn't look great. We want to have more control over the gradient so that we can tell where it's starting and where it's ending. That we can do with the smooth step function. This one works kind of like the step function, except we have one additional parameter. We have a limit 1, a limit 2, and a value. Godot is fundamentally going to check if the value is inside of the limits. If that is the case, it is going to interpolate the value. So we are always getting a value from 0 to 1. If limit 1 is 0 and limit 2 is 10, with the value being a 1, then this function would return a 0.1. We are 10% on the way to 10 from our starting point 0. If we exceed limit 2, then the value will be kept at 1. And if we go below limit 1, then the value will be kept at 0. At the minimum, we have 0, then we have some kind of gradient, and then we get a maximum value of 1. With that system, we can create a gradient with a starting point and an end position. Let's say for now, as an example, I want to go from 0 to 1 and then get the distance of the UV position to the center. And all of that we want to multiply with color A. Now, once again, we are getting a basic gradient that looked like the thing we have done before. But what we can now do is update the minimum value. If this is 0, we are starting at the center. But if this is 0.2, then we have a shorter gradient. And this we can push up to 0.5, then we can't see anything anymore, because the distance at the most can be 0.5. That would go from the center to the right side. Let's go with 0.2 for now. And to make all of this more visible, let's change color.rgb to vector 3, 1. That looks much better. Now, if I change these values, you can see much better what is happening. We are fundamentally checking an increasingly small band between the outer radius and this starting point. I think I am going to keep it at 0.25, which looks reasonably okay. That being said, we could define a uniform float width using the usual stuff, int range from 0 to 1 with a default value of, let's say, 0.25. And this value I want to use in here. That way, if I have the inspector and shader parameters, I can change the width of this thing pretty easily. Although you do have to be careful, if we cross 0.5, this doesn't work anymore. I want to multiply width with 0.5. That way, I can move this around and we are capping out at the maximum. Let's keep it at the default value. This looks alright, although I think now, since we are dividing it by half, it should be 0.5, like so. That looks much better. With that, we basically have the main shape. We could put all of this inside of a separate function, or alternatively, what you see much more often is just a comment with the main shape, which I also want to store inside of a float main shape. All we want is this operation, and the alpha color is then going to be main shape. Same results. Let me move all of this down a tiny bit, because next up, I want to add the highlight shape. This will be one point, let's say up here, that is going to be brighter. So inside of a radius around this point, we want to make this circle brighter. Or in other words, to the main shape, we want to add stuff, depending on it being inside of the radius of the highlight circle. The end result is going to be a float highlight underscore shape. This part will be your exercise. Add a highlight shape that should look like this. For now, we will only work on the alpha values. Pause the video now and see how far you get. For this highlight shape, most importantly, we will need some kind of position, which needs to be a uniform vector 2 highlight center. Next up, I want to check the distance from the highlight center to the current pixel position, so UV. Just to demonstrate what we are getting, let me show the highlight shape. We are getting the distance from the top left corner, which we want to invert, so 1 minus the distance. Inside of the inspector, we can move this point around to anywhere inside of this field. Let's for now move it here-ish. That looks about all right. And also, while we're here, I don't need a crosshair anymore. And I want to get rid of the other shaders so we can focus on the shield. Now that we have that part, we have to add a few more adjustments. The most important part is that this shape should be constrained to the main shape. Which means when we're getting the alpha value, I want to multiply it with the main shape. That way, we are getting a highlight that once again we can move around like so. And there you can see we can highlight the shield in specific parts. Although this I do want to customize just a bit more. I want to multiply all of this with some kind of a highlight, let's call it alpha, which we have to create. This is going to be a uniform float highlight underscore alpha with hint range from 0 to 1, with 0.5 being the default. Now what we can do is highlight alpha, and we can hide this value. Although at the moment, this is a bit awkward. If the value is 1, we can see the shape, and if it is 0, we can see the entire thing. It shouldn't work like that. At the moment, that is happening because we are multiplying before we're doing addition and subtraction. All of this should be inside of parentheses. That way, we are inverting the operation at the moment. So now, if I add it, we get a very faint shield, which is a bit of an issue. For this highlight shape, we have a point vaguely here, for which we have a gradient that goes roughly around this point here. However, if we end up, let's say here, this value is basically 0. I guess in practice, it would be something like 0.01. Because of that, the main shape is barely visible. But that shouldn't be the case. The main shape should always be visible. Hence, what I want to do is to multiply all of this inside of highlight shape with the main shape. And for the final output, I want to add it with the main shape. That way, if I now toggle the alpha value, we're getting one part highlighted, but the main part of the shield is always visible. Once we have colors, this will look a lot better. Although before we get to that, one more thing I want to do. Right now, we cannot control the size of this shape. Now for that, I guess you could use smooth step, but that's kind of overkill. A better approach would be the power function. Let's say if I add 2.0 in there and only show the highlight shape, so you can see what's happening. If we're taking a power of 1, we're not changing the value. And if I set this to 0.1, then we are increasing the value. In my case, I want this value to be 2.0. That way, we're getting this nice highlight effect. If you make it larger, this area is going to become smaller. Just to explain the math, as always, you want to think about every single pixel. At the moment, we are looking at the distance to the highlight center. The highlight center is roughly here, so this distance would be 0.2. Since we're subtracting that value from 1.0, we are getting 1 minus 0.2. The result would be 0.8. The power function now does this operation. So we are taking the power of 4. For an easier calculation, let's go with 2. That way, this would be to the power of 2. Or in easier terms, the operation would be 0.8 times 0.8, which is 0.64. We have made the floating point value a tiny bit smaller. However, if we are exactly on this point, so we're doing 1 minus 1, then we are doing 1 to the power of 2, which is still going to be 1. Effectively, the closer we are to the center, the less these values change. But the further we go from that point, the more the values are affected. For example, if you do 0.2, so the point that's vaguely here, to the power of 2, then you would do 0.2 times 0.2, which is 0.04. A much sharper drop than what we have seen from 0.8. For that value, we went down maybe 10-ish%. Whereas for this one, we decreased it by a lot more. In practice, the power function concentrates a gradient around a center much more. And the higher the number for the power, the more you concentrate it. So for our purposes right now, I want to go for power of 3. And then we have the highlight shape, which should be added to the main shape, hence main shape, plus the highlight shape. Just to double check, you can see that we have a highlight shape that looks pretty good. With that, we can work on the colors, for which I want to create a vector-free color, which, let's say for now, is going to be a vector-free with 1, 0, and 0, meaning we're getting a red color. This red color we can use right away instead of this vector-free 1. So color, then we're getting a red color that still gets the highlight shape. Looks good. I want to have 2 colors for the shield. One for the main shape and one for the highlight shape. All the way at the top, I want to have a uniform vector-free main color, which is going to be a source color. So we get the color picker. Besides that, I want to duplicate this thing and get a highlight color. For the actual color values, the main value I have set to 26A7 EC, and the highlight color is a purplish value with FC00A9. Although if you want to use other colors, that's totally fine. The actual value in here doesn't matter. As long as you have some kind of vector-free that is visible, you are good to go. I also don't need this much white space. That looks better. And now, for the color, we have to figure out how to combine the highlight shape and the main shape with the colors. For which, I want to start by getting the main color and multiplying it with the main shape, which is already giving us a bluish color. And I think to make all of this more visible, what I also want to do is to add another sprite 2D in the background, which we can give a gradient texture 1D that I want to scale out like so, and then make the entire thing black so we can see much better what's going on. The default background isn't great for this kind of operation. In a second, we are going to add glow, which makes all of this much more visible. But before we get to that, I want to get the main color plus the main shape, and then add the highlight shape with the highlight color. And that way, if I have the shader selected, I can control the alpha amount of that highlight, and I can change the color to whatever I like. A bit hard to see, but you get the idea. Also, we can move this thing around, which looks pretty good. After that, to add glow, I want to multiply the color with a vector 3. If this one, for example, has a value of 2 for x, y, and z, then we get brighter colors. If this is 5, it is much brighter, and you get the idea. If I set it to 10, then the effect becomes too strong. So you do want to cap it out at, let's say, 5. Now this we want to control via a uniform float glow with a hint range of 0 to 1. And then we can do the glow amount times 5.0. This at the moment is not going to be visible because glow is 0. This should be at least 1. Or well, inside of this slider, it should be 0.2 because we are multiplying it with 5. But other than that, this works pretty well. Now we can control the glow of this thing. To make sure that we always get at least 1, we can do 1 plus glow times 5. That way we have a stronger effect, which I think is still looking okay, but at the minimum, we get the original shield, which now looks a bit bland. I guess we can go with something like this. Cool. With that, we have the basic shape and the color. Next up, I want to add a texture, for which, first of all, we will need another uniform, and this one has to be a sampler 2D for the noise. Once you have that, inside of the inspector, you can create a noise texture 2D in which we want to create a fast noise light. For now, the default here is totally fine, but what you do want to make sure is that you have seamless enabled. That is going to be important. You'll see in a second why. Once we have that, inside of the fragment shader, I want to get a float texture alpha. I want to get the texture with the noise amount and the UV position. This will return the color information. So we get RGB and the alpha value. Alpha is always going to be 1, and since we have a grayscale, RG and B are going to be identical. We can simply pick R and we're good to go. This is now giving us the grayscale values for all of this, which we could, for example, multiply with our current shape. So add parentheses to the current stuff and then multiply with the texture alpha. And now we're getting lots of random noise around the thing that you could customize. So whatever change you make in here, like for example the frequency, we can see the result right away. You could also choose different kinds of noise. I'm going to keep it at simplex smooth with something like this. This texture I want to animate, for which we have to change the UV position. For example, what you can do is to not just get the UV, but to also add a vector 2 with time, and then for Y, we can go with 0. That way, we should be going to the right. But this at the moment does not work because this texture is not repeating. We basically go further and further to the right, but at some point we stop. To fix that, when you are creating the uniform noise, you can give it a hint. The hint that we want is called repeat enable. Once you have that, we can cycle over the texture as much as we want, which is a pretty cool effect. If you want to customize the effect, for example the speed, simply multiply the time with, let's say, 0.1, and then all of this is a lot slower. If you want to have a stronger effect, you could multiply the entire thing with, let's say, 3, which I think looks a bit better. And now we can still control the highlight alpha and the amount of glow. That still works pretty okay. Although I think we should lower the frequency, something like this, but obviously play around and see what you like. At this point, also what you want to do is to make sure that seamless inside of the texture is enabled. If you don't have that, at some point, you can see the texture repeating itself, which looks pretty bad. Although, if you like that kind of effect, sometimes it can look okay, I guess. Let's make sure I have seamless enabled. We can still control the highlight center and put this in different positions. That is working quite well. This would be the main part of the entire thing. With that, we have a main shape, we have the colors, and we are adding a texture at the end. The final effect, I think, is pretty nice. Finally, a small thing that we could be adding using a vertex shader. Void vertex. We can use this thing to make the entire thing scale up and down a tiny bit. All we need for that is to add something to the vertex position. I want to get vertex plus equal then the sin value of time multiplied with 0.05. That way we get a tiny bit of movement that is going to be hard to see. Let me zoom in a lot and then increase this value. Let's say 1 for now. Now you can see it quite a bit better. I think this is actually enough like so. That feels a bit more organic. You could change it to 10. Although there you can see we have a bit of an issue. We are only bouncing diagonally. To fix that, we want to multiply the current sin value with the vertex itself. Then we're getting something weird because now this effect is way too strong. Let's say 0.1. Then this is much better. To explain why we need this vertex, let me comment out this line just for now so we don't have too much animation. And then, remember, when we are working with the vertices, we are effectively working with these 4 points that all have their origin in the center. This would be 0 and 0. The point in the bottom right would be 64 and 64. This effectively is the direction. So when we multiply the vertex with some kind of distance, for this quadrant, we are going in the down right direction by whatever distance we have set. As a consequence, for each of these points, we are basically getting a direction that points away from the center, like so. Now, ideally, inside of the shader, when you're working with this kind of system, you want to normalize the direction, which in our case is the vertex, which you can do with the normalize function. That way, this thing is moving within a range of 0 to 1, which you can then multiply with some kind of distance. Let's do 50, make sure it's a float, and then we have a lot more control over all of this. The point down here is 64 and 64. If we multiply this vertex with the sign value, we are going to move by 64 pixels. But this isn't really that much control. And with the normalize function, we are turning this 64 and 64 into some kind of vector that has a length of 1. I think in practice this would be 0.7 and 0.7 something. The really important thing is that the length of this vector is 1, whereas the length of this vector is much greater than 1. Having a length of 1 for the vector is super nice. That way, if you multiply it with some kind of distance, you get that distance in some kind of direction. And well, with that, we have the shield that is pulsing a tiny bit, which looks pretty cool. Let's create an outline shader, which looks impressive, but isn't actually that difficult. Oh, and while we're doing that, we are going to learn 2 more concepts that should be kind of basic as well. If statements and while loops. You don't see them that often inside of shaders, but you can use them. Here we are in Godot once more, and I do have a slightly different setup. We still have the basic outline in Node2D, then a sprite, although this one is animated, and a camera. For the sprite, we have a basic bird animation that I have imported because I think this one looks really nice. But this one is important for another reason. For the outline effect to work properly, we need padding around the pixels inside of the texture. Or in other words, we have the visible pixels and we have empty space around it. This empty space is incredibly important. If you don't have that, like for example, you would have in the Godot texture, where the pixels end right on the edge of the texture. If you lack that empty space, the shader is going to struggle. Something we are going to talk about at the end of this part. It can be fixed. You basically have to use GDScript to expand this texture and then add padding. But for now, either use the bird texture or use some kind of texture that has padding around it. Really important. Other than that, for this animated sprite 2D, instead of texture, filter is set to nearest because we have pixel art. And if we didn't have that enabled, it would look pretty blurry. So this one is better. But anyway, besides that, I want to do the usual stuff, a new shader material with a new shader called outline. The rest is also fine. And then we do not need a vertex shader, nor do we need a light shader. And before we work inside of the fragment shader, I want to create two uniforms. Uniform vector 3 with the color, or I guess we could call it the line color. This one needs to be a source color, and we could give it a default value, let's say vector 3, 1. We get a white line color. Looks good. Next up, I want to have a uniform float line thickness with a hint range where we are going from 0 to 1, and the default should be, as always, 0.5. Finally, I want to have a const float max line thickness, which I have set to 4.0. So we have a line color, a line thickness that goes from 0 to 1, and then we have a maximum thickness that we don't want to exceed. Pretty simple so far. With that setup, let's talk about how we are going to approach this. And let me show the entire bird, like so. The basic logic for all of this is going to be, we will get all of the visible pixels, so all the pixels with an alpha value of 1. And then we are going to shift them in the 8 directions. So we go left, bottom, bottom right, and so on until we get all of the 8 directions. That way, effectively, we are expanding the bird texture in every direction. Once we have that, we can subtract the original alpha shapes, and the only thing that is left is an outline shape. That's all we have to do. So fundamentally, what I want to start with is a float outline that is simply going to be the current alpha value. So texture, UV, and I want to get the alpha value. This value I want to set to color.a right away. So outline here. This at the moment is not going to do anything. The input is equal to the output. Nothing has changed. But what we can now do is to add a value to the outline. For example, we can do outline plus equal and then do the same operation that we have done before. All of this, except now I want to sample a slightly different UV point, for which we need X and Y. For now, let's only worry about X, on which I want to go in one direction by a very, very small amount, 0.005. Then don't forget the semicolon. And now we have shifted the pixels a bit further to the left. And you might be wondering at this point, the UV position is going to the right, but the pixels we are sampling are to the left. The next section is going to be entirely on UV coordinates. Basically, the UV scale and positions are always inverse to the stuff on the texture. So if you go to the right on the UV coordinates, you go to the left on the texture. It's going to make a lot more sense in the next part. But with that, we have one direction. This we could duplicate in the other direction as well. So duplicate this line and then add the same thing to the right side. And now we get more pixels on the left and on the right. That means, next up, the only real thing that we have to fix is to get the right color for all of these pixels. And for that, to keep the math simpler, I don't want to have a vector 3 for the line color, I want to have a vector 4. So this line color has the alpha value included, which we are not going to use. But having this as a vector 4 makes it easier to combine it with the color property. For that, we don't want to do this line anymore. Instead, we want to update the entirety of the color right away. And before we are doing that, I want to get the original color values. I want to have a vector 4 color, which is going to be what we have done here without the alpha value. Once we have that, we get the original pixel colors. And then for the outline, we can get color A, which so far is not going to make a difference. But what we can now do is update color entirely by mixing the current color with the line color depending on the outline. So if I add outline in here, we are going to get a pure white color. That should make sense. We're getting the current alpha values and then adding a bit of stuff to the left and to the right. Hence, any visible pixel will become white. From that, we want to subtract the current alpha values of the original texture, color.a, which is not going to do very much. We are getting a couple of black pixels, but most of them are still pure white. The line that we need to fix this part is outline is equal to min, outline, and 1.0. If we're adding that, then we are getting the proper outcome. The reason we need this line is to make sure that once again we have a range for the pixels that go from 0 to 1. If any of the outline pixels gets above 1, let's say 2, then via this line we are always picking the 1. The reason we need that is for all of these pixels on the inside. We are getting, let's say, this pixel and then moving it to the left. And this is additive, so we keep on adding stuff. As a consequence, very quickly, the internal values in here are going to be much greater than 1. The only ones that keep the original value are these corner pixels, which is a problem because inside of this operation, the original color A values are 1. But if the outline value is a 4, then the result would be a 3, so we still have a pure white color. This should instead be 0, which we only get if we're limiting this value to a 1, which is what this line is for. This one is pretty important. Other than that though, we are pretty much good to go. What we now have to do is to duplicate this line a whole bunch of times to cover the additional sides. For example, we could also add a plus with 0 on the x-axis, 0.005 on the y1. That way, we are going up, and if I duplicate this to go negative, then we also get the bottom part. This would give you a very basic outline. Although, if you look closely, this isn't ideal because the pixel size is not consistent. This we can fix by adding a vector to size. When we are setting the line thickness, we want it to be consistent with the pixel size of the texture. That value we can get. It is simply, in all uppercase letters, texture pixel size. This value is 1 divided by the size of the texture. So for example, if this thing was, let's say, 100 pixels wide, the x value would be 1 over 100 or 0.01. You get a vector 2 returned. So this is working for x and y. All of that we want to multiply with the line thickness. And then, when we are getting the outline, we don't want to multiply it with 0.05, but rather size dot x, which I also want to do for the second one. And for the third and fourth one, we want to go size dot y. That way, all of this is much more consistent. On top of that, if you look on the right, line thickness can be customized. So now this is working much better. And to account for the max line thickness, all we have to do is to multiply this like so. That way, we are getting a much greater value that you do want to control. Let's go with I think the max line thickness should rather be 2. Otherwise, this is getting a bit strong. Let's stick to 0.5. We are nearly done with the basic setup. At the moment, we're getting the 4 directions, which does work for this kind of setup, but we are missing a lot of pixels. At the moment, we go left and right, up and down, but we are not going diagonally. For that, you would want to copy this one more time and then go, for example, with plus vector 2 in size.x and size.y. That way, we're going to the top left. If I comment out this line, you can see where this is going. Also, what would be a bit cleaner for the math is to not use minus vector 2, instead plus vector 2, but then minus size.x. The end result is the same, but the math I think is easier to understand. So this I want to do here and here. That way, all of this is much easier to read. Especially for the diagonal values, this is quite important. Now we can add a minus here, a minus here, and a minus for both of them. That way, we are getting all of the directions, which still works with the line. So this is looking quite good. And this would be the basic shader. It's actually pretty simple. Fundamentally, we're getting the alpha value of every single pixel, and then we are shifting it around in all of the 8 directions. Once we have that, we are cutting out the center bit and coloring the corner pixels. That's all we are doing in here. But while we are doing that, we can cover a few more additional concepts. Number 1, we only want to do all of this if the line thickness is greater than 0, which we don't necessarily have to do, but if this value is 0, doing this kind of operation isn't necessary. So we could add an if statement that we only want to do all of this if, and now you need parentheses, line thickness is greater than 0. To get an if statement, you need curly brackets, and then add all of the code that you want to have in the if statement, like so. Now, there is no obvious difference, but line thickness still works, and if it is 0, then we are not doing any of this. That being said, using if statements inside of a shader generally is not recommended. The reason is we are running logic for every fragment. And if one of those fragments has a complex if statement that takes a bit longer to calculate, you are slowing down the entire shader. Because of that, a lot of shaders use quite a bit of math to get around if statements. I guess when you're getting started, using them is totally fine. But for more advanced effects, and if you really care about performance, avoiding them is a better idea. With that, we have if statements. Besides that, I also want to talk about loops. Because looking at these 8 lines, you can tell this is super inefficient in terms of writing. We are pretty much copy-pasting 8 lines. This should be a while loop. Creating that is going to be your exercise. I want you to research 4 loops in a shader and convert our current shader code. To make this a bit faster, here is the relevant part in the documentation. Pause the video now and see how far you get. Back inside of Godot, let me expand all of this so we have more space. And I want to comment out the entire fragment shader and create a new one. Void fragment. That way we keep the original. I want to create a vector 4 color like we have done before with texture, and the UV coordinates. And then I want to check if line thickness is greater than 0. If that is the case, I want to do all of the logic. I want to create a float outline, which is going to be color A by default. Then we need a vector 2 for the size, texture pixel size times line thickness times max line thickness. All of this we have done before. Those bits are pretty simple. But now we can do the for loop, for which we will need 3 parts. The start value, which is going to be a float that I called y with a start value of -1.0. Next up, we need basically the end value, or rather the end value condition. So we want to check if y is smaller than 1.0, and this should be smaller than or equal to. Finally, we need the step size, which we can set to y++. This is going to give us the y values. Next up, we need another for loop. So we are getting the float x values that work in the same way, -1.0. We want to go up to x being smaller or equal to 1.0 with x++. Also, really important, you are separating these bits using a semicolon, which I have just forgotten, so it should be like this. I want to create a vector2 that is for the offset, where we are getting a vector2 with x and y and multiply it with the size. Finally, we can update the outline value by simply adding texture with texture, UV, and then plus the offset. And we always want to get the alpha value. And that is it. These nested for loops do the same as all of this. After we have that, we can update the outline, get minimum outline and 1.0, get color, and mix the original color value with the line color, and then outline minus color.a. And I guess I should show the final result, for which we also have to add some line thickness, and this is still working just fine. Let's go with 0.25. I think that one looks pretty good. And now we have covered 4 loops, which are really powerful, but you don't see them that often. Because understanding shaders with if statements and for loops does get a lot more complex. Most tutorials you see online use this kind of logic, which is totally fine, and honestly, in terms of lines of code written, it's not that much of a difference. Choose whichever you prefer, both would be acceptable. And by the way, what I forgot to mention, if I run the scene, we do get the animation, but the shader doesn't really care about it. Because when you are running the animated sprite frames, so we get all of these, we always get the texture into the shader. And the shader doesn't really care what the texture is. It simply does all of the operations and then returns the output. That way, animations can be incorporated super easily. However, what cannot be incorporated is one issue about the padding. Let me add a sprite 2D with the Godot logo, like so, and then assign the same shader to it. I want to add a shader material and then direct the outline shader in there. Now we are getting not really a great result. We get a couple of white outlines in the corners, and those can also be animated, so this does work. But on all of the borders, since we don't have empty pixels, so the shader cannot go outside of this texture, we don't get anything. And that we are fixing using GD script. Let me add a script to the outline, and then we have to add padding to this sprite 2D once the scene is ready. func_ready, get the sprite 2D, and update the texture with a function called add padding to texture. We want to get the texture that we want to change, like so, along with the amount of padding that we want to add, let's say 5 pixels. Sadly, this function isn't built into Godot, so we have to create it. Add padding to texture with the original texture. This needs to be a texture 2D, and we have padding that we want to add, an integer. The entire thing is going to return an image texture. In here, we need the original image, which we get from the original texture.getImage. This gives us the actual pixel information. Before we can update it, we have to check for 2 things. Number 1, if original image is compressed. If it is compressed, we can't change it that much. To fix that, we need original image and decompress. Besides that, we want to have a specific color format, which we can check for if original image get format, if that value is different from image format RGBA 8. This is the format that you can work with the easiest. So if the format in our current texture isn't that, we want to convert it. Original image, convert to this value. With that, we are making sure that the original texture isn't compressed and that we have the right format. Once we have that, we can actually change things. I want to get a var new width, which is going to be the original image, get width, and then add padding multiplied by 2. By 2 is important because we want to add the padding to the left and to the right. The same thing we want to do for the height. So new height is going to be get height plus padding times 2. I want to create a new added image, for which we want to create an image with the new width, the new height. We don't need mipmaps. I'll talk about those later actually, but here you can just use false. And then we need the format. We want to go with image, format, RGBA, and 8. This would create a new image, which by default should be entirely empty. So padded image dot fill with a color value that is entirely empty. 0, 0, 0, and 0. No color and no alpha value. But what we do want to do is padded image split a rectangle. On this line, we created a new image that is larger than the original. But we do want to reinsert the original with the padding around it, so that we have this value on every single side. For this thing, we are placing the top left. So we have to make sure that we are getting one bit of padding to the left and one bit of padding to the top. And then we are good to go. We will need the original image. Then we need a rectangle 2. This will be for the size. But we want to go from 0 and 0, so the top left. And then the original image, get width. And we want to do the same thing for the height. This covers the size. Next up, we need the position, for which I want to have a vector 2 with padding and padding. The last thing that we have to do is to return an image texture that is going to come from an image, which we can get via create from image with the padded image. And with that, if I now run the entire thing, we get a proper outline that sadly we cannot see inside of the editor. So in here, we don't get a border, but if we run the scene, we do get one. And this looks much better. I suppose what you could be doing is to add a slider that I want to make a bit larger and move down, and then connect the signal with value changed. And in here, I want to get the sprite 2D dot material and then set shader parameter, where we want to update the line thickness with value divided by 100. That should do something. If I now run the project, I can change the slider and we get a different kind of outline. Works pretty well. In this section, I want to talk about UV values. We have used them a tiny bit, but they can be pushed quite a bit further. You can use them for a couple of basic effects, and much more importantly, we are going to use it to create a pixelation shader. Although getting there will take a bit. Back inside of Godot, I have the usual setup, and I want to add a new material, shader material, along with a new shader. All of the defaults here are totally fine. And finally, we do not need a vertex shader as always, and I don't need the light shader. Instead, I want to, at least for now, visualize the UV values, which means color.rgb will be a vector 3 with UV and 0 for the blue values. That gives us the familiar UV graphic. The top left is the point 0 and 0. The bottom right is point 1 and 1. We are always within a ratio of 0 to 1, at least by default. This value is what we are using to sample a texture. Or in other words, I could get color.rgb and then assign it texture with the current texture of the node along with the UV values, on which we want to get the RGB values, and then we get the same result that we had before. Basically, what happened now is that we have the UV box, so the thing that we have already seen. And in there, we have the texture. What this texture function is now doing, it looks at the UV values and then it samples these points. For example, if the UV value is right in the center, then from this original graphic, we are picking this center point, which I guess is a white pixel right on top of the nose. But this relationship we can change by creating a custom UV value. For example, I want to create a scaled UV. And since this is a vector 2, we can simply multiply it with 2. What happens if I now use this scaled UV instead of the default 1? Then we are only getting the top left corner. Why is that? Let's say in the original UV position, we were here, where the X position is 0.1 and the Y position is 0.4. What now happens, because we multiplied this value with 2, these values become 0.2 and 0.8. As a consequence, all of the points are sampled further to the right and further down. The end result is the Godot logo being pushed to the top left in the opposite direction. We can also add or subtract values. Let's say I want to subtract a value of 0.4 and 0.1 inside of a vector 2. Then we are moving this thing around, which could also be a uniform, let's say, uniform float for the X values, where we are getting a hint range with the usual stuff. And this we are using inside of the vector. With that, inside of the shader parameters, I can move this thing around from left to right. Let's keep it at 0.6 and explain. Imagine the same point. We are here with, I think X was 0.1 and Y was 0.4. This value we now duplicate and move around using a vector 2. As a consequence, this vector 2 becomes 0.2, but then we are adding the X part as well, which will subtract at the moment 0.6, or whatever you have specified in here. And I think the best way to visualize all of this is to actually display the inside of color.rgb. I want to display a vector 3 with the scaled UV and 0 for blue. There you can see it a bit better. If I move this value around, we are simply shifting all of these values on the horizontal axis. And this is then used to sample from the original texture. Understanding this system is incredibly useful. Although because this is inverted, it does take you some time to get used to it. To finish up this part, I want to talk about the surrounding pixels, because at the moment, we get a lot of border pixels that are being repeated. I'm pretty sure you don't want that. Now, you could go to Texture, Repeat, and then set Enabled. Then you get a pretty interesting effect that you could use for stuff. Although I guess this is also very situation specific. Sadly, setting it to Disabled doesn't fix it. Instead, when we are using the shader, we have to tell Godot to clip all of these pixels. There is a formula that you can use. We want to create a vector 2 mask with 2-step functions. Number 1 is going to be a vector 2 with 0 for the edge, and the actual value is the scaled UV. If I then get the color.a value and multiply it with mask.x times mask.y, we are going to get rid of half of these pixels. All the pixels to the left and on top of the original texture are going to be below 0. And with the step function, the return value for this is going to be 0 if we have a pixel here. That way we can cut out all of them. The same thing we can do on the right side, for which we simply need to multiply this step with another step function. The edge is going to be the scaled UV, and the value is going to be a vector 2 with 1. Finally, to get rid of the corners, we have to update this value. I guess we can store it entirely inside of a, let's call it vector for scaled texture. And on this thing, I want to update the alpha value, like so. Finally, we can get color and assign it the scaled texture. That way, we should get a really nice effect. And this you can still move around, which looks pretty good. A really important thing when you are scaling or moving UVs is that all of this is always inverted. When we are moving the X position to the right, it only goes to the right because this operation is minus. That's the last thing you really want to think about here. But most importantly, I guess, practice and think about the UV positions relative to the texture. It is a tricky thing to understand, but once you get it, it's super powerful. In fact, there's one way I want to use it. And before I'm doing that, I want to add some comments here because we're going to write quite a bit more code. The first part is for scale and position. The next part is going to be on centering. There's one formula that you see all the time when working with shaders, where you have a lowercase uv and then 2 times uv minus 1. This formula is centering the UV values around the center point of the texture. I can demonstrate that by assigning once again color.rgb to vector3 UV and 0. Then we have 4 quadrants. The top left is black, the top right is red, the bottom left is green, and the bottom right becomes yellow, because in here we are mixing green and red. To understand the logic for this one, let's do 3 examples. The first value is in the original center point, 0.5 and 0.5. In a standard UV coordinate system, this is the center. But because of the entire formula, we are multiplying all of this with 2 and then subtracting 1. Because of that, we're getting 1 and 1 minus 1, which is going to be 0 and 0. This center point is the coordinate position 0 and 0. For another example, I want to look at the position 1 and 1. This we are still multiplying with 2 and then subtracting 1. As a consequence, we get 2 and 2 minus 1, and we end up on 1 and 1. The bottom right corner in the original coordinate system stays the same. This point is still 1 and 1. But now, finally, if I do a third example with 0 and 0, the original top left position, multiplying this with 2 and subtracting 1 will give us 0 and 0 minus 1, which is going to be minus 1 and minus 1. This point, instead of being 0 and 0, is now going to be minus 1 and minus 1. We have a center point, and in the bottom right, we are maxing out at 1 and 1. In the top left, we are maxing out at minus 1 and minus 1. The top right would be 1 and minus 1. The bottom left would be minus 1 and 1. That way, we have a centered UV coordinate system, which can be surprisingly useful. For a very basic example, if we wanted to create a circle, we now, to overwrite the alpha value, simply need to get the length of the current UV position. Since the origin point is 0 and 0, the direction is going to give us a circle, which we could, by using the step function, turn into a proper circle, like so. For something a bit more useful, since this is the center, when we made the crosshair shader, we had one formula for this rectangle to the right of the center, and then we needed another formula for the left side. We couldn't mirror it because the center point was 0.5, which is awkward to work with. But now, since this point is 0 on the x-axis, we could simply look at the value, let's say for this one, 0.5 and negative 0.5. and then mirror them super easily. All you need for that, and once again, let me use the color A values. I want to get the distance of the uv.x position to some point, let's say 0.5. This is giving us a line to the right of the center. But if I now turn this uv.x into the absolute value, then we also get the left side, which we can turn into distinct values using the step function, like always, with, let's say, 0.1. And now we have gotten two rectangles with much easier math. Having the UV coordinates centered around the center point can make your life a lot easier. UV.x would be 0 here, 0.5 here, and minus 0.5 on this point. Like so. And the absolute function turns this into a positive value. Hence, the left side and the right side are identical. Cool. With that, we can center a UV coordinate system. Next up, I want to start with a basic Pixelate shader. And for now, I want to define a vector2 grid that defines how many pixels I want on the x and the y axis. So a vector2 that is going to have, let's say, 4 and 3 pixels. Something like this on the x-axis, and on the y-axis, I want to have it like so. The end result should be separating the graphic into 4 columns and 3 rows. The formula for that is I want to have a vector2 with a pixel uv, where we are using the floor function in which we multiply uv with the grid. And the end result, we are dividing by the grid again. If I now show the result, you can see what this is doing. Color.rgb is going to be vector3 with pixel uv 0, and then we get a really interesting result. I guess just to demonstrate how this can be used, I could also update color.rgb to texture with the current texture and the pixel uv, on which we want to get RGB, and then we get a very limited amount of pixels. So what happened here? Let me only show the UV colors, like so, and then explain. Once again, to understand the shader, you want to plot in random values and do the math for them. That is the only way to really understand what is happening. Let's say for now, I want to be in the top left-ish position, where the original UV position is, this could be 0.4, and we get on the y-axis 0.1. Once we have those, we have to do this formula, where we get the UV position 0.4 and 0.1, which we are then multiplying with the grid, which in our case is 4 and 3. And the entire thing, we are once again dividing by 4 and 3. And don't forget, we are using the floor function, so all of this is going to be floored. To start with, we are doing this operation. 0.4 times 4 is going to be 1.6, and 0.1 times 0.3 is going to be 0.3. But because of the floor function, let's write it like this. This becomes 1 and 0. Floor is basically discarding anything after the decimal point. This result, we are still dividing by the original grid, 4 and 3. To do this operation, you want to go by the x values first. So we are doing 1 over 4, which is going to be 0.25. For the y part, we are doing 0 divided by 3, which is a very simple calculation. We are going to get 0. These two values are the actual UV values that we get. And this lines up perfectly with what we see, because 0.25 is this line here, and 0 is the top. If you combine the two, we are here. Via this formula, we are always jumping in increments. At this point, I would very much recommend you to add a few more points and do the math. It's going to be incredibly useful. This function you do see quite often, and you really want to understand it. Although once you do, this system becomes fairly trivial. We are not doing any kind of complex math. we are just using clever tricks to manipulate the UV coordinate. That's pretty much it. And to make this a bit better, let's go with 20 by 20 cells. That way we get a much nicer result. Although in practice, this doesn't look great. Let's go with 24 by 24. That's at least a bit better. What we are going to see when we work on the proper Pixelate shader is that this formula has one critical flaw. Look at the top left and the bottom right. Those are not identical. This function is pushing down the texture ever so slightly to the bottom right. And that is super not good. We have to account for it. Which can be done, we just need a bit more math. That's going to come later. For now, I just want you to understand this basic math. Other than that, we can cover the final part, and that is going to be a checkerboard. For which, once again, I want to create a vector2 grid. This time, I want to straight away use the floor function with UV times 4. If I am doing that and display the output, color.rgb is going to be a vector3, grid, and 0, we get this. If the UV position for either x or y is greater than 1/4, meaning we are down here, then this value is going to be a 1. If, however, we are here, so UVX is below 1/4, then we get no red values. If, however, we are up here, so UV.Y is below 1/4, then we don't get any green values. We would only be left with red. As always, plot a whole bunch of points in there, then this is going to make sense. To turn this into a proper checkerboard pattern, I want to create a float checker, for which we are going to use mod grid.x plus grid.y. The second argument will be 2.0. If I now assign color.a to checker, we're getting a checkerboard pattern. So, what happened here? I guess before we talk about the grid itself, we should talk about the mod function. It stands for modulus, and the usual symbol for it is the percentage sign. This gives you the remainder of an operation. For example, if you do 3 mod 2, the result is going to be a 1. The 2 fits into the 3 exactly 1 time. The remainder is going to be the integer 1. I guess we can actually demonstrate this by using color.rgb with, again, a vector3 with mod 3 and 2. Don't forget the semicolon. Now we're getting a white color. That is because this value returns a 1. If this was a 2, we would have a remainder of 0. 2 fits into another 2 perfectly, so there is no leftover value. But if we do 1 mod 2, the 2 does not fit into the 1 cleanly at all. So we don't get a division in the first place. So the 1 is what we're getting as the remainder. Basically, with this formula, we are checking if this number is odd or even. The return value is going to be either 1 or 0. For example, 5 is an odd number, while 6 is even, so we get 0 returned. 7 is odd, so this one gets a 1. If this kind of thing confuses you, definitely play around with it a bit more. Fundamentally, it's a really simple system. Usually people explain it with dots. That is, I think, a bit easier. Let's say 3 mod 2. The result is going to be a 1. We have 3 yellow dots, and we want to divide them by 2 green dots. We can remove the green dots from the yellow ones, and we get a leftover of 1. That's what this 1 stands for. I hope that makes sense, because now we are going to combine it with the grid. And as always, to understand all of this, let's do an example. Let's say the UV coordinate point is here. We are on the x position 0.4 and on the y position 0.1, which is a vector 0.4 and 0.1, which we are multiplying with 4, like so. The end result is going to be 1.6 and 0.4. Because of the floor function, this is going to be, let me do it down here, 1 and 0. we simply get rid of anything after the decimal point. These two values we now add together, which means we are doing 1 plus 0. The end result is going to be a 1. Finally, via the mod function, we are doing this operation, which is going to check if this 1 is an even or an odd number. The end result, at least for this pixel, is going to be a 1. So finally, this pixel is going to be visible. The basic idea for this checkerboard pattern is via the for, we are turning this thing into rows and columns. And then via the mod function, we are checking if every single cell is either even or odd. That way, you can get a checkerboard pattern. Once again, and I know I'm repeating myself, but to really understand this, you just want to sit down with a piece of paper and calculate a whole bunch of examples. That's the only way to get an intuition of what is happening here. But if you have done that, and you went through all of these 4 UV operations, you should be quite comfortable changing these values, at least on a basic level, which we can then use in the next part to create a proper pixelation shader. That is actually going to be your exercise. I want you to create a good pixelation shader that accounts for the offset that we are getting from the floor function. This is going to be a bit more advanced, but just try to see if you can figure it out. Basically, you want to play around with this function and see if you can add some kind of offset with lower values, that the bottom right is a pure yellow color. If that is the case, you know you have the right scaling behavior. I'm going to finish this video here and do the pixelation part next, but definitely try this one yourself. Alrighty, time to start the Pixelate shader, for which back inside of Godot, I have created a new folder. And we have the usual setup, a node 2D, a sprite 2D, and a camera 2D. To the node 2D, I want to add the shader material with a shader, canvas item, Pixelate. That looks all good. And then we can write some shader code. We want to work entirely inside of the Fragment shader. And then we have to export a uniform float pixel underscore size with a hint range from 0 to 1. Inside of the Fragment shader, we will need let's call it the pixel UV, for which we will need the usual formula. Floor UV, and this we want to multiply with what we called before the grid dimensions. This I am now replacing with the pixel size. The entire thing we want to divide once again by the grid, or in my case, the pixel size. This is going to make the shader just a tiny bit less powerful, because with a vector 2, we can define the rows and the columns. But if we only have a float, we always have the same number of rows and columns, which I guess for this kind of shader is okay. You could customize it. After we have that, I want to update the color to texture with the default texture and the pixel, not size, but UV. With that, right now, we can't see anything because the default value is 0. I guess for this to work, we should, at least for now, get a maximum hint range of 10. And then, in the shader parameters, if I increase this value, we get the basic pixel effect. And now we can see it much better. We always have an offset that pushes the graphic further down to the right. And that we have to account for. Fortunately, that part is surprisingly easy. All you have to do, when you get the top floor part, you want to add parentheses and then add 0.5. And then you are done. If I now do the same operation, we are staying in the center pretty well. Not completely, and this doesn't work perfectly, but I think for most purposes, this is going to work pretty well. Also at this point, what I think is going to be better is that instead of using a float, we should be using an integer. Then we have to convert the pixel size inside of the shader into a float, like so. Then Godot is happy. And now in the inspector, we can update this value. And if we don't have decimal points, this is looking much cleaner. So now we have a pixel shader that works surprisingly well. I suppose we should have a larger maximum value. Let's go with 32. If I now increase the value, we get increasingly more points that we can sample. This is looking quite good. And really quickly, to talk about why this line is working. So far, when we have used the floor function with some kind of value in here, let's say we're getting 1.9, then the floor function is going to turn it into a 1. Because of that change, we're getting a pretty large shift. A much better outcome would be to turn this 1.9 into a 2. That is much closer to the original value. All of that we accomplish with plus 0.5. If we get 1.9, let me write it here again, and we do plus 0.5, we are getting 2.4, which inside of the floor function is going to become a 2. However, if the original value is something like 1.2, then the 0.5 is going to return a 1.7, which will become a 1 still. For all practical purposes, this plus 0.5 changes the floor to a rounding, where any value below 1.5 will become a 1, and any value above that will become a 2. We can refine this just a bit more. I want the pixels inside of the shader to be relative to the original texture size. For which, number one, we will need to get a vector to texture size. Let's call it pixel. For that, we will need 1.0 divided by texture pixel size. That gives us the current size of this texture. I think for the Godot logo, this would be 128 by 128. This we can use for another vector 2, our grid dimension. Texture size pixel divided by a float of the pixel size. I want to use this grid instead of the float of the pixel size. And with that, we get much more consistent pixels. If I now change this number, the lower it gets, the higher of a resolution we have. And if I get to 1, we have pretty much the original. Not perfectly, but it still looks pretty good. And if I increase the value, we get a nice pixel shader. I guess some values look better than others. So this one works really well, but 13 is not looking so good. You definitely want to refine this a bit more. But I think to get started, this is a pretty solid shader. In this section, we are going to combine trigonometry with shaders, which will allow us to work with angles and waves. Trigonometry is incredibly important for shaders. You do see it all the time. So in this part, we are going to apply the math to shaders and explain the math in the first place. Although before we are starting with that, I want to talk about the most basic way to use trigonometry, and that is waves, which you can achieve via the sine and the cosine function. Both of those simply give you a wave that gets a 1 at the top and a -1 at the bottom. Cosine does the same, except it is a bit offset. Other than that, same concept. Now the math on why we are getting this wave, we are going to cover in the next part. For now, I just want to use the absolute basics of trigonometry. The end result is going to be a basic animation for the Godot logo. Via this one, you could, for example, indicate that some kind of machine is active. Stardew Valley, for example, uses this kind of system a lot. Back inside of Godot, I have a new folder, 3 Trigonometry, where we are currently covering part 1, Waves. This scene contains a node 2D, a sprite 2D along with a camera, so the usual setup, and I have already assigned a shader to this material. For this part, we will only need a vertex shader. Let's say I want to update the vertex positions, for which I can use sin, so the sine function, with time. If I'm doing that, we are going to move the logo. Let's only do this for the x values. .x. That way, we are only going left and right, which is a bit hard to see. So let's multiply this value with 20. So what happens here? What do we get from sin time? Let me comment it out so we don't have too much movement and talk about it. The way you want to think about it, we have a coordinate system with x and y values. The sin curve in this coordinate system would look vaguely like this. Depending where we are on the x-axis, we would get different y values. For example, if we are here, we would get this value. If we are here, we would get this value, and so on. And since we inserted the time as an argument, we keep on moving forward on the x-axis and keep on getting different values. So we're here, 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 and here. Then we're going here, down, and so on. We always move between a value of 1 and -1, which we are then multiplying with 20. As a consequence, the Godot logo first goes right, then goes left, then goes back right again, and so on. So basically, all you have to understand at this point is that this function gives you a value that goes from -1 to 1, and then back to -1, and this goes on forever. Besides the sine function, you also have the cosine function that basically does the same thing, except the starting point is different. Other than that, it's pretty much the same thing. Besides that, you have the tangent function, which unfortunately looks very different. So let's not use this one yet. I only want to work with the sine function. This one is much more predictable. So just to add a comment, this one is giving us a value of -1 to 1. But this very often is not what you want. Maybe you want to get values that go from 0 to 1, for which I want to have a float normalized curve. The formula for this one is 0.5 times 1.0 plus sin of time. If you're using that value to update vertex.x, like we have done before, normalized curve, and make sure this is plus equal, and you want to multiply the entire thing with 20 so we can see something. Now, we are only going from 0 to 1. And to understand it, as always, you want to plug in a couple of random values into this function and then do the math. Let's say the value for this one is a 0. 1 plus 0 is simply going to be 1, and multiplying this with 0.5 is going to give us a 0.5, which means a 0 has become a 0.5. If the value of sine time is -1, then this whole operation would be 1 minus 1, so 0. And if we multiply that with, well, literally anything, we would still get 0. Hence, -1 is going to be converted to a 0. Finally, if we get to the maximum value, 1, then we would do 1 plus 1, so 2, and then multiply it with 0.5, so the end result would be a 1. 1 would stay 1. Which means we have converted a range that goes from -1 to 1 to a new range that goes from 0 to 1, which at the moment we are adding to the points, but you could also multiply them with the entire vertex. That way, we are scaling the whole thing, although this might be a tiny bit too large. Let's multiply it with 2. That's going to be much better. Now, we are scaling this thing from 0 to a factor of 2. And let me rearrange the comments a tiny bit so this is more readable. Like so. This would give us a standard curve that you could use, but very often you want to have a customized curve, which you can actually create super easily. All you need is a uniform sampler 2D. Let's call this one the scale curve. If you now go to material and the shader parameters, you can assign it a texture, and the texture that we want is a curve texture. In there, you can assign it a curve, like so, and then set a couple of points. You can also set the range, although in my case, I just want to add a couple of random points, let's say like so. And then we can sample from this thing, which you would do by getting another float. Let's call this one the curve output. And as always, we will need the texture function. Although before we get to that, I should explain how curves work inside of a shader. For that, I do want to add the fragment function and update the color.rgb values with texture, the scaled curve, and the UV values. I only want to get the RGB values, and then you can see we are getting something. The way it works is that this fundamentally is a texture. If this point is higher, we get more white, and if it is lower, it gets darker. That's all that's happening in here. So via that, you could create some pretty interesting effects. But fundamentally, we just want to get one pixel across the x-axis, then sample it. Via the texture function inside of the vertex, I want to get this scale curve, and then a vector 2 with, for now, the normalized curve, and 0 for the y value. At the end of it, you have to get either red, green, or blue. Since we are working with a grayscale value, all three are going to be identical. If I uncomment the vertex function and change this to the curve output, then we get a very specific kind of effect. I could, for example, change this value, and then we get a different kind of curve. If I do it like so, then you can tell stuff is happening. Doesn't look great, but you get the idea. A really important thing to understand here is that this normalized curve is giving us values from 0 to 1, and then we are going back to 0. As a consequence, on this texture, we are first going to 1, and then we are going back to 0, which in practice means we first go this way, and then we are going backwards, which is very often not what you want. What you usually want is to start from 0, go to 1, and then start again from 0, and keep on going only one way. Although I guess if this curve was symmetrical, it wouldn't really matter. But you should be able to use math to only go forward. This bit is going to be an exercise. I want you to change the curve value to only go one way. You always want to go from 0 to 1 and then start again at 0. Pause the video now and see how far you get. I want to create another float called curve forward. The formula for this one is actually annoyingly simple. All we need is fract time. And then we are done. To demonstrate, let me copy it and use it to update color.rgb. We need a vector 3 with fract time. And then we always go from 0 to 1, which means if we use this value instead of the normalized curve, we can get the vertex again. And now we're getting something pretty random. But if I change it to something like so, I think you can see it a bit better. We start from 0, then go to almost 0.5, and eventually we go back down to 0 with this kind of thing in the middle. If I increase it, then we are staying up a bit longer. For the intro effect, I went with a curve that looked something like this, where we are going to 0.5, and then we are going a bit below the 0 point, which you could push further by lowering the minimum value. Instead of just getting the curve output, I went with 1.0 plus the curve output. That way we start with the default value and add the value to it, which I think at the moment is a bit too low. Let's go a tiny bit higher. And we might have to slow down the entire thing as well, for which we can add a uniform load. I guess we can just call it the speed with a hint range to keep it simple from 0 to 5. And this I want to multiply with the time. Right now, this value is 0, so we don't get anything. But if I change it to 0.7 or maybe even 0.5-ish, then you can see we are getting a repeated animation. That's pretty much it. And with that, we have basic curves using the sine function. Let's talk about trigonometry properly. Once we have that, we can create a planetary system. Trigonometry fundamentally is the relationship between angles and distances, for which we always work in a triangle that has one right angle. For example, in this triangle, this angle is 90 degrees, and it has to be for the math to work. Each side in this triangle has a name: the hypotenuse, the adjacent, and the opposite. For our calculations, we have to look at one of the other two angles, either this one or this one. I will use the left one. That is what most people use. And by the way, this angle determines the naming scheme for all of this, which can be a bit confusing sometimes. The adjacent is the side between this angle and the 90-degree one. The opposite is the side opposing the angle. Finally, the hypotenuse is the side that is actually angled from this, angle. Sometimes you do see people use the other angle, which flips the names around. Do be careful about that. For our purposes, I will always stick to this naming scheme. The most important thing to understand for all of this is that the angles in a triangle determines the ratio of the sides. If this angle is 30 degrees, then the hypotenuse will always be twice as long as the opposite. If the opposite is 10 units long and we have 30 degrees, then the hypotenuse will always be 20 units. If we double the size of the rectangle, so the opposite grows to 20 units. At the same angle, the hypotenuse is now going to grow to 40 units. It always needs to be twice as long as the opposite. At 30 degrees, this is always going to be the ratio, regardless of the size of the triangle. As a consequence, if we know this angle and the ratio that we are getting from it, along with one of these sides, then we can calculate the other ones as well. To get that, we have three formulas. The sine value of the angle is the opposite divided by the hypotenuse. The cosinus of the angle is the adjacent divided by the hypotenuse. And finally, the tangent of the angle is the opposite divided by the adjacent. Basically, everyone remembers this by the abbreviation SOHCAHTOA. What you absolutely have to understand at this point is that sine, cosine, and tangent with their angles are just numbers. You could put all of these into a calculator and you would get a number like 0.5. And that would be the ratio between these two sides. Now you could learn the formula for all of them, but you don't have to. Any calculator or programming language has these formulas inbuilt, so you don't have to do this manually. The only thing that you have to worry about is to rearrange these formulas to get the right side. So now you might be wondering, how can we use all of this for some kind of shader and game development more broadly? The first shader I want to create is going to be an orbital system, where we have a planet in the center, and then we have something circling around it. For this system, we do know a couple of things. We have the center, and we can determine the distance from the center to this orbital thingy. Let's call it the moon. Besides that, we can determine the angle ourselves. Let's call it alpha for now. After that, we want to get to this point, for which we will need the x distance and the y distance, which would be the adjacent and the opposite. And to give them better names for game development, the adjacent would be x, the opposite would be y, and the hypotenuse would be the length. I think that is much easier to understand. We have the center, and from that, we are creating a triangle. Let's also keep on using 30 degrees for one example. The last thing that we can set is the length from the center to the moon. This one can be 20. After that, we will need x and y, or the adjacent and the opposite. Let's start with y. The formula for that is the sine value of 30 degrees. This ratio is going to be the opposite divided by the hypotenuse, which in our case is going to be y divided by 20. After you have that, you need some kind of calculator. On Windows, this would be the standard calculator, in which you want to activate the scientific mode, because then you get trigonometry with sin, cosine, and tangent, among a couple of other things. To get the sine value of 30, all you need is type in 30 and then trigonometry, sine. You get 0.5, which means all of this is simply going to be 1 over 2 equal to y over 20. To solve this one, we have to multiply both sides with 20. That will give us 1 over 2 times 20 is equal to y over 20 multiplied with 20. On the right side, the 20s both disappear. On the left side, 1/2 of 20 is simply going to be 10. Hence, y is 10. This gives us the first side. Y is 10. Next up, we need the adjacent or the x coordinate. The formula for this one is the cosine of, we are still using 30 degrees, and then we have x divided by the hypotenuse, so in our case, 20. For the cosine of 30, I want to have 30 trigonometry cosine. We can round this to 0.87. X divided by 20. If we now multiply both sides with 20, we will get x equal to, let's type this one in. I still have this value, and I want to multiply it with 20. We get 17.32, like so. And I guess this should be rounded, which means with that, we know x and y is a 17.32. And with that, we have the basics of trigonometry. For all the really basic stuff, you want to calculate the x and the y side depending on an angle, for which you can use this and this formula, which you can also reorganize. If you only care about x and y, the formula for x would be the cosine of the angle that you are looking at multiplied with the, let's call it the length. For y, we need the sine value of the angle, which we also multiply with the length. These two formulas convert a distance and an angle to an actual xy distance. And this is what we are going to use in the shader to determine the position of this point. The last thing I want to talk about is why we're getting a wave from sine and cosine. For that, imagine we have a triangle where the opposite is 0. Or in other words, in a generic triangle, the opposite, this side here, would have a length of 0. The result is a line where the hypotenuse and the adjacent are identical. Now, if you take the sine value 0, you are going to get 0. And that number should make sense because sine is giving you the relationship between the opposite and the adjacent. But if this angle is 0 and we have a flat line, then the opposite is always going to be 0, regardless of the size of the triangle. Hence, we're getting 0 here. And if we were drawing that value inside of a coordinate system, where the x-coordinate is the angle that we are working with, and on the y-axis, we get the value, let's just call it b. If we get the sine value of 0, the return value is going to be 0. Hence, we are here. Besides that, if we increase the angle to 30 degrees, this we have done before, it's going to be 0.5, which means 30 degrees is going to be 0.5. To put in the numbers, let's say we are going in increments of 15 degrees, like so. Then we would be here. Next up, if we go to 45 degrees, then the ratio would get a bit closer to 1 because this side keeps on growing while this side stays the same. I don't know the actual number. I think it's going to be around 0.7. The specifics here don't really matter. Let's say we are roughly here. Finally, the really interesting case is when we're getting a straight line, meaning the angle is 90 degrees. If that is the case, the hypotenuse and the opposite are identical. As a consequence, when we're getting 90 degrees, the ratio is going to be 1. These two sides are identical, which means on this point, we are getting a 1 up here. Connecting these points gives you a half curve. And if you then add the other side, you are doing the reverse of all of this, which basically means if you're getting 91 degrees, you are going to be ever so slightly below 1. Let's say for simplicity, 0.99. And if you go all the way to the end, 180 degrees, then you're back at a flat line. So this would be 0. The outcome is going to be that we are going down on the curve once again, something like this. And there you can see it. We have the curve. If we go to the other side of the triangle, these numbers inverse once again, which means the curve continues like so, and at some point ends back at the origin point. This works for sine and for cosine, because effectively we are looking either at the opposite or at the adjacent. And they are both affected by it in the same way. We just get an offset. Exactly the relationship between the two, this one here, which we would get via tangent, doesn't give us a curve like that. This one would look very different. But that we don't have to worry about. We only care about that we're getting a curve from sine or cosine. With the math out of the way, let's work on the orbital system. All of this we can achieve by using sine and cosine. Back inside of Godot, once again, I have a new setup where we have a node 2D with a sprite and a camera, and I already applied a material to the sprite 2D, in which we have a fragment function and nothing else. All of this is inside of a new folder with the shader and the scene. In here, we want to create an orbital system. The first thing that I want to do is to create a vector 2 UV with 2 times the standard UV minus 1.0. So we are getting a UV coordinate where the origin point is in the center. That's going to make the math quite a bit easier. Now that we have that, I want to start by doing something simple. I want to create a main circle, and this one is going to be static. Effectively, this is going to be the Earth, and in just a second, we're going to create a moon. But step by step, for this center, let's call this one the Earth. I want to have a float Earth mask, which is simply going to be the length of the UV, which we can then use for color.a. Earth mask, like so. To turn all of this into a proper circle, I want to add this step function where we have the length of the UV and then some kind of float value. Let's call it the Earth radius, which does not exist at the moment. So at the top, I want to have a uniform float Earth radius with a hint range. For this one, I went with a start value of 0.05. The maximum value can be 0.2, and we don't need a step size. Although I do want to set a default value of 0.1. Like so. And then we get a center point. What we can now do is color.rgb, and I want to mix color.rgb with some kind of other color. I guess for the Earth, we can go with a blue-ish value. We have 0 for red, 0 for green, and 1 for blue. The mix amount is then going to be the Earth mask. That will give us a blue dot. Although I guess what we should be doing to make this look a bit nicer is uniform vector 3 Earth color with source color. And this is the color I actually want to use. So replace this one. Then inside of shader parameters, we can set an Earth color with a nicer bluish value. Choose whatever you like. This part doesn't matter so much. I'm gonna go with this. With that, we have the basic setup. And I hope at this point, this kind of operation is at the very least understandable. Next up comes the important part, where I want to work on the moon. For now, I want to create a moon here, where we have a 45-degree angle along with some kind of distance. The distance we can already set dynamically. The angle later on is going to be animated, so we are going around the entire circle. But to keep things simple, I want to have a static angle, at least for now. And also let me drag out the code window a bit so you can see more. This is a bit better. Perfect. Number one, I want to have a uniform float moon distance. As always, I want to have a hint range without a step size. And for this one, I want to go from 0 to 0.5. The default value should be 0.4. And by the way, these values you can kind of set to whatever you want. Just choose something that looks good. This 0.05 isn't a requirement. It's just the smallest size that kind of makes sense. It's still really, really small. Anyway, now we have the moon distance. After we have that, I want to calculate a center point for the moon, which is going to be a float moon x and a float moon y. Let me comment out both of them so we can talk about what we have to do. Remember, this origin point at the moment is 0 and 0 for x and y. From this point, we want to go down by 45 degrees. We also have a distance, the one we have just created, this one here. And this is how far we want to go. From these two bits combined, we want to get this point. For x, that means we want to get this distance, and for y, we want to have this one here. This triangle here is a right-angled triangle that we can work with. The only difference now is that the entire thing is inverted. That happened because in this coordinate system, going down means increasing y. Not too much of a challenge to overcome. But luckily, for both of them, we can use the math formulas we have just talked about. The top side is going to be calculated with cosinus, and the bottom one will be calculated with the sine function. To get started, I want to calculate moon x, for which we have a triangle, and we want to get this side. The formula for all of this is going to be the cosinus of the angle, in our case 45, which is going to be equal to the adjacent divided by the hypotenuse, which in our case is going to be x divided by the distance, which means the formula is going to be the cosinus of 45 multiplied with the distance. That's all we have to do down here. Moon x is going to be the cosinus of the angle 45 for now, and this we want to multiply with the moon distance. This is almost going to work, there's just one problem. This line here is wrong because we cannot use 45. Sine, cosine, and tangent all work with radians, meaning a full rotation is going to be 2 times pi. Half a rotation is simply pi and 45 degrees, so this distance would be pi divided by 4. So this 45 should be pi divided by 4.0. Alternatively, you could also multiply it with 0.25. Both would work. And with that, we have the x distance to the moon. The same thing we can do pretty much for the y distance. All I have to do is copy all of this and replace cosine with sine. Once we have that, I can create a vector 2 that I'm going to call moon center, which is going to be vector 2 with moon x and moon y. With that, we know where the center of the moon is supposed to be, which means at this point, we can create a float moon mask, which is going to be very similar compared to what we have done up here. In fact, let me copy the entire thing. We still want to use the step function, but we don't want to use length anymore. Instead, I want to get the distance from the UV position to the moon center. After that, we need some kind of radius. So moon radius, and then all the way at the top, besides the Earth radius, I want to have a moon radius, which by default should be a bit smaller, let's say 0.05. Now we have to make it visible, for which I want to get color A and then add the moon mask. Like so. And now this should be visible. And there we go. we have a moon. On top of that, with the sprite 2D selected under the shader parameters, we can customize the distance. That looks pretty good. And we can change the radius. That also works pretty well. For the color, let's do it like we have done before. I want to duplicate Earth color and change it to moon color, which should be, let's go with a whitish color, something like this. And then copy the line we have done before for the Earth and do it down here. Except now we want to get color RGB, moon color, like so. And finally, we want to get the moon mask. And this is working. Perfect. All the other stuff also works just fine. So I am quite happy. Finally, to animate the whole thing, all we have to do is to not have a static angle and instead use something that can be animated. Like, for example, the time. If you add that, you get a rotation. And that is looking really, really nice. Although, before we are doing that, let me undo it and talk about the math one last time. Let me zoom in just a bit as well, like so. Fundamentally, we are working with a triangle that has a right side. This one here is 90 degrees. And using trigonometry, we can calculate the x distance and the y distance from the angle next to the center. This alpha value here is fundamentally all we need, along with the distance. All we needed were fundamentally these two lines to get the x and the y distance. From that, we could calculate the moon center, which is this point. And after we have that, we can calculate the distance from the UV values to the moon center, which would give us all of this. Finally, we added the whole thing to the alpha value. So we have both the Earth mask and the moon mask. And that is pretty much it to use basic trigonometry. Let's practice it. I want you to give the moon a smaller moon. So a smaller circle that rotates around the moon. Pause the video now and see how far you get. I want to add another section for the exercise, and I guess we can call this part a meteor around the moon. For which, first of all, I want to have the uniforms that we have used before. We will need a meteor radius, a meteor color, like so. And finally, I want to have a meteor distance. We can fine tune all of these values later on. For now, I just want to have something. After that, for the moon, we did the x and the y point separately, but we don't really have to. We can simply do a vector to meteor center and then create a vector 2 for it right away. Although, first of all, let me comment out the entire thing so I can talk about it. Fundamentally, I want to get this center point and then create another triangle that gets us a point vaguely here. And this one should then rotate around the moon, which means we want to get the moon center and then add some kind of x-y distance to it. For that, the x distance is going to be moon center dot x plus, and then we basically have to do what we have done up here. Let me copy it. I want to get the cosine of, for now, 45 degrees multiplied with a meteor distance. The same thing I want to do for the y part, like so. The rest can stay the same, although this should be the sine value. Don't forget the semicolons here, then Godot should be happy. And also, what can be a bit confusing, if you have a comma at the end here, Godot is going to complain. This one shouldn't be there. With that, we have the meteor center. Basically, the same thing that we have done here. So next up, we have to create a mask for the meteor. For the meteor, down here, I want to have a meteor mask, for which we want to get the distance from the UV coordinates to the meteor center. We also want to have the meteor radius. And finally, we can get color.a plus equal the meteor mask. And this should then finally be visible. If you zoom out, there you can see it. We definitely have to update the distances, but this should be workable. The meteor distance should be much smaller, and the entire thing, so the meteor radius, should be something like this. That is much better. Finally, for the color, I want to duplicate all of this, and then I want to get the meteor color along with the meteor mask. Then the color updates, this looks good. And now we have to give this thing some kind of color. Let's make it, I don't know, let's go with a slight reddish color, whatever you fancy. I want to make this just a tiny bit smaller, and that looks good. Cool. With that, the last thing that we have to do is to change the static angle to something dynamic. For the moon itself, I want to simply use time. Time in here, then this thing should animate, and that looks really, really good. For the meteor, so these two angles, I want to have time times, let's say 2. And then we should get a really nice orbital animation. And that is working really, really well. If you want to change this value, all you have to do is to make this value negative. And then we're going the other way, which I think looks a bit better, but play around. And all right, with that, we have created an orbital system via a shader and trigonometry. For the next shader, I want to add a line over a texture. I call this one a shine effect. The name isn't perfect, but I think you get the idea. For this kind of thing, we have to talk about line math and how to express lines using numbers. The most important concept in here is going to be the slope intercept. This is simply a formula that looks like this. X and Y are the points that we want to get. M is the slope, and B would be an offset. Via this formula, you can express a line quite easily. For example, imagine we have a coordinate system and we get actual values for M and B. M could be 2 and B could be 1. And then we basically go down the X numbers, so 1, 2, 3, 4, and so on, and plot in the values. If X is a 1, Y is simply going to be 2 times 1 plus 1, which would be up here, 1, 2, and 3. And for a second point, let's do the origin. That one would be 2 times 0 plus 1, so we are getting 1. We would be here. This line is always going to be linear. As a consequence, we can connect these 2 points like so, and this would be the line that we have expressed via this formula. That's all that we are doing in here. It's fundamentally a pretty simple formula, and we can make it even simpler. Since we always want to go through the center, we can drop the b. So we only care about y equals a slope times the x values. And for the shader, what we want to do is to rewrite this thing a tiny bit to get y minus slope times x. That way, for every single pixel, we can check if the pixel is on the line, so we're getting 0. If the value is positive, then the point is above the line. And if the value is negative, then we have a point under the line. And that, I think, is already quite a bit of stuff, so let's play around with it. Back inside of Godot, I have a new project called Shine with a sprite2d and a camera. The sprite2d has a shader called shine.gdshade, in which we have a fragment shader that doesn't contain any logic. All of that is inside of a new folder that should actually be called Shine, like so. In there, we have the shader and the scene, nothing special. To get started, I want to create a vector 2 with the adjusted UV values. 2 times UV minus 1. After that, I want to create a basic line, for which I want to create a float. Let's call this one line. And on there, I want to get UV dot y minus the slope times uv dot x. That is the formula I just talked about. Via that, we can check if a point is above, on, or below a line. The only thing that we have to do is to define a slope, which we can do via a uniform float slope. Let's set a hint range from 0 to 1, and this should be working. We just have to make it visible, which we can do via color.rgb. I want to have a vector free with the line. And with that, we are getting something. And if I go to the shader parameters, I can also rotate this thing at least a tiny bit. This should be a range from -1 to 1. That way we can go left and right to a degree. And to really understand this, as always, you want to insert a couple of points and do the math. By default, this slope is 0, which means we are basically getting uv minus 0 times x, which means all of this simply disappears and we're getting the uv.y values, which looks pretty good since this is the origin point 0, all this stuff is black, and this is a gradient that ends at 1. So far, so good. But now, if I change this value to, let's say, a -1, we want to be in the origin point, meaning uv.y is 0 and uv.x is 0. The slope is going to be -1. The end result here is simply going to be 0. For this point, we're getting a black color. That part is a bit boring, but next up, I want to get this point and this point. The first one has an x position of 0.5 and 0 for y. The second one has 0 for x and 0.5 for y. That way we know that they are on a diagonal line, meaning they should have the same value. To plot that into the formula, the slope is always going to be -1. For the first one, this one here, we are doing uvy is 0, -1, and uvx is going to be 0.5. This is going to be 0 minus -0.5. So the end result is going to be 0.5. This -5 is what we're getting from this operation. And if you do minus a negative value, you are doing the opposite. So you are adding stuff. This would be the first color value. For this point here, we get an RGB value of 0.5. For the second one, the point down here, uv.y is 0.5. And from that, we subtract -1 times 0, which is a very easy calculation. All of this simply disappears because we are multiplying it with 0. As a consequence, the end result is going to be 0.5. These 2 points have the same RGB value. Both get 0.5. If you sample the point in the middle with 0.25 and 0.25, you would also get the same value. And if you went a bit further down, let's say here-ish, you would get a slightly higher value. The really important thing is that at this slope, when you are sampling a single line, you are going to get the same RGB value. That is what we're getting from this formula. Cool. With that, we can express a line that we have to refine, because this slope I want to get from an angle. Later on, I want to define a uniform float angle without a hint range, but the default value should be 0.0. And this should be float. This angle I want to convert to a slope. And for that, we need to use trigonometry. We will need the tan function. The basic idea is, inside of a triangle, the tan function gives us the ratio of the opposite divided by the adjacent. And this part might sound really simple, but the tan function is already giving us the slope. Because fundamentally, all that the slope really is some kind of ratio that's telling us how much higher we want to go, depending on how far left or right we are going. So the change on the y-axis relative to the x-axis. And that is literally what we are getting here. Which means to turn this angle into a slope, I first of all want to comment out the slope and then create a float slope in here. To get this value, I simply want to get the tan of the angle. And then the code doesn't crash anymore. And if I change the angle, we can rotate this thing quite a bit. We can already make refinements by, for example, putting line into absolute and then subtracting all of this from 1. That way you are getting much closer to something that looks kind of like a line, but it's still not perfect. The really important thing that we need is some kind of formula that measures the distance from the line to all of these points. The formula for the line distance is going to look a bit weird. It's this one. The top part, this bit here, is simply another way to express a line, where we basically have a slope for x and a slope for y, along with an offset. From that, we are taking the absolute value and then dividing it by all of this. The square root of the squares of the two slopes. That formula we have to adapt to our purposes because we are using a different way to express a line. In our case, the entire thing is going to look like this. The top part is the formula that you have already seen. This is what we are using to express a line. From that, we can take the absolute value and then we are dividing it by the square root of the two slopes. The first slope is easy. We simply have this one and then we are getting this one. This one here we are getting because technically this y is 1 times y. It doesn't matter for this part, but down here, it is really important. But other than that, this is all we need to get the distance from the line for every single fragment. Let's implement it. Back inside of Godot, I want to, for now, comment out this RGB line and instead create another float. Let's call it distance to line. I want to get the absolute value of what we have done for the line. Since we already have the line, you can simply add it in there and then divide the entire thing by the square root of 1.0 plus the square of the slope. So slope times slope. Don't forget the semicolon. And now we are getting the distance to the line for every single fragment. If I now uncomment all of this and then use vector 3 distance to line without the 1 minus, we're getting a proper line. And this one we can rotate without changing the width. That looks really good. To turn this thing into a nicer line, we can add a uniform float thickness with a default value of 0.01. And after that, I want to create a float shine mask where we are using the step function with the distance to the line and the thickness. Once we have that, I can use vector 3 with the shine mask, and now we are getting a much nicer line that we can customize however we like. To retain the original colors, I can cut out this part and then use the mix function. We want to get color.rgb, then some other color. Let's for now go with vector 3 1.0. And finally, I want to have the shine mask. That way, we are mixing the color wherever we have this shine mask. All the other stuff still works perfectly fine, so I can move this line around and it looks pretty good. The last thing that we have to do is to animate the entire thing, which means I want to move this line left, right, up, or down. This part is going to be your exercise. I want you to move the line. As a tip for this one, try to think about the UV positions. Other than that, pause the video now and see how far you get. The main thing that you have to change is this number. But step by step. Number 1, I want to create a uniform vector 2, let's call it center, with a default value of vector 2 1.0. If I set this center to this 1.0, like so, then by default, nothing is going to change because this vector 2 is the same value that we already had. But now, what I can do via these two numbers is to move the entire thing, and that looks quite nice. I can also move it up and down. That also works. Right now, this looks the same because the angle is diagonal, but if I move it like so, we can see it much better going up and down. Although now, moving it left and right doesn't really do anything. So you do want to be careful, but this still works really, really well. And with that, we pretty much have the entire shader. You could animate it via a tween. I think that part at this point is fairly trivial, so I'm going to finish it here. Time for chapter 4. I call this one the world coordinates. So far, we only use shaders within the local space of a texture, which can create nice effects, but is quite limited. To expand that, we will learn about how to get the global position of vertices and fragments. This information is vital to create things like grass shaders or customized light effects. While doing this, we will also learn about matrix math, which sounds fancy and complicated, but is actually quite doable, at least when it comes to the fundamentals. Although, before we get to any of this, we need to look into vertex shaders quite a bit more. For which, here we are back in Godot, and I have the usual setup. The sprite 2D is what we care about. This one already has a shader, although without any content. The entire scene is inside of a new folder setup, where we have 4 world coordinates with 1 vertex, in which we are working at the moment. And basically now, we want to do a recap and a bit more detail on vertex shaders. Inside of the vertex shader, we don't really work with all of the individual pixels or fragments. Instead, we are working, at least in the sprite 2D, with the 4 corner points. These 4. Their information we can target via the vertex property, which, by the way, we also have available inside of the fragment shader. But in there, it means something different. I'll talk about that in a second. For now, just ignore it. Instead, inside of the vertex shader, we can update all of the vertices, for example, by adding a value to it, let's say a vector 2 with 50 and 0. That way, we are moving these 4 points 50 pixels to the right. Important to note here, inside of a vertex shader, we are working with actual pixel distances. Or in other words, this distance here is actual 50 pixels. Inside of the fragment shader, we basically always worked with a range from 0 to 1, which inside of the vertex shader is much less common. In there, you can use actual pixel positions. I suppose while we are here, we can also read the vertex position. So for example, what we could be doing is I want to increase vertex.x by vertex.y. And this should be plus equal. That way, the further down we go, the more stuff we're adding to the right. But now you might be wondering, by how much are we moving the pixels? So for example, how much has this pixel moved from this position here? When we are talking about these vertex positions, we are talking about a coordinate system like we have done before. This one has the center around the origin, so this is 0 and 0 for x and y. After that, the actual corners are defined by the size of the texture. That information you can get from hovering over the icon.svg. There you can see this thing is 128 by 128 pixels, which means the entire thing is 128 by 128 pixels. And since the origin point is right in the center, the bottom right point has to be 64 by 64 pixels. The top left, this one here, would be negative 64 and negative 64. As a consequence, when we are doing this kind of operation, we are moving the bottom right vertex by 64 pixels to the right, whereas the top left one, this one here, is going to be moved by negative 64 pixels. And since we only work with the corner vertices, we basically only change this point and this point. No matter what kind of math we are doing in here, we are always going to get some kind of straight line. If you want to have more control, let me go a bit to the right and then add two more objects. The one that you probably want to use the most if you just want to have more vertices is the mesh instance 2D. If you add this one, you can add a mesh, which for our purposes is always going to be a plain mesh. And to that, you can also add a texture, which should be, in my case, a texture 2D. If you have that, let me hide the original sprite 2D, then we get a straight line. To actually make something visible, you want to click on the mesh, and then, if you worked with 3D objects before, this should look familiar. We can create a mesh in here. Although at the moment, it's facing the wrong way, which we can address by changing the orientation. We want to face not X, but Z. Then you can see something, although this image at the moment is very, very small. To account for that, the size should be 128 by 128. That way, we get the original size of the Godot logo. You can basically treat this size as the pixel size, with one difference. The Y value has to be inverted. So this should be negative 128. The reason for that is in 2D, Y is pointing down, whereas in 3D, it's pointing up. If you want to combine the two, one of them has to be inverted. Once we have that, we can apply the same shader inside of material. And do be careful here. You could apply a material inside of canvas item and inside of the mesh itself. There's also material. This material, at least for our purposes, you don't want to use. You want to go, like we have always done, to canvas item material, and then a new shader material. And I want to get the shader that we have been using already, the Vertex GD shader. Apply this one, and then we get the same result. Both of these shaders get the exact same logic. But now, if I want to add not vertex.y, but the sin value of vertex.y multiplied with 10. And all of this, to make it more visible, we want to multiply with, let's say, 40. This at the moment is giving us simply another slant. But what we can do now, inside of the mesh instance 2D, if I click on the mesh, we can add more subdivision to it. And if I increase both of these to, let's say, 100 and 100, then you can see we're getting a very different result. Because of these two parameters, we don't just work with the 4 corners. Instead, we get a lot of points in between that we can customize. If you really want to distort some kind of 2D image, a mesh instance 2D is your best bet. Besides that, for a third part, you can also add a polygon 2D, in which you can add a texture, which in my case is going to be the Godot logo, like so. And this right now you cannot see. To actually make something visible inside of a polygon 2D, you have to use these points at the top to tell Godot which part of the texture you want to show. For example, if I have create point selected, I can click on a whole bunch of points and then show only the inner part of the Godot logo. Every single one of these points would be a vertex inside of the shader. Which means to this polygon 2D, let me move it over here. I can, inside of material, add a shader material and then apply the same vertex shader. Like so. And then we're getting something kind of interesting. Because these points are so customized, we do get a bit of a weird result. We're going to work with polygon 2Ds in the next part in a bit more detail. For now, I guess don't worry too much about it. Anyway, with that, we have the 3 main 2D objects that you can apply a vertex shader to. After we have that, we have to talk about a couple of minor parts for Vertex Shader that are becoming quite important, for which I want to comment out this part. So we are back to the default texture. When you're working with the vertex property, you have to be careful because it means different things inside of the vertex and the fragment shader. In fact, we can display the entire thing by using the color property. Inside of the fragment shader, I want to get color.rgb and assign a vector 3, where we are getting vertex.x, vertex.y, and 0 for the blue values. If we're doing that, we are getting a yellow color. If you get a yellow color inside of a shader, it's a shorthand for these two values having a value greater than 1 by quite a bit. We'll fix that in just a second. But before we get to that, I want to create a varying, let's call this one the vertex varying, which has to be a vector 2. I want to use this value to assign, so vertex varying, the vertex value from the vertex shader. And if we now use this vertex varying for the color inside of the fragment shader, we are getting 4 different colors. Hence, we are getting different things. What happened here? This vertex we have already talked about. The origin is in the center, and then in the bottom right, you would get, for example, 64 by 64, or whatever is half of the width and height of the original texture. When you are assigning this information to a varying and pass it to a fragment, Godot is keeping the information mostly, but it also adds linear interpolation. As a consequence, if we only look at the x values along this line here, the center would be 0, the right side would be 64, and the left side would be negative 64, at least for the Godot logo. If you have a texture with a different size, these numbers would be different. You always get half of the texture size. What is really important now is that we are getting a linear scale, meaning we go from 0 to 1 to 2 to 3 to 4, all the way to 64, which we can make more visible by dividing both of these values by 64, like so. Then we're getting a gradient. That still is 1 and 1 in the bottom right. And if I add color.a being 1, then you can see this a bit better. The bottom right is a pure yellow color. The really important thing you have to understand at this point is that inside of the vertex shader, the vertex property refers to these 4 points that all have distinct pixel positions. However, inside of the fragment shader, via the varying, Godot is converting these 4 points into a linear scale. That way we can get a gradient for all of these points. I think this part can be quite confusing when you're getting started. Besides that, let me comment this part out. If we get color.rgb and assigning a vector 3 with the vertex.x directly along with vertex.y and 0. Now we target vertex right away, but we're getting a yellow color. What happened here? To understand this one, when we are working inside of a fragment shader, the vertex does not refer to these corner points. That is not what's happening. Instead, this vertex position refers to the position of the fragment on the screen. And to really demonstrate how this is working, inside of a shader, we can get this screen pixel size, which is a vector 2 on which we can get x and y. So I want to get screen pixel size.x, and then for vertex.y, screen pixel size.y. To understand this value, if you have a screen resolution of 1920 by 1080, then screen pixel size.x would be 1 divided by 1920. That way you know exactly how large a single pixel is. And inside of the Godot editor, our current screen pixel size is defined by this area. whatever you see inside of the viewport. So if I simply toggle the full screen view, you can already see this graphic changing. You can see it even more if I hide the shader editor. Since the viewport size changes, the screen pixel size also changes. But we always have in the top left the point 0 and 0, so the origin, and in the bottom right, we have the maximum value. So down here, we will get the value of 1 and 1 for the color. In the bottom left, we get a pure green color. In the top right, a pure red one. Because up here, for example, we only have the red values, or values on the x-axis. Later on, we will use this information for a couple of interesting effects, but for now, I kind of want to ignore it. We simply don't need it for this part. With that, we are nearly done. There's just one more important topic that I do want to cover, and that is that inside of a Vertex shader, you can also target color. Although, once again, color inside of a Vertex shader is not the same color that you would have inside of a Fragment shader, although this is still a vector 4. But let's just assign a value to it. I want to give it a red color, so 1.0, then 0 for green, and 0 for blue. For the alpha value, I want to have 1.0. With that, we are tinting the Godot logo red, which is the same thing that you would get if you went to visibility, modulate, and if you make this value a pure red, so no green or blue, then you get the same thing. Effectively, this color modulates the texture. And this you could use with other things as well, like for example uv.x. Then you would get a more interesting modulate effect. Also note here, if you overwrite the color, then modulate is not going to work anymore. If I change this to anything else, the shader is going to overwrite it. The same applies to self-modulate. This one also doesn't do anything anymore. And with that, we have done a bit more of a deep dive into Vertex shaders. For the next shader, we will animate the Japanese flag. While doing that, we will also learn about polygon 2Ds in quite a bit more detail. Here we are in Godot, and I have kind of the usual setup. We have a node 2D, then we have a polygon 2D along with a camera. The polygon 2D already has a shader that at the moment has the vertex and the fragment function, but nothing else. Before we can get to that, inside of the polygon 2D, we have to assign the texture. Oh, and by the way, all of this is inside of the folder 2 flag. I want to, inside of the polygon 2D, go to texture and then assign icon.svg, like so. Then, inside of the polygon editor, we have to, via creating polygons, draw points around this thing that we want to select. Just select a whole bunch of points, like so. Do make sure that the entire thing is closed, and then you are going to see something like this, on which you could also modify the points. I guess I want to move this one around. Also, really make sure that these points are outside of the logo, so you get these repeated border pixels. That at the moment is intended. But basically now, we have a whole bunch of points that we can move around, and if you move them inwards, you are changing the logo, which I don't want to do yet. Before we get to that, via the shader, I want to remove these repeating border pixels. The way to achieve that is actually quite simple. We still have the UV coordinate system that starts in the origin point, so this is position 0 for x and y, and in the bottom right of the original texture, we have position 1, meaning all of the pixels that we actually want to see, all of these, are within a range of 0 to 1 for both x and y. All of the pixels that we want to get rid of, all of these, they are either greater than 1 or smaller than 0. And these we have to get rid of via a fragment shader. Let me do one side. I want to do color.a and multiply equal it with step uv.x and 1.0. With that, we are removing the stuff on the right side. As a reminder, the first argument is the edge, and the second one is the value, usually called x. If x is greater than the edge, the step function is going to return a 1. If it is smaller, then we are returning a 0. uv.x on the left side of the logo is going to be 0. If we are on the right side, this line, then we are 1. And if we are exceeding it, then we get to a value greater than 1. Let's say, for an example, 1.2, which means inside of the step function, we get 1.2 is greater than 1. As a consequence, we are returning 0. This one here. For all of these fragments, we are multiplying then the color A value with 0. So nothing is going to be visible. For the left side, we want to multiply the entire thing with step 0 and uv.x once again. Then we're getting rid of the left side. Notice here, I have flipped the arguments around. For the first step function, we want to check if uv.x is greater than 1. For the second one, this one here, we want to check if uv.x is smaller than 0. So two slightly different operations. The same thing we can repeat for the vertical pixels. I simply want to duplicate all of this and then get uv.y for both of them, like so, and then we are done. That's pretty much it. And this kind of line you always want to have when you're working with a polygon 2D. Without that, you're going to struggle with these repeated border pixels, which basically always look horrendous. So this shader on its own should already be useful. But now, I want to animate this logo. And for that, I want to target the vertex property. Let's start with vertex.y. I want to add the sign value of time, and to see it a bit better, let's multiply it with 20. And with that, we have the Godot logo moving up and down. But that's not the proper flag behavior. Most importantly for now, I want to mostly move it on the right side and keep the left side static, which we can achieve by multiplying all of this with uv.x. That way, the left side gets a value of 0 for this one, and the right side a value of 1, which is already looking quite a bit more like a flag. But now you might be wondering, we have loads of points, but it looks like we are only moving the corners. What we can do to overcome that is, number 1, get uv.x, and from that, I want to subtract the time. And for all of this, I want to get multiply with some kind of frequency, let's say 5. And now we get a much nicer result. Let me zoom out. We have a much more flaggy kind of looking thing, which we can also control a bit better by adding some kind of speed property. Let's say I want to have this thing animate twice as fast. I can just add multiply with 2 to the time. You could also add a plus equal here. Just feels a bit nicer. And to get proper naming into the entire thing, I want to get a couple of uniforms. Uniform float speed. This should be 2.0. I want to duplicate this because next up, we're going to get a frequency y, a default value of 4 here, and then I want to have also for y the amplitude, for which I want to get 40 as the default value. And then for the vertex shader, I want to multiply the time with the speed. The frequency is going to be this value, and for amplitude y, we want to replace the 20. And with that, inside of the shader parameters, we can change these values and then get a different kind of effect for our flag. You can make it quite crazy, so do be careful here. To finish all of this, let's do an exercise. I want you to finish the flag, which is going to involve 3 parts. Number 1, animate vertex.x, give it an incline, and add the colors. Pause the video now and see how far you get. To get started, I want to duplicate these 2 uniforms because I also want to have a frequency and amplitude for the vertex x property. After we have that, I can duplicate this entire line and update vertex.x. Simply by having that, we are going to get a different kind of animation, but this does not look good. To fix that, I used the cosine and then used uv.y. And for this one, you do want to add minus. That is looking a tiny bit better. Also, to fine tune this, I want to get frequency x along with amplitude x. Now, this is definitely too strong. So for amplitude x, let's go with 20. Actually, 10 might be a bit better. Just play around and see what you like. Besides that, I want to get vertex.x once again, and then subtract uv.y multiplied for now, let's say with 40. And then we are getting the incline, which should be a uniform. So uniform float incline is going to be 40. And this we want to use down here, incline. Don't forget the semicolons, that's always important. And I guess what we should rather be doing for this one is to add a hint range from 0 to 1, with the default value being a 1. And besides that, I want to have a float max incline. And for this one, we are setting a value of 40. After that, I want to get the incline and multiply it with the max incline. That makes it a bit easier inside of the shader parameters to animate the thing. Let's keep it at something like this. That looks reasonably okay. And that is going to be a nice flag-ish animation. We just have to add the colors, for which I want to work inside of the fragment shader. You can do it before or after the color A property, doesn't really matter. First of all, I want to get color and assign it a vector 4 with 1.0. Then we're getting a white color and also sharp corners, because now we are removing the alpha values of the original texture. After that, I want to get a float center mask, which is going to be a step distance with the UV position and a vector 2 with 0.5. For the x value in the step function, I want to have 0.2. That way, we're getting a center mask, which is going to be a circle that I want to use via color.rgb. With the mix function, I want to get either the current RGB value or a red color. Vector 3 with 1.0, 0, and 0. And then the center mask. And with that, we should be getting a red circle, and we do. And that would then be a nice flag kind of effect. You just have to fine tune it a tiny bit, but I guess that you can do on your own. So for example, the incline could be a bit more. Amplitude X, I guess I want to lower a bit. While amplitude Y could be a good bit greater. Actually, let's make it lower. There we go. This looks a bit better, I think. Just play around and see what you like. But this is the basic idea of how you would work with a Polygon 2D and the Vertex shader. To properly use Vertex shaders to their full extent, we have to cover another topic, and that is matrix math. This one sounds really cool and complex, but the basics at least are pretty simple. Matrix math is just a way to do lots of simple calculations at the same time. And when I say simple, I really do mean simple. When we do matrix math, we do operations like 2 plus 3 times 4. That's pretty much it. The only slightly more complex part would be something like cosine and sine, but we have already covered them, and we're not going to use them too much. Let's do an example. Matrix math might look like this, where we are multiplying a matrix 2 with a vector 2. Matrix 2, by the way, because we have a 2 by 2 grid, 2 rows and 2 columns. And before we do anything, it's really important to mention that the order of operation matters. You always want to start with a matrix and then with a vector. Doing the operation the other way around is going to give you different results. But other than that, fundamentally what we're going to do is multiply the vector with each row of the matrix. We first multiply the 5 with the 1 and then the 6 with the 3. The result is going to be added together. And then we do the same thing for the second row, so 5 times 2 and 6 times 4. As a consequence, all of this would look like so. The end result will be 23 and 34. This would be a very basic matrix operation. And like I said before, this kind of math is pretty simple. We just have a lot of it. But now you might be wondering, how is any of this useful? Well, imagine you have the Godot logo or any kind of texture and you want to rotate it. Which effectively means for any fragment, you want to add some kind of position to it, where you go in the x direction by a certain amount and then by the y direction. Getting these 2 points via trigonometry would be possible, but it would already be quite a bit of math. If you also wanted to move the texture to the right and scale it down, then you wouldn't just have to do this operation. From this point, you would also have to go to the right by some amount, and then to account for the scale, you would have to go down here. So 3 operations that you have to do together. Once again, you can do that without matrix math, but matrix math makes it a lot easier. Fundamentally, matrices are just tables that we mesh together. And they simplify the math a lot, which is why they are useful. So, let's talk about matrices in shaders. And what I want to do for now is use a matrix 2 to move the vertex position of a shader 50 pixels to the right. The answer to that would look like this. And to understand why this is working, we have to cover a few more fundamentals. The most important part is the identity matrix. For matrix 2, this one would look like this, and for matrix 3, it would be this one. The point of this matrix is that it changes nothing. If we, for example, multiply the identity matrix with a vector 5 and 6, the operation would look like so, and the end result is still going to be 5 and 6. Since we always multiply this one with this one, and this one with this one, the 0 here makes sure that the second one disappears, at least for the first row. For the second row, we would multiply the 5 with a 0, so the 5 disappears because of the 0. Now that we have that, we can add stuff to the identity matrix so that we don't get the original. Instead, we get something slightly different depending on what we want. For that, if we want to move a texture 50 pixels to the right, and to make it a bit more understandable, for x and y, I have added actual values. If we now do all of the math, we are going to get this. The first row is the only thing that you really want to look at. That's the important part for now. We get the original x position. This 10 we want to keep. The 20 we want to ignore, which we are doing by having a 0 for the second part. But then, finally, this 50 we want to add to the 10, which we're now doing by 1 times 50 plus what we have already done. So the point of this entire line is that we are doing 10 plus 50. Once again, there are a lot of numbers, but nothing here is complicated. You just have to understand the basic principle. Once you get that, the rest is pretty simple because we are not doing anything new. So the rest is going to look like this, and the end result is going to be 60, 20, and 1. The 1 at the end we are simply going to ignore. What we care about is the vertex position with 60 and 20. Effectively, to the original vector, we have added 50 pixels, so we are going to the right. And that was quite a bit of theory. Let's work on Godot. Here we are, inside of a new scene in a new folder called Free Matrix Basics. We have a scene with a sprite 2D and a shader. For this part, we only need the vertex function. And let's say I want to create a uniform float x of z, which is just going to get a value of 50 for now. And this I want to use to offset the texture and move it to the right, or whatever this value is, which you're going to do via a matrix. And we're going to need a matrix 3, which I want to call a translation matrix. To create it, we want to get a matrix 3, and then we need 3 vectors, 1 for each column. So if I add 1, 0, and 0, and this has to be a vector 3, which I guess I can copy twice, like so. Then I want to change this to 0 and 1, and 0, 0, and 1. Also, don't forget the semicolon. Then we have a matrix. Each of these vector 3s is 1 column. If this is the entire matrix 3, the first vector 3 would be this column, the second one would be the middle one, and the final one would be the one on the right. Can sometimes be a bit confusing because it feels like these should be a row, but they are not. We are always creating a matrix via columns. And this at the moment is an identity matrix, so it shouldn't do anything. To test all of this, let me create a vector 3 result, for which I want to get the translation matrix and multiply it with a vector 3, where we are getting the vertex positions, and then 1 for the remaining part. I suppose you might be wondering, why do we need a vector 3? Wouldn't we just apply a translation matrix to the vertex right away? The answer is we couldn't. When we are working with an identity matrix, at least for now, these original 4 points are really important to keep the original values. All of the stuff we are doing here does not change the original. These points, at least for now, we don't want to change. As a consequence, to add additional numbers in here, we have to expand the matrix. This is why we need a matrix 3 instead of a matrix 2. And you can only multiply matrices with the vectors of the same order. So if you want to multiply a matrix 3 with a vector, you need to have a vector 3. Because of that, we have to convert the vertex information into a vector 3. With that, I can get the vertex position and assign it result.xy. The result should be no change, and that looks good. Oh, and by the way, if you multiply a matrix with a vector, the return value is going to be a vector as well. Finally, we want to actually implement this x offset, for which we want to get the top right value, which is this one here. In there, we want to add the x offset. If we're doing that, you can see it right away. We are moving the Godot logo 50 pixels to the right. And inside of material and the shader parameters, we can change this value super easily. With that, we can move the logo left and right. I guess this value could just be called X. Feels a bit nicer. Make sure you are using that down here as well, like so. And I guess while we're here, we could also add a Y uniform, which we have to implement here. With that, we can move the texture around however we want. This could also be negative. Let's say negative 100. Looks good. And that is a translation matrix, the easiest one to understand. Although this so far really is not impressive. However, besides the translation matrix, we have two more. The first one is a scale matrix. This one looks like this. We don't keep a 1 for the translation. Instead, we change it to the scale. For a quick example, let's multiply this thing with a vector 3 that has 5, 6, and 1. And the scale is going to be 2. If we now do the first line, we do 5 times 2 plus loads of zeros. Anything we do for these two numbers is going to be 0 because we are multiplying it with 0. As a consequence, the end result here is going to be 10. We have multiplied this 5 with a 2. Besides that, we have a rotation matrix. This one does get a bit more complex. It looks like this. Don't worry, we are not going to do too much trigonometry in this part. Now, the really useful part of matrices is that you can combine them. So we could be doing scale times translation times rotation times the actual vector 3. That way we combine all of these operations on a single line. To demonstrate, back inside of the shader, I want to have a uniform scale. This should be a float, and it should just be a number. Let's go with 2. After that, I want to create another matrix 3, the scale matrix. Mat3 once again, with a vector 3 that is going to get the scale 0 and 0. This would be the first column. This we want to copy and paste 2 times, like so. And also don't forget the semicolon. After that, for the final one, I want to have 0, 0, and scale. And for the middle one, I want to have 0, scale, and 0. Let me also clean up the white space a tiny bit. This looks good. With that, we have a scale matrix, which we could use right away. Scale matrix times the vertex, and then inside of the properties, we can scale this thing super easily. And what is even better, we can do translation matrix times the scale matrix, and then apply both at the same time. I suppose let me add 0 here for everything, so we get the original. And now I can scale the thing. I can move it left or right. I can move it up or down, all at the same time. And I hope at this point, matrices start to look a bit more useful. Although for the really useful one, we want to get matrix 3 rotation matrix. That one is going to be your exercise. Create and implement the rotation matrix. As a reminder, the formula for it looks like this. Pause the video now and see how far you get. I want to create a matrix 3 with 3 vector 3s. And besides that, I also want to have a uniform float angle, which is going to get a hint range from 0 to 1. To use this angle for the first column, we will need the cosinus of the angle. Then we need the negative sine value of that angle. And the last value is going to be a 0. And let me do all of this over multiple lines, so it's at least a bit more readable. For the second column, we want to get the sine value of the angle, and then we will need the cosine of the angle. The final one is going to be 0. Finally, for the last column, this one is a bit easier, 0, 0, 1. It does start to get a bit more complex, but I think this is still fairly usable. After we have that, I want to get the rotation matrix and multiply it with the other two matrices. Once we have that, I have an angle and I can rotate the logo by a certain amount. For the full rotation, we need to go from 0 to tau, or 2 times pi, which we can also do right inside of the matrix. I want to multiply the angle with tau. Now I can get a full rotation. All the other stuff also works. I can still scale. I can move the positions. And this looks really nice. And with that, we have matrices. A super useful concept because now we can apply a ton of math fairly easily. For the next shader, we are going to use matrices for a fake 3D effect. What you see on the screen right now is a sprite 2D that is being rotated around the X, Y, and Z axis separately, which you can do fairly easily using a matrix. Or in other words, we have a rotation around the X axis, the Y axis, and the one that we have already seen, the Z axis. Combining all three of them is giving you a fake 3D effect. And before we jump into Godot, I have to clarify a thing. When I talked about rotation matrices in the last part, we only talked about one kind of rotation, the one around the Z axis. Besides that, we have two more, a rotation around the X axis and the Y axis. We are still using trigonometry, except now we are adding different numbers. You could look up the specific formulas on why this is working, but I don't think it matters that much. What matters, however, is that you can still combine all of this. So you could do something like this, where you get the X rotation, the Y rotation, the Z rotation, all of which are matrices, and that you multiply with a vector 3. And all of this is going to be your exercise right away. Create a shader that uses the 3 rotation matrices. Pause the video now and see how far you get. Inside of Godot, I have the usual setup, a node 2D, a sprite 2D, and a camera 2D. For the sprite 2D, we already have a shader with a vertex function. All of this is inside of a new folder for fake 3D. Number 1, I am going to need a couple of uniforms. Uniform, load, let's call it rotation X. And this is going to be a hint range from 0 to 1, at least for now, with a default value of 0. I want to duplicate that 2 times because we also want to have rotation Y and rotation Z. Once we have that, inside of the vertex function, we can create the 3D rotation matrices. There are 3 that we need. The first one is going to be a matrix 3. Let's call it rotation X matrix. We will need a matrix 3 with 3 vector 3s. The first column is going to be 1.0, 0, and 0. The second one is a vector 3 with 0, the cosine of rotation X, and finally, the sine value of rotation X. And I think all of this should be done over multiple lines, so it's at least somewhat readable. We need a third vector 3, for which I want to get 0, the negative sine value of rotation X, and finally, the cosinus of rotation X. And with that, we have our first matrix rotation for the X-axis, which we can use right away. I want to create, first of all, another matrix 3 that I called the rotation matrix, for which at the moment we only have the rotation X matrix. And I guess this should rather be called the roto X matrix, just feels a bit nicer. Later on, we're going to multiply this with the Y and Z matrix as well, but for now, we're going to keep it as it is. After we have that, we can update the vertex positions, for which we want to assign basically the roto matrix multiplied with a vector 3 for the vertex positions and 1.0. Although this is currently assigning a vector 3 to a vector 2. To only get the xy values, I want to use parentheses and then dot xy. With that, I can go to the shader parameters and change rotation x. We are getting something. Effectively, what we're doing now is we are rotating around the x-axis. Although we do have the issue, like we had in the last part, that we only get a partial rotation. That is because the full rotation goes from 0 to 2 times pi, and we only go to 1, meaning we only get about a sixth of the full rotation. To account for that, we want to multiply all of these values with tau. You could multiply it in there right away, or you can do before the matrix if float full x rotation and then get rotation x multiplied with tau. And this is the value we actually want to use. The full x rotation for all 4 of these values. Then I can do a full rotation. And let me zoom out a tiny bit and expand the code window so you can see a bit better what's going on. Basically, the only really complicated part is this part here with the cosine and sine values. If you practice this a bit, it should be fairly doable. The most important thing to understand is that each vector is a column. Other than that, you just have to work through it step by step, and then you're done. Besides that, we need a rotation for y and z. And before we are doing that, I also want to get the full y rotation and the full z rotation, which we can get with rotation y times tau and rot z times tau. After that, let me copy in the other 2 matrices so you don't have to watch me type for too long. There we go. Now we have also the roto y matrix and the roto z matrix, all of which we can collapse for just a bit more space. That way, all of this is more readable. And once we have that, we can multiply the 3 matrices together. I want to get roto x matrix times roto y matrix and roto z matrix. Once we have that, inside of the shader parameters, we can still use x, that looks good. We can also use y, that also looks good. And we can get z, that also looks good. And now, if you combine the 3, let me set them to the default. Let's say if I use x and then a tiny bit of z, you can now see that this looks very much like a 3D effect, even though we only work inside of a sprite 2D. If you want to create any kind of card game, this kind of effect is going to be super useful. And this effect we can make even more interesting, because at the moment, we always pivot around this center point. But we could also add a bit more math to pivot, for example, around this point, or this point, or this point, or really any of these points. It's actually pretty easy. To rotate around a pivot point, you need to understand one vital concept called translate, rotate, translate. Basically, you first want to get a pivot point and subtract that from the current vertex position. That is going to give you new points, and these new points you want to rotate. After you have done that, you want to add the pivot point back to the new points. With that logic, you always rotate around the pivot point. That's pretty much it. It's 3 lines of code at the most. Let me add another section where we are going to add a pivot point. And before we're doing that, we need another uniform, which is going to be a vector 2 called pivot. After we have that, I want to create a new vector 3. Let's just call it v. For that, we are going to get a vector 3 with the vertex positions and 1. This one doesn't really matter. We're just going to keep it because in a second, this point we're going to multiply with the roto matrix. But for now, all we want to do is to subtract a vector 3 with the pivot vector 2 and also 1.0. And just to demonstrate what this is doing for now, let me comment out the last vertex operation and assign a new value with vertex being v dot xy. At the moment, this pivot is simply giving us an offset with x and y. If I change these values, we're going left and right or up and down. Doesn't do very much. But what we can now do is to assign the roto matrix times the vertex. That way, we're getting back our rotation. And if I still move stuff, we can move around. And this also makes the rotation super wonky, which might be what you want, but we have to update this thing just a tiny bit more. We want to get the new points, so v plus equal the vector 3 with the pivot and 1.0. And then we are done. Let me set all of the points to a default value and also make all of this just a tiny bit larger, like so. By default, if I change rotation y, we are rotating around the y-axis. But if I now set the pivot point to 64, and really important, for this pivot, we are working in actual pixel positions. If you want to be on the right side of this texture, you have to get 128 by 2. If you work with a different texture, this number is also going to be different. If I now rotate y again, we are rotating around the right side of this texture. All the other rotations should also still work, and they do. With that, you can do some really funky stuff. You could also set this to 64 by 64, like so, and then rotate like so. You are pretty much creating a really convincing fake 3D effect. Now that we have covered the basics of vertices and matrix math, we can start working on world-based shaders, meaning we actually look at the position of a fragment inside of the world coordinates, which lets us create a whole bunch of super interesting effects. To get started with all of that, we have to talk about spaces. Inside of a shader, we are operating in multiple. For example, the vertex position could get a position that is relative to the center of the sprite 2D, basically what we have always done so far. But it could also be the distance from the origin point of the world. And to understand all of this a bit better, let's do it more visually. Here we have a texture with a shader. And we want to look at this point. So far, we have worked in the local space, meaning we go from the center to this point. For the Godot logo, this would be -64 and -64. Basically half the size of the texture. Besides that, we also have the world space. This coordinate system is the actual world coordinate. Inside of Godot, it would be this point, the actual origin of the entire project. Or in other words, vector 2, 0, and 0. And if we go from this point to this vertex, we would get a coordinate like 40 and 20. This would be a different way to think about the position of the vertex. Besides that, we also have a canvas space. This purple outline is the viewport or the window of your game. And in the top left, we have the origin, from which we can once again go to this point. This time we will get a vector of 20 and 200, so this distance. The canvas space we have actually already used. When you use the vertex property inside of a fragment shader, you get the fragment position inside of the canvas space, meaning the position is relative to the screen. Understanding these three spaces is incredibly important. For now, we are going to focus on the world space, and the local space we already have, which means we have to talk about converting this space. To go from the local to any other space, you have to multiply the vertex attribute with inbuilt matrices. There are two that we care about at the moment, the model matrix and the canvas matrix. Both of those are matrix 4, meaning we have 4 rows and columns. Both of these are only available inside of the vertex shader. If you want to go from the local to the world space, you would need this, where you get the current vertex position inside of a vector 4. Meaning we have to add 2 additional numbers in here. In case you're wondering, these 2 numbers are important. It should always be a 0 and a 1. The specific reason doesn't matter, just make sure you are adding them. Besides that, the really important part is that you are multiplying all of this with the model matrix. You get that from the vertex shader. This converts the local position to the world position. This was quite a bit of theory. Let's work on Godot. Here we are, inside of a new scene. I have the usual setup with a bit of extra stuff. This animated sprite 2D for now contains a character, and inside of the folder 5 model matrix, we have a few more graphics. For now, just ignore them entirely. We're going to use them in a bit. Much more importantly, we have a sprite 2D in which we have a shader called model matrix, which doesn't do anything at the moment, but we do have a vertex and a fragment shader. I want to get the vertex. This is currently in the local space, meaning this point in the top left is -64 and -64 for x and y. This I want to convert to the world space. We are going to need some kind of variable to store the data, for which I'm going to use a varying. That way, we can move stuff from the vertex to the fragment shader. I want to create a vector 2 called world position. After we have that, inside of the vertex shader, I want to get the world position and assign it model matrix multiplied with a vector 4, in which we are getting the vertex position, 0 and 1, and all of this is going to return a vector 4, but we only care about the xy position, so parentheses and then dot xy. That is all we needed to get the world position. So what can we do with that? And I think the best way to get started is color.rgb. I want to get a vector 3 with the world position and then 0 for the blue values. With that, we are getting the thing that we have already seen. In case this looks familiar, this is the same thing that we have gotten when we assigned simply the vertex position, like so, as a varying, and then added it to the fragment shader. And just to be clear here, this vertex position is inside of the local space. However, this line is returning the world position. The reason these 2 values are identical at the moment is because we are in the origin point. The origin point of the world is here, and this is also the center of the sprite 2D. So for this specific situation, the world position and the local position are identical. But that doesn't have to be the case. To demonstrate the difference, if I move this sprite 2D with the vertex local position, it is not going to change. We are always going to get the same color. However, if I comment out this one and re-enable the other one, then the colors are going to change. So you can see it quite well if I zoom out. If we're in the bottom right, we get pure yellow. In the bottom left, green, then black, and red for the other sides. The reason we are getting yellow now is because we are going from the origin point to these 4 vertices, since all of them are on the positive x and positive y axis, meaning we always get a value greater than 1 for red and green, hence the yellow color. If we go to the left, then we still have positive y values, but the x values are negative, meaning those will become 0, hence we only have a green color. And with that, we can tell where we are inside of the world from the point of view of the shader. I hope so far all of that made sense. Just to go over it one more time. For the local position, so this line here, we are going from the center to these vertices. We have 4 in total. These ones here. And these points are only relative to the center, meaning this point will always be -64 and -64, regardless of where this thing is. However, for the world space, this line here, we start from the origin point and then we go to the 4 vertices. This one here, and finally this one. Because of that, the position of the entire texture will become super relevant. I think a good idea to practice all of this is to create an actual usable project. Meaning I don't want to get the color anymore. Let me comment this one out. And then I want to create some kind of circle. Let's say something like this. If the texture is inside of the circle, it should be hidden. If it is not, it should be visible. This could be an exercise. I want you to create a circle. The center should be at position 100 and 150 in the world coordinates. And then, if the texture is inside of the circle, hide the fragments. The end result should look like this. Pause the video now and see how far you get. I want to have 2 uniforms. Uniform, vector 2, circle, center. This is going to be a vector 2 with, I think I said, 100 and 150. After that, I want to have a uniform float radius with 200. Both of these are inside of the world coordinates. I think if I implement it, you will understand it quite a bit better. I want to get inside of the fragment shader a float distance. Via this, we want to get the distance from the world position to the center of the circle, which is what we have defined up here, circle center. If I now set color.a to this distance, then nothing is going to happen because this distance is basically always going to be greater than 1. However, what I can do is to use this step function with the distance and then the radius that we have used earlier. Now, if I move this thing around, you can see it, we have the actual circle. If I go around the points, you can see it much better. If we are inside of it, you can see the texture. If we go outside of it, we can't see it anymore. Although this should be the other way around. So we can do 1 minus this, and then we do the opposite. Now, the texture disappears once we get into this circle. And this only works because we have the world position of the vertices. Besides that, what you can also do, I want to add a uniform sampler to the, I call this one the space texture, which I also want to repeat. So repeat enable. Once we have that, inside of the shader parameters, we get the space texture, which I'm getting from the folder. There we have space.jpg. Just drag this one in there. The entire thing looks like this. And basically what I want to do, let me put it in the background. I want to use the Godot logo to cut out from this texture, but the texture itself should not move. The only thing that I want to move is the Godot logo. I don't want to do this part anymore. Let me get rid of it. And instead, I want to get a vector 4 with the space color, for which we want to get the texture. We want to get this space texture that we have used earlier, this one up here. And then we need a UV coordinate. So far, we have always used UV. And this equal sign shouldn't be there. Now this is working. If I now assign color to the space color like so, we're getting the space color inside of the logo. And if I move the texture, this one doesn't change because we are once again working inside of the local coordinate system. However, what I can do now, instead of getting the UV coordinates, I can get the world position. If I do that, then this thing is going to become very, very small. But if I zoom in, I hope you can see that we have a whole bunch of small space textures. To get the right size, I want to multiply this with the texture pixel size. And then we get a much better result. That is already looking a bit different and really important now. If I move the texture, you can see that we don't move the background anymore. Instead, we are only cutting out a different part of it, which we could scale up quite a bit more by multiplying it with 0.01. That way, if I now move around, this might have still been quite a bit too small. Let's go with 0.1. Now we have the space background, and we are cutting out parts from it. I think if I hide the space background, you can see better. Now we are getting a mask that we can move around. Looks quite nice. You do want to be careful that this texture repeats properly. Right now, I have this hard cutoff, but that's because of the original graphic. This one just doesn't tile very well, but that's not really that much of an issue. Everything else still works pretty well. This you can also control by adding a uniform float amount, which is going to get a hint range from 0 to 1. This amount I then want to use inside of the color, where I want to mix color.rgb with the space color and the amount. Also, we only want to update color.rg and b, which means for the space color, we also need the RGB values. Now we get the Godot logo back, but if you look at the inspector, there we can change this thing quite a bit. If it's set to 1, then we get the space texture once again. And with that, we have the world position that we can use for the alpha values and the color, along with a whole bunch of other properties. And to actually get a nice result, I want to work in the animated sprite 2D. This one at the moment looks like this. To that, I want to add the material, so new shader material, and the shader we just created, model matrix, for which we have to add the space texture, so space texture, and then we can make this thing look really spacey. If I move it around and zoom out just a bit, you can see that we get this spacey outline, which we can make look even better by adding a background, for which we have ground.png. Just drag it in there below the animated sprite 2D, like so. And then the camera should be on the animated sprite 2D. And looking at this, I realized the animated sprite 2D should be transform scaled up by a factor of 4. That way the pixel art lines up. And now if you are inside of this world, you could use a tween to make the main character look like they are doing some kind of special effect where we are exploring space. Something like this. You just have to move the character around. The animations are still going to work just fine. To the animated sprite 2D, I want to add a script. All the defaults here are fine. And I want to get func_process, in which, most importantly, I want to get a direction. The direction is just going to be UI left, UI right, UI up, and UI down, which I can then use to update the position. And I want to add the direction multiplied with, let's say, 100 and delta. If I now run the entire thing, we get some weird behavior. I think the reason for that is because the animated sprite 2D and the camera 2D are not in the same position. The camera is down here, the animated sprite is up here. So inside of the camera transform, position should be 0. With that, we get an actual result, and there you can see it a lot better. This is a pretty nice effect. For the animations, to get the most basic example, I want to copy in a constant dictionary. These are vector to integers with, for example, left, and then we get the left animation. If you look at the animated sprite, we have down, left, right, and up, which I want to target via this dictionary. I want to, number 1, check if we have a direction, and then play the direction animations, for which we're going to need some kind of vector to integer. which we can get by rounding direction.x and round direction.y. And if we don't have a direction, else the frame should simply be 0, like so. With that, we are getting an animation that at the moment is a little bit hard to see. Also, the camera should, I think, zoom out just a tiny bit. So camera 2D, the zoom level should be, let's go with 3. And the animated sprite 2D for the amount, I want to have 0 to get started. Now we get a very basic movement animation. Doesn't do very much. And after we have that, we can check if input is action just pressed with UI accept. If that is the case, we want to create a tween via create tween. And this tween is going to target the amount. Then we want to tween property for the current material, in which we are getting the shader parameter along with the amount. The target value is going to be 1.0 over a duration of 2 seconds. Inside of the game, I can walk up here, and let's say there's an important quest bit starting here. Then I can press enter, and the player starts to space out. Looks pretty cool, I think. Time for the next chapter. This time, we will use canvas coordinates. In other words, we will take information from the screen itself. This chapter will also cover how to combine multiple shaders, which lets you add some truly weird stuff. Although, before we get to any of that, we have to cover the basics of canvas shaders. Here we are in Godot, and I have a new folder, 5 canvas coordinates, and in there we have 1 canvas intro, which does have a bit more stuff. Don't worry about any of this. Also, when you look at the actual scene, we have a whole game, which I'm going to cover in just a second. It looks like this. We're going to use that to create a shader like this in just a second. However, before that, I want to work inside of the demo scene to cover the absolute basics. In here, we have a background that's just a sprite 2D, and on top of that, we have an icon. And this icon is going to get the shader. So material, new shader material, and then new shader. This is going to be called Canvas Intro Demo. And in here, we are going to talk about canvas coordinates. Let me rearrange things just a bit. Also, let me move the icon somewhere here so I can talk about it in a bit more detail. So far, we talked about 2 kinds of coordinate systems. Inside of this shader, we have the local coordinate system that goes from the center of the sprite to the different vertices. So we have the various corners, and we get basically this space. Besides that, we have the world coordinates, which start in the origin point. So here we have 0 and 0. And then we can go in any direction and look at the pixel coordinates. For this chapter, we will look at a different space, and that is the canvas space, which looks at the screen itself. So at the moment, this green thing is going to be what we are looking at, which also has the origin point in the top left. This point is still 0 and 0. And from there, we go to the bottom right. This point could either be, in my case, 1920 by 1080, or whatever your window resolution is, or it could be 1 and 1, if you work with UV coordinates. And this value we have gotten before, inside of a fragment shader. If you get the vertex property, you get the position of a fragment inside of the screen space, which means I can do color.rgb and then assign it a vector 3 with the vertex for red and green, and blue gets 0. That way, right now, we're getting a yellow color. And if I move it around, this thing is always pure yellow. That is happening at the moment because this viewport this area here, is the window that the vertex is sampling from. The top left is still 0 and 0, and the bottom right is going to be our resolution. So if this thing is, let's say, 3000 by 1000 pixels, then this point would be 3000 and 1000. And since these values are basically always greater than 1, the values for red and green are permanently maxed out. To get something more interesting, we could multiply this with the screen pixel size. That way, we are turning the coordinate from pixels into basically UV coordinates, where the top left, this point here, is 0 and 0, so there we're getting a black color, and in the bottom right, we're getting 1 and 1. So down here, we are back to yellow. In the top right, we're getting red, and in the bottom left, we're getting green. If I am, let's say, in the bottom right of the window, and I run the project, in this bottom color, we now have a pure yellow color. And instead of getting the viewport for our screen coordinates, we are now getting this window. With that, you can get the pixel position on the screen, or you can basically get the UV coordinates. Could also get the screen UV right away. This effectively would give you the same result. So once again, in the bottom right, we have a pure yellow color. And if I move this thing around on the screen, you can see we get pure red in the top right, green in the bottom left, and black in the top left. For some reason, inside of screen coordinates, there are multiple ways to get the same information. Let me go through all of them. The most elaborate way to get the screen coordinates is to create a varying vector to, let's call it the screen position. We need a varying because inside of the vertex shader, we can get the screen position and assign it the canvas matrix multiplied with the model matrix, which we then want to multiply with a vector for vertex 0 and 1. All of this should be in parentheses because we only care about x and y. So far, we have done this operation to get the world space coordinates. If you multiply the entire thing with the canvas matrix, you are turning the world position into the canvas position. And by the way, the order here is super important. You always want to go first the canvas matrix, then the model matrix, and finally the vector. Once you have that, inside of the fragment shader, you can get the screen position, and now we are back to pure yellow. Meaning for both x and y, we are getting a value much greater than 1 that we can work with later. If I multiply this with the screen pixel size, we are once again back to UV coordinates. With that, you can get, both inside of the vertex and the fragment shader, the pixel coordinates inside of the canvas space. Besides that, what I've already covered, you can get color.rgb, vector free, vertex times screen pixel size with 0 once again, same information, and finally, you could also do color.rgb with a vector free and a screen UV. And once again, no change, we can still do the very same thing. And there's actually one more approach. With color.rgb, you can assign a vector free with reg coordinate, which is a vector 4, and the xy property, after which you want to have 0 for blue, is giving you the screen position once again. So this, once again, if we multiply it with the screen pixel size, is giving us the same thing. The frag coordinates do have more bits of information, but those don't really matter for our purposes. People use these 4 approaches kind of interchangeably. Now, there are minor differences between these approaches, but at least in 2D and for our purposes, those don't really matter. But with that, we can get the current position of a pixel inside of the canvas space. And that's the only part that really matters. Let me add a comment. This is going to be the canvas space position. Another important part for canvas shaders is how to get the entire screen. So basically, I want to get anything that is behind this texture on the screen. And that you can get via, we have to go up first, inside of a uniform. We want to create a sampler 2D, and let's call it screen texture. We have to add a hint, screen texture. That way Godot is automatically filling this sampler 2D with anything happening on the screen. Or in other words, and let me comment out all of this, just to focus on one thing, I want to get the color and assign it texture with the screen texture and the screen UV. Once I add the semicolon, look at the Godot logo. It is going to disappear. Because now, every pixel color is exactly the color that we get behind this logo. And I think a better way to show that is to only work with the RGB values. Then we still get the same color, because the alpha values for all of this are going to be 1 anyway. But now, if I do 1 minus the value here, then we are inverting the colors. And now, we can go around, and we are getting the background pixel color, and we are inverting it. Let's place it here so it's a bit easier to see. A super cool effect. And with that, we have the absolute basics that you have to know about canvas shaders, where you get a position and the screen texture. This gives you anything on the screen that happens up to this node. In fact, I can hide this one and make the game part reappear. There you can see it a bit better. Now, anything that's happened inside of this node is going to be picked up by this screen texture, and then we are inverting the entire thing. And that way, we can work with all of this pretty well. But not something I want to do yet. These are the parts you absolutely want to be aware of. Once we have that, we can work inside of the game part. Let me go over it really quickly. Inside of the game scene, we have water, which is a tile map layer, and we have ground, which is just the grass. After that, we have a player with an animation and a camera 2D. The script inside of the player is something that we have already used a couple of times. We have the animation dictionary, then we are capturing basic input, we are moving around. If we are moving around, we are playing the animation, and if we don't move around, we're going to frame 0. And besides that, we have a whole bunch of trees. Those don't really do anything. And to run this scene, you want to go to Camera 2D and enable the camera. And with that, we can walk around on the island. Works pretty well. And to that, I want to add a shader, for which I want to add a canvas layer. All the way at the end, that way we are ignoring the camera. And to that, I want to add a color rectangle, which is going to get the shader. So in here, material, shader material, and I want to get a new shader. Canvas intro is fine. Basically now, I want to draw a circle around the player that turns all of this into a black and white image. I want to get a uniform sampler 2D with the screen texture. Don't forget, you do need hint screen texture. That one is super important. With that, we get all of the textures that have been drawn before this shader. And since we now, via the canvas shader, ideally cover the entire screen, so make sure you go to the anchors and select this one. Now we covered the entire window. If I run the game, we can't see anything. That's intended. But what we can do now, inside of the fragment shader, we can assign the color of this thing, and I only care about color.rgb. We can get texture with the screen texture and the screen UV, on which we want to get the RGB values. And then, back inside of the game, we have the stuff that we had before. Looks good. But now, all of this is rendered on a shader. So this value, we could change as much as we want. Like we have done before, this could, for example, be 1 minus the texture. Then we are inverting every single fragment. Can be a spooky effect, although not what I want to do. If you want to make everything grayscale, the way you would approach it is, let me create a vector-free grayscale, and this is going to be a vector-free, where we are getting the screen texture like so, but then we only look at one color, like for example, red, and that value we can then use for the RGB value, like so. Now everything is in grayscale. This could also be, besides red, we have green and we have blue. Blue is the color I have used inside of the demo, but play around and see what you prefer. This grayscale we only want to apply in a circle around the player. To get that, we will need a float distance, which is going to be the distance between a vector to 0.5 and the screen UV. 0.5 here is used because the player is always in the center. Since the camera is looking at the player, like so, the player has to be in the center. We can mix the screen color, which we should get first of all. So I want to have a vector for screen color, which will be the texture with the screen texture and the screen UV. You generally want to get this one first of all. After we have that, the grayscale we can get from this value. And finally, inside of mix, we can get screen color dot RGB, then the grayscale, and then some kind of ratio. If I set this to 0.1, we're making everything just a bit more gray. But this value should be set via the distance. So distance now. And then we are getting kind of a vignette effect. If I run the whole project, you can see that this is doing something. To get sharper corners, we want to use the step function, where we get the distance and then let's say 0.25. With that, we get a clear cutout. But the issue now is that we don't have a circle. We have an ellipse. And this we have to account for. And this, by the way, happens because the screen is not a square. So we have to account for the aspect ratio, which we have done before inside of the project, shader projects. And there we had transition. This is the shader you want to look at, where we first of all want to get a ratio and then apply the ratio to get a better UV coordinate system. In our case, since we always work with the screen, we can simply look at, and let me delete the other stuff. This is getting a bit crowded. We don't need a vertex shader for any of this, and I want to have a bit more space. We will need, most importantly, a float ratio. This is going to be the screen pixel size dot y divided by the screen pixel size dot x. This we can use to create a vector to, let's call it a square UV via a vector 2, where we are mixing 0.5 with screen UV dot x and the ratio that we have just defined. After that, we will need screen UV dot y, and then we are done. If I now use the square UV instead of the screen UV, we are getting a perfect circle. And this is much better. And to finish this part, I want to pixelate this circle, which is going to be an exercise for you. Here's the end result. This kind of operation we have already done a couple of times. Pause the video now and see how far you get. To get a pixelation effect, we need an updated UV, which is going to be a vector 2 pixel UV. We want to get the square UV and multiply it with some kind of pixel size value, which I guess should be a uniform load pixel size. And I went with 95. This I want to use here and then get the floor value of the result. And the entire thing, I want to divide by the pixel size once again. After we have that, we have to use the pixel UV down here. And then we are getting a pixelation effect, which you could also customize. So inside of the shader parameters, this value you could change as much as you like. If you set it to 10, you get really large pixels. If you set it to, let's say, 200, you get very small ones. I'm going to stick with 95. It just looked good. And with that, we have the basics of a canvas shader. In this part, we are going to use the canvas data to create a reflection effect, very similar to the old Pokemon games. While we are doing that, we are also going to learn about a really important node called back buffer copy. But step by step. Number one, we have a problem for the reflection. And that is that we want to check for a mask on the canvas. But this mask should not be visible. This is what we want to show in the game. But for the shader to work, we need to have a mask like this. And this mask we want to read via the canvas information. So we have to figure out some kind of system to read the mask, but not have it visible. This we can do via back buffer copy. This is a node that controls when we are getting the screen texture. Let's have a look. Back inside of Godot, I have a new scene called Reflection, in which we have a game part. Don't worry about this part for now, I'll talk about it in a second. But more importantly, we have a demo scene, in which we have a background. We have seen this one before. Then we have 3 sprite 2Ds that I have colored via visibility and modulate. None of these have any shader or any kind of material, so material is empty for all 3 of them. There you can see it, we're not using a shader so far. But on top of all of this, we have an overlay shader, in which we have the file buffer demo that at the moment gets the screen texture, and then by the screen UV copies anything that comes before it. So via this overlay shader, we're getting all of this information, whatever is visible. I think so far this part is reasonably straightforward. But what I now want to do is to add a back buffer copy, which on its own doesn't do anything. Although in there, you can set a copy mode to rectangle, viewport, or disabled. I want to go with viewport. And then this is still not doing anything. But if I now move the back buffer copy between the green and the blue sprite 2D, then the green node is going to disappear. This happened because when we're getting the screen texture inside of the overlay node, by default, we are getting all of the stuff that comes before it. But if we have a back buffer copy, then the screen texture looks at this point and tries to find all the stuff that came before it. Since we are drawing the green sprite after that, this green texture does not pick it up. So inside of the actual game, it will not be visible. That way you can use the screen texture without having something visible inside of the actual game. And that's all that back buffer copy really does. It's fundamentally a simple node. If you move back buffer copy between blue and red, you can't see either the blue or the green one. And if you move it one step further, then you can't see the red sprite anymore. And if you move it here, you can't see anything because there's nothing visible behind the back buffer copy. Let's move it here just for demo purposes. But this is not what we want to use. So let me hide the entire thing and instead talk about the game scene. In here, I can run the whole project. We have a player character that can move around, and we have a tile set below. So far, this is pretty simple. Inside of this game scene, we have the visible layer that covers the grass and the water. Then we have a mask layer. This one adds the mask on top. So basically, inside of Photoshop, I changed all of the water pixels to a pure red color. And the pixels between the water and the land, I have colored in a pure green color. That way, these pixels are super easy to identify. Besides that, inside of the player, which is a node 2D, we have an animated sprite and a camera 2D. And in the script attached to this node, we have the usual stuff, a dictionary with the animations. Then we're getting the direction, updating the position. If we have a direction, we are playing the animation. And if we don't have a direction, we are going to an idle state. So far, so good, I think. Now we have to work with this scene to get a proper reflection. And to get started with that, the animated sprite 2D needs to be copied because this thing needs to be upside down and below the player, here-ish. Let me copy it. I want to have the animated sprite 2D and move it outside of the player. Let's also rename it. This should be called reflection. Although it should be a child of the game scene, that looks much better. This reflection animated sprite 2D, I want to move with the player, but it should be below the player and flipped around the x-axis. Inside of the reflection, you can go to offset and then flip V. That way, the entire thing is upside down. After that, I want to have it below the player and move along with the player. So we want to control it from the player node right away. And Godot has a node for that kind of purpose. It is called a remote transform 2D. So this remote transform 2D is a node 2D that at the moment is going to move along with the player. But inside of this node, you can assign a remote path that is also going to be influenced. And this node can be anywhere in the scene. So in my case, I want this to be the reflection. And this you want to drag into the remote path. If you're doing that, you are moving the thing around. And that happens at the moment because the animated sprite 2D is not in the origin. It should be here. That way, this looks more predictable. Inside of remote transform, we can go to transform and move this thing down. Let's say vaguely like this. I guess 30 pixels exactly would be a good number. If I now run the project, we are getting two animations on top of each other, and the two move together because of this remote transform. It's a super handy node. Besides that, we have to fix the animation for this reflection, which is pretty easy. Inside of the player script, we basically want to play the same animation for this reflection node. All we have to do for that is to get the reflection node and then run the same script for it, like so. And the entire thing we want to do here as well. Dot frame is equal to 0. With that, inside of the project, we are getting a reflection effect. Now we have to use a shader on the reflection to make sure it's only visible when we are on top of a red or a green pixel. And for that, we want to apply a shader to the reflection. I want to go to Material, create a new shader material, and in there, New Shader. The defaults here are totally fine. And in there, we don't need a Vertex shader, and we also don't need the light shader. We only want to work inside of the Fragment shader, and I also want to get the screen texture. Let me copy it in. I want to have a uniform sampler 2D, screen texture, within screen texture, and don't forget the semicolon. With that, inside of this reflected sprite 2D, we can see what is on the screen. So what we can do is color.rgb will be texture with the screen texture and the screen UV. .rgb, and that way we are hiding the entire thing. The sprite is going to be identical to the stuff behind it. Good start, but not exactly what we want to do. Instead, I want to use the mask to make it visible. But for that, I only want to get the mask layer, which means I want to have the mask layer behind the visible layer and then add a back buffer copy between the two. Like so. With that system, when we are going from the reflection shader, the screen texture is now going to look at all of the stuff behind it and finds the back buffer copy. So it only looks at the stuff behind there, in which we only have the mask layer. So this is what we're getting inside of the screen texture now. And you can see it right away. The reflection is going to look different. And fundamentally what I want to do now is to get a vector-free, let's call it this screen color. And this is simply going to be what we have done here. I do want to use it multiple times. After we have the screen color, I want to create a float water alpha or water A. which is going to be a float of screen color being equal to a vector 3 with 1, 0, and 0, which is going to return a Boolean, which we're then turning into a 0 or 1 via the float. So water A is going to be 1 if we have the mask, and otherwise it's going to be 0, which we can then use via color.a and multiply it with water A. This at the moment is not doing anything. If I run the project, we don't get a reflection. That happened because inside of the backbuffer copy, the copy mode should be set to viewport. And now, this is looking much better. We are getting a proper reflection below the player. So effectively, just to go over it again, this green texture is going to look at anything behind the backbuffer copy, which at the moment is the mask layer, with red and green pixels along with other stuff, but those bits we don't care about. After that, we are checking if any of these pixels is pure red, which we're then multiplying with the alpha, so this sprite is only visible when we have this red thing behind it. With that, we have the effect. We just have to fine-tune it a tiny bit. This part is going to be your exercise. I want you to refine the reflection shader with two things. Number one, add another reflection for the coast pixels. Those are the green ones in the mask. They should look like the water reflection, except have a lower transparency. Besides that, tint the reflected image with a blue color. The end result is going to look like this. Pause the video now and see how far you get. I want to get a float, let's call it coast A, for which we want to get a float that converts the Boolean for screen color is equal to vector 3 with 0, 1, and 0. So pure green color. And this should be called coast A. And to see what we are getting, let me copy it in and run the whole project. Now we only get a reflection on these coastal pixels, because we are only looking at the green pixels, all of those. And to use all of that, I have gotten water A, multiplied it with 0.5, and then added coast A, multiplied with 0.3. That way, we are adding the two together, and that looks pretty okay, I think. Besides that, I want to add another uniform vector 3. Let's just call it color, and this should be a source color. I went with 0, 1, A2, E0. And this I want to mix with the actual image that we can see, all of this, for which we want to get color.rgb and mix color.rgb with the color that we are getting by some amount. Let's say 0.2, and then the entire thing is much more blue, which I think looks much better. But play around. I think this could still be refined a bit, but other than that, this is the basic effect. At this point, we have created a lot of shaders, but we only ever created a single one. This would change in this part, where we are going to combine multiple shaders, which lets you create some pretty funky stuff. But don't worry, in the next part, we're going to apply this system to create something more useful. But for now, we have to learn about a new node called Subviewport. This one lets you combine multiple nodes and display the output as a single texture. This is useful because you can insert multiple shaders in there. Here we are in Godot, and I have a new scene called Subviewport. This is inside of 6 Subviewport, in which we have nothing else. And for now, I want to add a simple sprite 2D with the Godot logo, like so. This we have done multiple times by now. But besides that, I also want to add a Subviewport node. And this on the surface doesn't really do anything. I can zoom out, nothing has changed. This Subviewport can have a couple of children, and those are going to be stored inside of this viewport. And the output we can then treat like a texture. To demonstrate, I want to get the sprite 2D again. Let me zoom in. And attach the sprite 2D as a child of the subviewport. Then it's going to disappear, and that is expected. After that, I want to create another sprite 2D. And for this one, I want to go to Texture, click on the arrow, and then add a viewport texture. Now Godot wants to know what kind of subviewport I want to use. We only have a single one. And if you add this one, then you are getting something. Now you might be wondering, why do we get this result? Let me explain. When you're getting a subviewport, you are effectively creating a new texture that has this size, at the moment 512 by 512. And this texture starts in the top left in the origin point. So this subviewport would cover roughly this area with 512 and 512 pixels, or whatever you define in here. And the original Godot sprite, this one here, was in the origin. So this point here, and as a consequence, the bit that we see was this bottom right corner. After that, when we assigned the subviewport to the sprite 2D, this new sprite 2D has the origin point still in the center here. And since the viewport became the texture of it, we have created this new texture like so. We basically moved the entire thing top left. The basic thing that you have to understand is that a subviewport always covers the parts in the bottom right of the coordinate system, where we have positive x and positive y values. If you wanted to see the entire sprite 2D, you could go to Offset and then disable Centered. Now we can see the entire thing. And that fundamentally is a viewport. You create a new texture that could have any size, and then this new texture you assign to any kind of node 2D that can accept a texture. Could be a sprite 2D, could be a mesh instance 2D, could also be some kind of 3D object. This system is really flexible. And where it becomes even better is that you can add shaders to both of these sprites. Let's start with the inner one. In here, I want to go to Material, New Shader Material, and then create a new shader. Let's call it Subviewport _ inner. And in here, I want to do something super simple, where we are using the Fragment function to set the color.rgb value to a red color. So vector 3 with 1, 0, and 0. This so far worked as expected. But now, in the sprite 2D, where we are getting the subviewport, we can also assign a material, and this is going to be shader material, new shader, subviewport _ outer. And for this one, I also want to work only with the fragment function. And in here, let's say color.a is going to be uv.x. And there you can see that we are getting both a red color and the alpha value from both of these shaders. And to make this effect even better, let me add another sprite 2D to the viewport. I want to have another sprite 2D with the Godot logo. This one for offset should not be centered. So once again, this is the top left point here, in the top left of the Godot logo. And this I want to move to the right and down. And since I know that icon SVG is 128 by 128 pixels, I can use transform and insert 128 by 128. Now we're getting two objects that are both affected by the shader inside of this sprite 2D. The subviewport outer shader is affecting both of these textures. A bit hard to see right now because we are only covering the top left part of the texture. I guess what we could be doing inside of the viewport, the size should be 256 by 256. That way, we are covering the entire available space. And there you can see it. If I now do, for example, 1 minus UVX, this thing works in both directions. We get an outer and an inner shader. Super useful. And with that, we have a way to combine multiple shaders. So let's recreate what I've shown in the beginning. Number 1, inside of the fragment function, I want to have a float diagonal position. This is going to be uv.x plus uv dot y. That way, we're getting a diagonal line. I suppose to demonstrate, I want to get color.rgb and assign it a vector 3 with the diagonal position. This is what we're getting, and from this thing, I want to get a clean line. For which, first of all, I want to get a float, let's call it pattern, in which I want to get the fract of the diagonal position multiplied by some kind of line count. Let's go with 20 for now. Don't forget the semicolon, like so. And then, if I use the pattern, you can see we are getting a ton of lines. This 20 should be a uniform, meaning I want to have a uniform float line count, which is going to get a hint range. We want to go from, let's say, 1 to 50 with a default value of 20. This we can use down here, like so. Then we can animate this inside of the Sprite2D, shader parameters. Looks pretty good. Besides that, I also want to have a vector 3. This is later going to become a rainbow color. Let's just call it rainbow. For now, this value is going to be a vector 3 with 1, 0, and 0. So we get a red color. And besides that, I want to have a float is underscore line, where we are turning, let me comment this out, where we are turning these gradients into distinct values. This you could do via a step function like we have done before. Alternatively, what you could also do is to check the pattern, the one that we have gotten here, and then compare it against some float that I'm going to call line width. This is going to be another uniform line width that can go from 0 to 1, like so, and the default value is going to be 0.5. The entire thing should be a float, so Godot is happy. There we go. And after we have that, instead of using a vector 3 for the color, we can mix the original color.rgb with the rainbow color, and the value is going to be is line. With that, we can determine the line width, and this looks pretty good. Super neat effect. However, I only want to have these lines when we have a texture in here. So these lines here should not be around. And that happens at the moment because inside of Subviewport, we have a background. Or in other words, inside of the outer shader. If I set color.rgb to a vector 3 with 1, 0, and 0, then we are filling up the entire texture. So this entire viewport is going to be filled. If you don't want that and retain the original alpha values, then inside of Subviewport, you want to enable transparent background. And with that, you get the original alpha values. Much nicer, which also helps in here. Also, while we're here, inside of the inner shader, this color shouldn't be red, it should be green. That makes things a bit more visible. We're going to make the entire thing animated in just a second. But before that, I want to work on the colors. And for that, we have to figure out how to cycle through colors. So I want to go from red to green to blue and so on, and eventually go back to the beginning. To get that system working, we have to look at other ways to express color. So far, we basically always work with RGB colors, where we have a value for red, green, and blue. This system gives us lots of control, but it's hard to cycle between colors. For this particular case, we would rather want to use HSV colors, which stands for hue, saturation, and value. All we care about in here is the hue. This is the actual color. And this is a different way to express a color that is much better suited for our purposes. Now for HSV colors, we get a color circle that looks like this. And we want to get the red color, the green color, and the blue color, and then cycle them around. So we are going this way, basically, for which we have to write a function that does get a bit more complex. But let's go through it step by step. I want to create a vector 3 HSV to RGB function, which accepts one argument, the float hue. The return value is going to be some kind of vector 3. Let's go for now with 0, 0, and 1. So we are returning a blue value, and this should be return. With that, when we are getting the rainbow color, I don't want to get a plain red color. Instead, I want to get HSV to RGB and insert some kind of value. Let's for now simply go with the diagonal position. Like so. Then we're getting a blue color, so at the very least we know this is doing something. We're going to need a vector 3 that I called k, and this is going to be a vector 3 with 1.0, 2 divided by 3, and finally 1 divided by 3. We're getting the full amount, 2/3 and 1/3. This is going to be the amounts on the color wheel. We want to get 0, 120, and 240 degrees. Or back in the slides, we want to get this point, and this point, which would be 0, 120, and 240. If I return that value, we are for now going to get a pretty weird result. But don't worry, next up, we are going to implement the actual logic, for which we want to have another vector 3 that I called p, in which we want to have a vector 3 with the hue, and to that, we want to add k.xyz, or just k. If I now return that value, we're getting a pure white color, but in the top left, we're getting a slight gradient. Via this vector 3, we're getting our start amount, and via the k part, we're adding different numbers to each part of the vector. That way, if we increase hue, we are moving all 3 of them. We just have to normalize all of these values. And the way that is done is by putting all of this into parentheses and then multiply it with 6 and subtract 3.0. Via these two numbers, we are turning the entire color wheel into 6 segments. And via the -3, so half of 6, we are making the entire thing symmetrical. Don't worry, in a second, this is all going to come together. These values right now are way too large. Only in the top left do we get some proper colors. Anything after that is going to be larger than 1. So this we want to clamp. For which, first of all, from p, we want to subtract vector 3, 1.0. That way, at least in the top left, we're getting a red color. Then we're getting a yellow color, and then things become white. So all of this is still getting greater than 1. Which means we want to clamp it to a range from 0 to 1. The issue we have now is that these values max out around here, which isn't ideal. And this we want to loop, which we can do by putting all of this inside of the fract function, like so. And then we are getting a color cycle. Also, these values can become negative, which sometimes looks a bit weird. So all of this should be an absolute value. Much better. Once we have that, we can animate the entire thing down here. Before we are getting the pattern, I want to have a float, let's call it moving position, which is simply going to be the diagonal position minus time multiplied with some kind of speed. This speed should be a uniform that doesn't exist yet. Let's create it really quick. With a hint range from 0 to 1, the default can be 0.5. I suppose that's fine. And this we want to use down here, moving position. And now we get a color wheel that looks pretty neat. You can also change the speed. And that is a really nice effect. This is the kind of function you definitely want to go over a couple of times yourself. It does take a while to understand. But anyway, this is all we have to do in here. Besides that, I also want to update the line movement, for which we already have a moving position. So now, instead of using the diagonal position, we want to get the moving position. And if we then increase the speed, we get both a line movement and a color movement. And with that, if I increase the speed, we get both a line and a color movement, which looks super neat. And with that, we have covered the hard part. To finish up the shader, I want you to do an exercise, actually multiple exercises. I want you to finish both shaders, for which you want to rotate the sprite inside of the subviewport. Do this via the shader. Then pixelate the line and wobble the final texture. The end result should be what you have seen in the beginning. Pause the video now and see how far you get. I suppose the easiest part would be to pixelate the line, which we have already done multiple times. Inside of the fragment function of the outer shader, I want to have a vector to pixel underscore UV, in which we are getting the floor of UV multiplied with some kind of value. I went with 120. This could be a uniform, but in my case, it's not too important. This we want to divide by the same number, 120, and that way we're getting the pixel UV, which we now want to use for the diagonal position, like so, and then we are done. We now have pixelated values. After that, inside of the inner shader, I don't want to turn the entire thing green anymore. In fact, I don't want to use the fragment shader whatsoever. I only want to work inside of the vertex function. In here, I want to have a scale and a rotation matrix. Let me just copy them in. I want to have all of this. The scale matrix has 3 columns with the scale that scales up or down the entire thing. For the rotation matrix, we are using trigonometry for the rotation. All of this we have done before, so shouldn't be too difficult. The one additional thing that we need is a uniform float scale that is going to be a hint range between 0 and 1. Besides that, we want to have a uniform float speed, which is also going to be a hint range with 0 to 1. And these t values we are getting via a float t, which is going to be time times speed. That way, we get 2 matrices that we can control. To apply them, we want to get the vertex, multiply the scale matrix with the rotation matrix, and multiply all of this with the vector 3 of vertex and 1. This is going to return a vector 3, but we only care about the x, y values. Now we can't see this in a sprite anymore because for this one, inside of the shader parameters, the scale is set to 0. If we increase this one, that's much better. And now, if I increase the speed, we are getting a rotation, which is at the moment quite hard to see because we are rotating around the top left point. Not ideal. So for this sprite 2D, inside of a region, I do want it to be centered. Then we are rotating around the center. And to keep it visible, I want to go to transform and set a transform of 64 by 64. Then we can see the entire thing. And then for the scale, so we don't cut it off, I want to scale it down a tiny bit. That looks about all right. Besides that, we can change the speed. For now, I want it to be 0, so we don't have too much movement. That gets a bit distracting. We have a vertex shader and we have a fragment shader that both work together. And I hope at this point you do see the potential. This is a pretty cool system to combine multiple shaders. But now we have to figure out the third part. How can we add a wobbly lines effect? This we can do via a mesh instance, not a sprite 2D. So I want to get rid of this sprite 2D and instead add a mesh instance 2D, in which we can set a texture. Once again, this is going to be a viewport texture with the same viewport that right now we cannot see because we need a mesh. In 2D, you basically always want to use a quad mesh, and in there, you have to set the size. Since our viewport is 256 by 256, we should set the same size in here, 256 by 256. Although this is going to be inverted, you always want the y numbers to be the opposite, like so. And after we have that, let me reapply the shader first of all. Material, new shader material. And then I want to get the Subviewport outer shader. This so far is going to do the same thing that we have done before, although we want to customize it just a tiny bit. Something like this, I guess looks okay. There we go. What we are now able to do inside of the mesh is we can set a subdivision width and height. I went with 100 by 100. And after we have that, inside of the outer shader, we can add a void vertex function, in which we're doing something fairly simple. Vertex.x plus equal the sign value of vertex.y multiplied with 10, and the entire thing we want to multiply with 20. With that, we are getting a wobbly effect. And if you add the other shader animations to it, like the rotation, for example, you get a pretty weird outcome. I guess to animate everything, we can also re-enable all of this stuff here with the speed. That way, you can definitely see that this is coming together in a super weird way. And finally, to animate this vertex function, we can simply add time to it. And then we are getting a, well, pretty strange effect. But I think you get the idea. The main thing that you have to take away at this point is that via a subviewport, you can place multiple nodes on a separate viewport and display this viewport inside of any other node that can display a texture. So whenever you see a texture, you can use the drop-down menu and assign any of these. And if you look through them, you can find some really interesting stuff. A viewport texture in particular is incredibly powerful. Time for the final chapter, in which we are going to talk about light. A light shader is going to run once for every fragment and for every light source. This could either be a point light 2D or a directional light 2D. And really important, this is going to replace the default light behavior. You will see in a second what that means. Finally, you can get a lot of basic properties like in a vertex or in a fragment shader, but you cannot get the UV coordinates, which is a bit limiting. Here are all the properties that you could be working with. And let's explore all of those in Godot right away. I have a new scene, light intro, with a sprite 2D that does not have a shader at the moment. All of this is inside of 6 light and 1 light intro, in which at the moment we only have this one scene. Now to use a light shader, we need a light first of all, for which you could use a point light 2D or a directional light 2D. I guess if I write light, you can see this a bit better. We have these two options. A directional light 2D is basically a sun, while a point light 2D is a single light source, which is also what I'm going to use the most. So create, and then nothing happened. Because for point light to work, you need to have a texture. Most of the time, this is going to be imported, but you can create a gradient texture 2D, and then you can see we have a light. This light is basically a texture that is going to be applied, and then we are mimicking a light source. So wherever this thing is white, we have a lot of light. Where this thing is black, we don't have light. And for a better light source, you would want to go to Fill and then set this to Radial. The front part should be 0.5 and 0.5. That way we are in the center, and the center should be white, while the outer parts should be black, which you can get by setting the gradient to inverted, like so. And then we have a light source that looks much better. Although you do want to make sure that the outer parts are black, so you don't cut off any of the light, which you can get by scaling down the gradient just a bit. Something like this looks alright. For the actual scale of the light, you want to go to Texture Scale. In there, you can scale up the entire thing, and there you can see we have a light source, in which you can also set the color of the light. Let's go with a reddish color, and the energy of the light, like so. These would be the most important properties that you are going to work with. And all of those you can also access via the shader, for which you want to apply the shader to the sprite 2D, not to the light source. Inside of the sprite 2D, as always, you want to go to Material, Shader Material, and in there, new shader. And then, for this part, I do not want to work with either the vertex or the fragment function. Instead, I want to uncomment the light function, like so, and then the light disappears. Because once you start using this light function, the default light behavior disappears, so you have to recreate it by hand. The most important property for that is light. This is a vector 4 that you can assign, for example, a 1, 0, and 0, so red color, and a 1 for the alpha values. That is giving us a red color without any kind of transparency, which is at the very least a decent start. To get an actually proper effect, you need to get a couple of properties that get you all of the properties of the light, like the color and the energy. For that, let's go through them step by step. Let's say I want to start with the light color. This is already giving us a really nice effect. This is the combination of the color and the texture. So if I change the color now, you can see the effect in real time, which is pretty handy. However, the energy at the moment doesn't do anything. To get this one, you want to multiply the light color with the light energy. This one here. And then you can see this is working. Now we can use both of the properties. Besides that, and let me get rid of the stuff so far, we can also get color. And this is the color that you're getting from the fragment function. So basically at the moment, we're getting the color from the texture and we are adding it to the original. If we subtract this value, then we are getting black because we are subtracting the original value. You can also set this to mix, then you don't get anything because now you're mixing the original color with itself. And with that, we have all we need to recreate the original light behavior. You want to have a vector 4 with color.rgb, so the original color value. This you want to multiply with the light color.rgb, and all of this we want to multiply with the light energy. For the alpha value, we want to get light color.a. And with that, if I go back to the properties, this shouldn't be set to mix. I want to add the color, and now you can see this much better. We get the color from inside of the color, and this I can change to, let's go with a yellowish value, like so. We can change the energy, this also works, and we can update the texture. Still works just fine. Although not what I want to do at the moment. And now that we have this part, we can change the light behavior. For example, if you wanted to invert the light, you could simply change this value and do things like 1 minus the light color, and this should be a 1 dot. You get a very different kind of effect. I guess for something a bit more realistic, you could multiply the light energy with the sine value of time, and then you are animating the entire thing, which at the moment looks a bit weird because this value becomes negative. But if I place it inside of the absolute function, like so, then we are getting a pulsing light, which looks pretty alright. Although once again, also not something I want to do at the moment. So let's get rid of this. And then we are back to a single light. Now, what is really important to understand is that this light shader is going to run once for every light source, which means if we have multiple lights, then this shader is going to run 2 times. Let me give them different colors, like so. We have a red and a yellow light. And for each of those, we're getting this shader. These values can also overlap, like so. And you basically, via this line, get the default light behavior. So if I mix them together, we're getting a more orangey color. Not something you have to think about most of the time. And for now, for simplicity, I want to work with only a single light source. This one here. Now, besides these properties, you have a few more. Let me comment out this bit and then assign light, the light direction. This at the moment is not going to work because light direction is a vector 3. So we have to place it inside of a vector 4 and set the alpha value to 1.0. With that, we're getting a slightly weird thing where we have green in the top, right in the bottom right, and yellow in the top left. The bottom right is blue. What happened here? And I think the best way to demonstrate is to look at the different parts of this vector. If you get light direction dot x and place all of this inside of a vector 3, then you can see this direction is a 1 if we're going left, -1 if you're going right, and a 0 if you are at the top or the bottom. For light direction dot y, you get pretty much the same thing, except on the y-axis. At the top, we have +1, and at the bottom, we have -1. I suppose a better way to demonstrate all of this is to create a float mask where we are using the step function with, let's say, 0.5 for now, and light direction dot x. And this mask I want to use inside of this vector 3, like so. Then you can see we're getting a much better shape. And this we can animate by creating a uniform float. Let's call it progress. And this should be a hint range from 0 to 1, which I want to use inside of the step function. And then inside of the shader parameters for the sprite 2D, the progress can go from 0 to 1. And then we are covering the entire range. And with that, we can do an exercise. I want you to create a lighthouse effect, like this one. I would recommend to use a rotation matrix. Other than that, this should be reasonably doable. Pause the video now and see how far you get. To get started, we have one cone, but we want to have it in both directions, which we can get by putting the light direction into the absolute function. And then we have both sides. And this is going to be a mask for the actual light that we want to use inside of this function. So let me comment out the stuff we have done before and reuse the light that we have seen earlier. All of this I want to multiply with the mask. And with that, we can see the light only to the left and to the right. Now to rotate this thing, we are going to need a rotation matrix. Let me copy it in. We have a matrix 2 rotation matrix with the usual trigonometry stuff to rotate the entire thing. The value that we are going to use is simply the time. Although you could change this thing to make it faster or slower, or have some kind of custom behavior. This rotation matrix we now want to use inside of this light direction. Although this should be a new vector2 variable, let's call it rotated light, for which we want to get the rotation matrix and multiply it with the light direction. This doesn't work at the moment because light direction has x, y, and z values. The z values don't really do anything, so you can ignore them. We only care about x and y. Once we have that, rotated light should be replacing the light direction. And with that, we are getting a rotating light, which we could also change. So if this is ×2, it's getting faster. And if we multiply it with 20, it becomes unreasonably fast. You get the idea. So with that, we basically have the light, and I guess for a lighthouse, this should be a bit more like this, and I guess a bit more red-ish. I don't know, play around and see what you like. Energy could also be more, and we could work with the texture scale. Just see what works for you. But with that, we have a very basic light shader. Next up, let's work on the light position. Using that, we can create some pretty interesting light effects. And once again, here I am in Godot with a new scene, light position, in which we have a sprite 2D and a camera. I forgot this one in the last part, but doesn't really matter. And finally, we have a light source, where the texture is a gradient texture 2D, the same I've used in the last part. Let me scale this one down a bit as well, like so. And then we have a custom color, a red color. The energy is set to 2, and finally the texture scale is set to 3. The result is a plain red light. On the sprite 2D, I do have a shader, which at the moment doesn't really do anything. And I want to uncomment the light function. So the light disappears because there's nothing in here. To recreate the basic light behavior, I want to get the light function and assign it a vector 4 with color.rgb multiplied with the light color.rgb multiplied with the light energy, like so. And for the final alpha value, we will need light color dot alpha. And with that, we have our light back. This looks pretty good. And now on this light, we want to get the position, for which we have two properties. The first one is the, well, light position. I suppose we can comment out the light we have used so far and instead do something like this, which is not going to work because this light position is a vector 3. So I want to place it inside of a vector 4, and the final value is going to be 1.0. With that, we are getting a yellow color. This once again is an indication that the values for x and y, so red and green, are much greater than 1, and we don't have any blue value. This light position gives you the center value of the light, so this point at the moment, and this is in canvas space. So we are working inside of this viewport for the actual dimensions. I suppose a good way to demonstrate would be to multiply all of this with 0.001, so the color is much less strong. And if I now go in the top left, we are getting no value here. The light position effectively becomes 0 and 0. So this light doesn't do anything. But if I go to the bottom right, we are back to a yellowish color. And if I go to the top, we're getting a red color. And if I go to the bottom left, we are getting a green one. And really important, we are only talking about the center of the light. This is the only point that matters. And besides the light position, we have the light vertex. This looks at every single light fragment, but we are still working inside of the canvas space. So if I move this thing around, you can see this changes. Just like before, if we are in the top left, we are at 0 and 0. And if we go to the bottom right, we are getting to 1 and 1 for x and y. And with that, we can get the center position and all the pixels around it, which you can already use. Let me recenter the entire thing like so. You can use these two properties together to get the vector to center, let's call it center position, for which I want to get the light vertex dot xy and subtract the light position, on which we also want to get the xy value. If I now use this value, let's say inside of the vector 4, where we want to get the center position dot x, center position dot y, and 0 for the blue color. You can see we get the color for every quadrant. And this, once again, is a gradient. If I multiply this value with some kind of number, let's say 0.01, then you can see the borders are blurring. Basically, if we are here, then x is going to be 0, and if we go further to the right, then we get increasingly large x values. And if we're only in this quadrant, then we don't have any y values. So this is a pure red color. If you go to this quadrant, you get both x and y values, so you have a yellow color. And in the top left, you get neither. So there we have negative values, and this is getting subtracted from the Godot logo, which ends up looking blue. If you wanted to remove this one, you would want to use the max function with 0, and then the actual value, and this you want to do for both of them. So max 0 and the center position. That way, these values in the top left go from negative to 0. Something that you could be doing, but not too important for now. What is instead really important is that via this function, you can get the center position and then the position of every single light fragment relative to that center. Once you have that, you could create, for example, a float circle, which is simply going to be the length of the center position. And I suppose a better word here instead of center position would be center distance, but I hope you get the idea. I want to comment out this line and reuse the original light behavior with this circle load. And then we get a cutout in the center. And if I zoom in and out, you can see that this is relative to the screen space. And for a proper circle, you want to use the step function with, let's say, 0.2, like so. And then in the center, we have a circle. Let's make the 0.5 so it's a bit larger. And I guess we should do a uniform float progress in which we have a hint range from 0 to 20, which I then want to use inside of the step function, like so. And then in the shader parameters, I can go to the sprite 2D, shader parameters, and increase the progress value. Now we have a proper circle cutout. I suppose I should do it like this and make this thing just a bit smaller. And besides that, what I also want to do is to create a float small circle where we are getting the step function with the progress minus some kind of width, which is going to be another uniform, which is going to go from 0 to 1. The second value is going to be what we have done in this circle via length and center position. These two values I then want to combine via a float cutout, and in here we want to get the circle minus the small circle, which is then going to give us a ring. So cutout multiplied with light color, and then we have to increase the width just a bit. You can see we are getting a circle, which right now is inverted. So what we want to do in here is to get the small circle minus the main circle. That looks better. And with that, we get a circle that we can animate. Pretty nice effect. And with that, we have a basic way to use light position. Although this we can push quite a bit further. And for that, let me comment out all the stuff we have done so far and not use the multiply with the cutout. And let me move all of this stuff a bit further down, because next up, I want to create a grid. Let's call this one grid, and we are going to use mod light vertex dot x and then some kind of size. Let's go with 20. And to visualize the entire thing, I want to go to the light function and multiply lightColor.a with the grid. And now you can see we are getting, I suppose these would be vertical bars, and this value I can change. Let's go with 100. Then it's a bit easier to see. And the way you want to think about it, for this light vertex, we are starting in the top left, because that's the top left of the viewport. And for the x values, we are going further and further to the right. For simplicity, let's say this point here is 100. And after that, we keep on increasing the numbers. So this one here could, for example, be 1000. Via the mod function and 100, we keep on going in this direction. But once we reach this point, we are going back to 0. So we always go from 0 to 100, and then we start again at 0. Because of that, these values here, when we start the cycle, are going to be 0. As a consequence, they will reduce the light alpha to 0. So basically, this value is going to be 0, this value is 100, and in between there, we have a range, meaning this value here would be a 10, in the middle, we would have 50, and on the right side, right before the end, we would have 99, which is super handy because all of that we can use inside of a step function, like so. And via that, if I set it to, for example, 20, we can tell Godot when to start making things invisible or visible. So when we start at the beginning, we are at 0, and the further we go to the right, the greater the value becomes. And via the step function, we tell Godot when to cut things off. This at the moment is going to cover the x values. And this we can copy and add in here, except now I want to get lightVertex.y. And with that, we are getting a grid. which is once again inside of the canvas space. So if I move the camera around, this is going to look a bit weird, but you get the idea. And I guess what we can also do is to add a few more uniforms. Uniform, I suppose we can call this the float cell underscore size with a default value of 20. Besides that, I want to have a gap with a value of 10. The cell size is going to be what we are using in here for the 100. The 20 is going to be the gap between them, like so. And with that, inside of the shader parameters, I can reset these values, and then inside of the cell size, I can increase this number as much as I want. Same with the gap. This looks pretty neat. And finally, you can multiply this with the cutout that we have created before. So let me uncomment all of this. And then I want to use this cutout with the grid. So in here, I want to have grid multiplied with the cutout. And then we do need some kind of width, most importantly, and then a bit of progress. And you can see we get a super interesting light effect. So if you want to highlight something, this could work pretty well. And all of this can be updated in real time, which is really, really handy. And to finish this part, I want you to create lots of dots via a light. Here's the end result. Pause the video now and see if you can figure this one out. For this kind of effect, let me add another comment. I want to have dots. With another float, dots. I think the best way to think about it is that we want to separate the space into a coordinate system, like so. Inside of every single one of these cells, we want to get the center and then measure the distance from that center. Once we have that, we basically have a circle. So, step by step. Number one, I want to get the mod value between height vertex dot xy and a vector 2 with the cell size. Let's say 20 for now. This is going to give us the cell size on the x and the y axis. So basically, for every single point, we will be down here or here or here. We are always in the bottom right. From that point, we want to go to the center, which means we want to subtract half of this value, which is going to be a vector 2 with 20 divided by 2. So with that, we have the center. This we have to turn into a length. I want to get the length of all of this. And this we should already see. So let me multiply light color A with dots. And there you can see something. To control the size here, we want to place all of this inside of a step function, where the first argument is this value, and the second one is going to be the size of the circle. Let's go with 5 for now. And then we have the circles. And once again, all of this should be uniforms. I think for the 20, we can reuse the cell size. So cell size here. And for the second value, this one should be a radius, which we do have to create. So float radius, default value of 10 is totally fine. And then you can increase this value. Looks pretty good. And also, what you can do is to multiply all of this, like we have done before, with the cutout that we have created earlier. And with that, you get a neat effect that you can customize as well. So once again, pretty cool. Alternatively, what you could also do, and for that, I want to add another variable. Let's call it float side. I basically want to have the grid on the left and the dots on the right, for which we can get the grid multiplied with light direction.x. Let's demonstrate what we are getting here. So I want to multiply the light color with the side. Now on the left side, we are getting the dots. Although on the right side, we are getting the negative values. And this shouldn't be the case. To get around that, I want to check if the light direction is greater than 0. this is going to return a Boolean, which we want to convert to a float. That way, we only get this on the left side. To that, we want to add the dots and multiply it with the float of light direction dot x being smaller than 0. And with that, we have a grid on the left, dots on the right, and this is pretty interesting. All of this could be multiplied with the cutout mask. I think at this point, you do get the idea what you can do with this kind of shader.